What if most of the universe is made up of something we cannot see or fully understand? Dark energy and dark matter, two elusive forces, shape and control the cosmos in ways that remain among the most profound mysteries, challenging our understanding of reality. Despite their presence being critical to the fabric of the universe, these forces remain nearly invisible to us, with their full nature and mechanics still hidden from our eyes. Yet within these cosmic enigmas lie objects so strange and unrecognizable that even the most advanced scientists are at a loss to explain them. Join us as we venture into the heart of these mysteries and explore the profound, puzzling forces of dark energy and dark matter. These forces, although distinct, both hold power that influences everything in the cosmos, yet in vastly different ways. And it all begins with the expansive, omnipresent force known as dark energy. Dark energy is a mysterious, almost otherworldly force that plays a crucial role in the expansion of the universe. To understand its effects, imagine the universe as a balloon that is continually being inflated. As the balloon expands, different sections of it move further apart. Dark energy is thought to be the driving force behind this ever-accelerating expansion, pushing galaxies farther away from one another at an increasing rate. This discovery was not always understood, but the clues came in the late 1990s when astronomers were studying distant supernovae, massive stellar explosions marking the end of certain stars' lives. These astronomers, while studying the light from these explosive deaths, had expected to find evidence that gravity, the attractive force between masses, was slowing down the rate of expansion, pulling galaxies back together. Instead, the opposite was true. The further they looked, the faster galaxies seemed to be moving away. This unexpected observation led scientists to propose the idea of dark energy, a radical concept suggesting that not only was space itself expanding, but that it was doing so at an accelerated pace, driven by an invisible force. Thus, the existence of dark energy was born, forever altering our view of the universe. Since its discovery, dark energy has become a central piece in modern cosmology, a fundamental component of our current understanding of the universe. Yet, despite its profound importance, dark energy remains one of the greatest unsolved mysteries in science. It accounts for roughly 68% of the total energy content of the universe, yet it is completely undetectable by conventional means. We can't observe it directly, and we can only infer its existence by looking at the universe's large-scale structure and how galaxies behave over time. Dark energy's counterpart, dark matter, serves a very different purpose, although it remains just as enigmatic. While dark energy is pushing galaxies apart, dark matter works invisibly to hold galaxies together. If dark energy can be thought of as a repulsive force, dark matter can be considered the invisible glue that binds galaxies and galaxy clusters, preventing them from flying apart under the immense forces of cosmic expansion. Imagine trying to hold a group of stars together in a cosmic dance. Dark matter is the unseen hand that provides the gravitational pull necessary to maintain this delicate balance. Despite dark matter being equally invisible to us, scientists have observed its effects. When light passes around massive objects in space, it bends, a phenomenon known as gravitational lensing. This bending of light is caused by the gravitational pull exerted by unseen mass. And this is how scientists have come to understand that there is more mass in the universe than we can observe. Similarly, by tracking the motion of galaxies, astronomers have inferred that there is far more mass present in clusters of galaxies than can be accounted for by ordinary visible matter. Dark energy, on the other hand, represents a force working against gravity. If dark matter is the force that holds things together, dark energy is the force that causes the universe to expand at an ever-increasing pace. It is as though the universe is filled with a repulsive force that drives it to stretch, inflate, and expand, much like a balloon that continually inflates. Unlike gravity, which pulls masses together, dark energy pushes galaxies apart. The significance of dark energy grows over time. As the universe expands, the effects of dark energy become more pronounced. In essence, dark energy accelerates the expansion of the universe, stretching the fabric of space itself. Initially, one might assume that gravity, being an attractive force, would slow the expansion. But dark energy does the opposite, pushing the universe apart and accelerating its growth. Over time, the expansion does not simply continue. it speeds up, and the rate of acceleration only grows faster. This phenomenon forces scientists to reconsider their understanding of the universe. The more we study dark energy, the more we realize how little we know about it. Despite its dominance in the cosmos, its nature eludes us. It is theorized that dark energy makes up around 68% of the universe's total energy content, but its actual composition remains a mystery. We cannot observe dark energy directly, and we are forced to rely on indirect methods, such as observing the behavior of distant galaxies and supernovae, to understand its presence. Each new discovery about dark energy adds another layer to our understanding of the universe and challenges our current theories of physics. For instance, some theories suggest that dark energy is a property of space itself. As the universe expands, new space is created, and this new space could have an energy density that exerts a repulsive force on nearby objects, pushing them apart. This concept is known as cosmological constant. According to this theory, dark energy remains consistent throughout the universe, and its properties do not change as space expands, just like a balloon that inflates but maintains the same surface tension no matter how big it gets. Other theories suggest that dark energy is not constant at all, but rather a dynamic field that can change over time in a concept known as quintessence. Quintessence proposes that the properties of dark energy could shift and evolve, just as weather patterns change over time. This means that dark energy might behave differently at various points in the universe's history, influencing how quickly the universe expands during different epochs. Some researchers are even considering modifications to our understanding of gravity itself. According to this theory, what we perceive as dark energy could be a manifestation of gravity behaving differently on large cosmic scales. Essentially, if gravity works differently on the largest scales of the universe, what we interpret as dark energy might actually be a result of altered gravitational laws. As scientists continue to gather data from new observations of distant galaxies, supernovae, and cosmic structures, these theories continue to evolve. The future of dark energy research promises to be one of the most exciting frontiers of modern astrophysics, as each new discovery could radically change our understanding of the universe. By studying the behavior of galaxies and galaxy clusters over time, scientists aim to understand the impact of dark energy on cosmic structures. The more we observe, the more we can refine our measurements and theories, inching ever closer to uncovering the truth behind dark energy's mysterious nature. The study of distant galaxies offers us a glimpse into the past, allowing us to observe the universe billions of years ago and trace its expansion. By comparing these observations with galaxies closer to home, we can measure how the universe's expansion has accelerated over time. One of the key methods used to study dark energy is the observation of supernova, exploding stars that serve as cosmic standard candles. These supernovae have a known brightness, which allows scientists to calculate their distance from Earth. By examining the apparent brightness of these explosions and analyzing their redshift, the shift of light towards longer wavelengths due to the expansion of space, researchers can infer how quickly the universe is expanding, and by extension, how dark energy is influencing this expansion. In the coming decades, as observational techniques and technologies continue to improve, scientists may be able to answer the fundamental questions surrounding dark energy. How does it interact with other forces in the universe? Why is it causing such rapid expansion? And most importantly, what is it really? As we peer deeper into the cosmos, we may finally unravel the true nature of dark energy and unlock some of the greatest secrets of the universe itself. Scientists also employ gravitational lensing, a technique in which massive objects such as galaxy clusters bend the light coming from more distant objects. This bending, caused by the warping of space-time, reveals crucial information about the amount of mass within these galaxy clusters and how the expansion of the universe affects the arrangement of matter. By carefully studying the patterns of this lensing, researchers can further probe the influence of dark energy, which is believed to play a significant role in shaping the universe's expansion. Combining methods like gravitational lensing with other tools, scientists are able to create a more detailed and comprehensive picture of the cosmic environment. Each new measurement helps to refine our understanding of dark energy's impact on the fate of the universe and its large-scale structures. This ongoing work is crucial for unraveling one of the greatest mysteries of the cosmos: dark energy. Dark energy is an enigmatic force that drives the accelerated expansion of the universe, pushing galaxies further apart at an ever-increasing rate. To better understand its influence, imagine the universe as a balloon being inflated. Initially, the expansion of this balloon was slow, but over time, something extraordinary occurred. The expansion began to accelerate. This acceleration is attributed to dark energy, which acts as an invisible force, relentlessly pushing galaxies away from one another. Remarkably, scientists believe dark energy makes up more of the universe than ordinary matter and energy combined, fundamentally altering our conception of the cosmos. As we look toward the far future, the influence of dark energy becomes even more pronounced. If this acceleration continues unchecked, galaxies will drift ever farther apart, and eventually, distant galaxies may become invisible. Their light will take longer to reach us than the rate at which space itself is expanding. In this distant future, a scenario known as the Big Freeze could unfold. In the Big Freeze, the universe would become an increasingly cold, dark, and empty place. Stars would burn out, their fuel exhausted, and they would leave behind black holes or neutron stars. As galaxies vanish from sight, the overall temperature of the universe would plummet. In this stark, inhospitable reality, the universe would enter an era of irreversible decline, raising profound questions about the ultimate fate of everything we see around us. Dark energy, in this context, is not merely a scientific curiosity. It is the central force shaping the evolution of the universe, and its influence is felt not only in the present day, but will continue to guide the cosmos toward its distant future in ways that remain elusive to us. One of the most valuable tools scientists use to investigate dark energy's role in the universe is the study of distant supernovae, particularly a class known as Type Ia supernovae. These explosive events mark the end of a star's life. Type Ia supernovae occur in binary star systems, where one star siphons material from its companion until it reaches a critical mass and detonates in a violent explosion. These supernovae are of great interest because they have a consistent peak brightness, making them reliable cosmic beacons. Just as the brightness of a lighthouse can tell you how far away it is, the apparent brightness of a Type Ia supernova allows scientists to measure its distance from Earth. By studying these supernovae, researchers have made an extraordinary discovery. The explosions are fainter than they would be if the universe were expanding at a constant or decelerating rate. Instead, their dimness points to an accelerating universe driven by an unseen force, dark energy. The dimming of these supernovae provides the evidence needed to confirm that something is pushing galaxies apart, and this force is what we now call dark energy. By charting the light from supernovae across vast distances and over time, scientists have been able to reconstruct the history of the universe's expansion. These studies have led to a deeper understanding of how dark energy influences the universe's structure and fate. The evidence gathered from these distant supernovae has helped establish that dark energy constitutes a significant portion of the total energy in the universe, altering its course in ways that challenge our traditional understanding of cosmic forces. Another key piece of evidence comes from the study of the cosmic microwave background, CMB, the faint radiation left over from the Big Bang. This ancient light, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe when it was only a few 100,000 years old. By analyzing the tiny temperature fluctuations across the sky, scientists can infer the density variations that existed in the early universe, shaping the formation of galaxies and large-scale structures. These fluctuations also help to determine the relative amounts of ordinary matter, and dark energy present in the universe. The CMB measurements have been instrumental in revealing the geometry of the universe and its overall density. If the density of the universe falls below a certain threshold, it suggests that dark energy is the dominant force. This dark energy, in turn, counteracts the effects of gravity and causes the universe to expand at an ever-increasing rate. Far more than just a remnant of the universe's past, The CMB serves as a crucial tool in studying the present and future behavior of dark energy. Its study is essential for unlocking the mysteries of the universe's expansion and the forces that shape it, offering a glimpse into the nature of dark energy and its profound impact on the cosmos. The phenomenon of dark energy stands as one of the most significant challenges in modern physics and cosmology. At its core, dark energy is an unknown force that constitutes a large part of the universe and drives galaxies apart at an accelerating rate. This force fundamentally challenges our understanding of gravity. Traditionally, gravity is considered a force of attraction, one that pulls objects toward each other. However, dark energy operates in the opposite manner, pushing galaxies away from one another. This behavior forces scientists to reconsider their models of the universe's structure and evolution, as the acceleration of the expansion contradicts the predictions of gravitational forces that should slow this expansion. The elusive nature of dark energy further complicates matters. While we can observe its effects, such as the movement of galaxies, we have yet to identify its true nature. It does not fit neatly into the categories of matter or energy that we understand. This ambiguity has led to numerous theories and debates, with some physicists speculating that dark energy may be a property of space itself, rather than a form of matter. Such ideas challenge our very understanding of the fabric of the universe. As researchers continue to investigate dark energy, they may find that the fundamental laws of physics need to be revised to account for this mysterious force, pushing the boundaries of our knowledge and understanding of the cosmos. Exploring the nature of dark energy presents significant technological challenges. Detecting its subtle effects requires advanced instruments capable of measuring minute changes in the universe's expansion rate and structure over immense distances. This demands the development of more sensitive telescopes and detectors capable of observing the faintest signals across the vast reaches of space. Additionally, the sheer scale of the universe means that collecting enough data requires a concerted effort from researchers, with technology powerful enough to cover enormous distances and gather information from a wide range of perspectives. The technological challenges are compounded by the need to overcome the limitations imposed by Earth's atmosphere. Advanced satellites and space missions are essential for observing dark energy from above the atmospheric distortions that interfere with ground-based telescopes. These missions, which require significant resources and time, are key to furthering our understanding of dark energy and its role in the cosmos. Yet, despite these obstacles, each new breakthrough brings us closer to understanding one of the most profound and mysterious forces in the universe. The quest to unlock the secrets of dark energy is ongoing, and as scientists continue to push the boundaries of what we know, they inch ever closer to unraveling one of the greatest mysteries of modern physics. Furthermore, data processing in the realm of modern cosmology presents a monumental challenge. The sheer volume of information gathered from astronomical observations is staggering. The task of sifting through these vast amounts of data to identify meaningful patterns, particularly those associated with dark energy, requires highly sophisticated algorithms and cutting-edge supercomputing power. However, even with these advanced tools at our disposal, the process remains an immense undertaking. The complexity doesn't end with the tools required to handle the data. There's also the issue of uncertainty. Dark energy, which governs the expansion of the universe, behaves in ways that are not yet fully understood. This enigmatic force presents a unique challenge when it comes to designing experiments and space missions. The technology we develop must be flexible, capable of adapting to unforeseen results, and prepared for unexpected findings along the way. This necessity for adaptability underscores the dynamic and exploratory nature of cosmological research. The technical difficulties we face today highlight the frontier of modern cosmology. We are on a quest to understand not only what is visible in the universe, but also the profound, invisible forces that shape it, forces like dark energy. This ongoing search to unravel the mysteries of the cosmos is what drives much of current scientific inquiry, providing a deeper understanding of the universe's structure, behavior, and ultimate fate. Dark matter, one of the most significant and elusive phenomena in our universe, is a prime focus of modern cosmology. While it is thought to account for a substantial portion of the universe's mass, it remains completely invisible to our current instrumentation. Imagine trying to assemble a jigsaw puzzle when most of the pieces are missing. That's the challenge scientists face when they try to understand dark matter. Though we can't observe it directly, we infer its existence through its gravitational effects on visible matter such as galaxies and galaxy clusters. Dark matter addresses a critical gap in our understanding of the cosmos, one that has confounded scientists for decades. To understand why dark matter is essential to our comprehension of the universe, we can begin by examining the formation and movement of galaxies. Galaxies, when observed, seem to be rotating at speeds that should cause them to tear apart if only the visible matter within them were at play. However, they remain intact. Something invisible must be exerting an additional gravitational force, which scientists attribute to dark matter. To put it simply, dark matter acts as the unseen scaffolding that holds galaxies together, preventing them from disintegrating as they spin. This invisible force allows galaxies to evolve and develop into the intricate structures we see today. In addition to holding galaxies together, dark matter plays a crucial role in shaping the large-scale structure of the universe. In the earliest moments following the Big Bang, dark matter's gravitational influence helped pull matter together, contributing to the formation of galaxies and their clusters. Without this invisible material, the universe would have developed very differently. The very existence of dark matter is therefore central to understanding how cosmic structures emerged and continue to evolve. As researchers delve deeper into this mysterious substance, they are gradually uncovering the story of the universe's origin, structure, and potential destiny. This ongoing investigation is a testament to humanity's insatiable curiosity and determination to understand not just what is visible to our eyes, but also the invisible forces that govern the cosmos. The mystery of dark matter dates back to the early decades of the 20th century, when astronomers began to notice peculiarities in the behavior of galaxies. When they observed these galaxies, scientists expected to see a specific pattern in their rotation, influenced by the visible mass within them, such as stars and gas. However, something odd was happening. Some galaxies appeared to be rotating far faster than expected, based solely on the visible matter they contained. This discrepancy led scientists to question if there might be something else at play, something that could not be seen. To help visualize this, imagine watching a carousel with a set number of horses. As the carousel spins, the horses on the outer edge move faster than those near the center. If you were only able to see the visible horses, you might assume the carousel is balanced. But if you notice that the outer horses were moving much faster than anticipated, you might suspect there was an unseen force at work. In the case of galaxies, this invisible force became known as dark matter. The term dark matter was coined in the 1930s by astronomer Fritz Zwicky, who was studying galaxy clusters. Zwicky found that the mass of the visible galaxies within a cluster wasn't sufficient to account for the gravitational pull needed to hold them together. His observations led him to hypothesize that there was a significant amount of invisible mass present, which he referred to as dunkel materie, or dark matter. Despite Zwicky's groundbreaking discovery, dark matter remained elusive for decades, and it wasn't until later research that more evidence began to accumulate. In addition to Zwicky's observations, studies of the cosmic microwave background radiation, the afterglow of the Big Bang, revealed subtle fluctuations that provided clues about the universe's composition. These findings, along with many others, solidified the idea that dark matter is a fundamental component of the universe, although it remains undetectable through conventional means. Today, scientists estimate that dark matter constitutes around 27% of the total mass energy content of the universe, even though it neither emits nor absorbs light. The challenge of detecting dark matter lies in the fact that it does not interact with electromagnetic radiation, which is the key to observing most objects in the cosmos. Despite not being able to observe dark matter directly, scientists have developed methods to infer its presence. One such method is gravitational lensing, a phenomenon where light from distant objects, such as galaxies, is bent as it passes through a massive object like another galaxy or a cluster of galaxies. This bending occurs because the mass of the foreground object, both visible matter and dark matter, creates a gravitational field that distorts the light's path. By studying how light bends, scientists can infer the distribution of mass within the lensing object, which includes both visible matter and the elusive dark matter. The bending of light through gravitational lensing provides powerful indirect evidence of dark matter. By measuring the amount of light bending, astronomers can estimate how much dark matter is present in a given area. This technique has enabled researchers to map the distribution of dark matter across the universe, revealing that it is not concentrated in clumps in the same way that visible matter is. Instead, dark matter tends to be more diffuse, spread out across vast regions of space. This has significant implications for our understanding of how galaxies and other cosmic structures form and evolve. Gravitational lensing offers another key insight into the behavior of dark matter. It shows how this invisible substance interacts with visible matter. For example, galaxies in the process of formation rely on the gravitational influence of dark matter to pull together gas and dust, which eventually condenses to form stars. Without this unseen scaffolding, galaxies would not be able to hold on to the gas necessary for star formation. Thus, dark matter plays a vital role in the creation and evolution of galaxies, acting as the cosmic glue that allows these massive structures to come into existence. In the search for dark matter, scientists are considering several potential candidates for the particles that could make up this elusive substance. One of the leading candidates is the weakly interacting massive particle, or WIMP. WIMPs are hypothetical particles that are massive enough to exert a significant gravitational influence, yet they interact only weakly with regular matter. This means that WIMPs could pass through ordinary matter, including stars and planets, without leaving any trace. This makes WIMPs extremely difficult to detect directly, but they are appealing because they fit well within existing theories of particle physics and could potentially be detected through their rare interactions with normal matter. Another candidate for dark matter is the axion, an incredibly light particle that has been proposed as a solution to certain problems in particle physics. If axions exist, they could form a type of dark matter known as cold dark matter, which behaves in a specific way that helps explain how galaxies and other large-scale structures form and move. There are also theories suggesting that sterile neutrinos, heavier versions of the neutrinos that we already know about, could account for dark matter. These particles would not interact with normal matter in the same way that regular neutrinos do, but they could still provide the necessary mass and behavior to fit the dark matter models. Finally, some scientists are exploring the possibility that the effects attributed to dark matter might actually be a result of modifications to our understanding of gravity. According to this view, gravity may behave differently at large scales than we currently understand, leading to effects that resemble those we associate with dark matter. Although these theories remain controversial, they present an intriguing alternative to the idea that unseen particles are responsible for dark matter. As researchers continue to search for direct evidence of dark matter, the scientific community remains energized by the possibilities that lie ahead. The discovery of dark matter, or at least confirmation of its precise nature, would mark one of the most significant breakthroughs in our understanding of the universe. It could open the door to a deeper, more comprehensive understanding of the cosmos, shedding light on the very foundations of space, time, and matter itself. In summary, dark matter is an invisible yet essential component of the universe. It provides the gravitational scaffolding that holds galaxies together, influences the large-scale structure of the cosmos, and plays a critical role in the formation and evolution of the universe's most massive structures. While much remains unknown about dark matter, scientists are actively pursuing a variety of experimental techniques to uncover its secrets. The search for dark matter is one of the most exciting and challenging areas of contemporary physics and cosmology, and it promises to yield groundbreaking discoveries in the years to come. In the vast expanse of the universe, where galaxies swirl and stars burn, an unseen force, invisible to the naked eye, plays a pivotal role in shaping the cosmos. Dark matter, this enigmatic and mysterious substance, is integral to the dance of the galaxies. Imagine a boat gliding across a vast ocean. The boat's course, though influenced by visible waves, is also subtly shaped by the invisible currents beneath the surface. These currents represent the gravitational pull exerted by dark matter, guiding the motion of galaxies in ways that are not immediately apparent. It's not just a passive backdrop to the cosmos, but a force that actively affects the very way galaxies move and interact with each other. Galaxies, vast collections of stars, gas, and dust, behave in a manner that is governed by the presence of dark matter. Its gravitational influence is so profound that it alters the rotation of galaxies, causing them to spin much faster than what would be expected based solely on the visible matter we can observe. This behavior hints at the presence of a hidden mass, dark matter, acting as a gravitational anchor, keeping everything in motion. Without dark matter, galaxies would likely spin apart, unraveling the intricate balance that allows them to persist over time. More than just an invisible force, dark matter is thought to form colossal halos around galaxies. These halos act like an invisible cocoon, enshrouding galaxies in a protective layer. This structure plays an essential role in the life cycle of galaxies, particularly in the process of star formation. The gravitational well created by dark matter halos slows down the escape of gas and dust from galaxies, thus allowing these essential materials to stay within the galaxy longer. In turn, these materials can condense and form new stars, creating the vibrant stellar nurseries that give birth to future generations of stars and planets. However, the role of dark matter doesn't end there. When galaxies collide, an event that happens more frequently than one might expect, the gravitational influence of dark matter dictates the dynamics of these interactions. The presence of dark matter can determine how two galaxies merge, how their stars are redistributed, and even how new structures emerge from these cosmic collisions. These mergers can trigger spectacular bursts of star formation, igniting a new era of activity in the galaxy's life cycle. Thus, dark matter is not only a silent participant in the creation of galaxies, but also a key player in the evolutionary processes that drive the ongoing reshaping of the universe. Dark matter's contribution to the structure, stability, and evolution of galaxies cannot be overstated. It sets the stage for their formation, helps them evolve, and ensures their cohesion as they traverse the vast distances of the universe. Without dark matter, the universe would be a fundamentally different place. The galaxies we see strewn across the night sky would be absent, and the very fabric of the cosmos as we know it would lack the richness and complexity we take for granted. Yet, despite its importance, dark matter remains one of the most elusive and challenging subjects of study in modern physics. This invisible substance makes up nearly 27% of the universe's total mass energy content, yet it cannot be observed directly. Unlike ordinary matter, which emits light and energy that can be captured by telescopes, dark matter is undetectable by conventional means. It neither absorbs, emits, nor reflects light, making it completely invisible to the traditional tools we rely on to observe the cosmos. To unlock the secrets of dark matter, scientists around the world are employing a range of cutting-edge experiments, each designed to detect the subtle traces that might reveal the existence of this elusive substance. One of the leading candidates for dark matter is a type of particle known as weakly interacting massive particles, or WIMPs. These particles are believed to be incredibly difficult to detect, as they only interact very weakly with ordinary matter. Nevertheless, scientists are tirelessly searching for signs of these particles in experiments like those conducted at the Large Hadron Collider, LHC, where the conditions mimic the extreme energies present in the early universe. By smashing particles together at high velocities, physicists hope to recreate the conditions that might allow WIMPs to reveal themselves. In addition to large-scale particle accelerators like the LHC, other efforts are underway in underground laboratories, where the detectors are shielded from cosmic rays and other sources of interference. The Lux-Zeppelin experiment, for example, is set up to capture the rare and faint interactions between dark matter particles and ordinary matter. These highly sensitive detectors aim to observe any signals that might be produced by the collision of dark matter with atomic nuclei. The hope is that by detecting these minute interactions, scientists can confirm the presence of dark matter. Another promising method for detecting dark matter involves cryogenic techniques, where materials are cooled to extremely low temperatures in order to reduce the amount of background noise from other particles. At these frigid temperatures, any small amount of energy imparted by a dark matter particle colliding with an atom can be more easily detected, providing another potential avenue for discovery. Additionally, researchers are also investigating alternative theoretical candidates for dark matter, such as axions, hypothetical particles that are much lighter than WIMPs, but could still account for the observed gravitational effects attributed to dark matter. Experiments like the Axion Dark Matter Experiment, ADMX, use strong magnetic fields and ultrasensitive equipment to look for signs of these particles, which might emit faint signals under the right conditions. The pursuit of dark matter detection, though rife with technological challenges, is driven by a profound curiosity about the nature of the universe. Every experiment, whether successful or not, provides valuable data that brings us a little closer to answering one of the most fundamental questions in science: what is dark matter, and how does it shape the universe we see around us? On a larger scale, dark matter is a key player in the formation and organization of galaxies and galaxy clusters. Unlike ordinary matter, which makes up everything we can see, stars, planets, and other celestial bodies, dark matter cannot be directly observed. Its presence, however, is inferred from its gravitational effects on visible matter. In the aftermath of the Big Bang, as the universe began to expand, small density fluctuations created the seeds for the first cosmic structures. Dark matter, being far more abundant than ordinary matter, began to clump together under the influence of its own gravity. This clumping formed a sort of scaffolding throughout the universe, guiding the formation of galaxies. Ordinary matter, in the form of gas and dust, was drawn toward these clumps of dark matter, leading to the birth of the first galaxies. Imagine this process as creating a net, with the knots in the net representing areas of higher dark matter concentration. Ordinary matter is drawn into these knots, where the intense gravitational pull triggers the collapse of gas clouds, initiating the process of star and galaxy formation. Over time, these structures coalesce into vast cosmic formations, such as galaxy clusters and superclusters, which are massive conglomerations of galaxies bound together by gravity. This distribution of dark matter is not random. It influences the movement of galaxies across the cosmos. Rather than galaxies being scattered haphazardly, they tend to align along specific paths dictated by the underlying structure of dark matter. These paths form the cosmic web, a vast network of galaxies interlinked by the gravitational framework laid out by dark matter. Within this web, denser regions of dark matter correspond to areas in galaxies, while vast empty voids exist where dark matter is less concentrated. In this way, dark matter acts like the glue that holds the universe together, organizing galaxies into the intricate filament-like structures we observe today. The cosmic web, then, is a testament to the invisible influence of dark matter. It organizes not only the formation of galaxies, but also their long-term movement and evolution. Over billions of years, this invisible framework has shaped the structure of the universe, influencing the formation and interactions of galaxies and ensuring that the rich tapestry of stars, planets, and cosmic phenomena we observe today is possible. The distinction between dark matter and ordinary matter lies in their interaction with light. Ordinary matter interacts with electromagnetic radiation, light, allowing it to be detected using telescopes and other instruments. Dark matter, however, is completely transparent to light. It does not emit, absorb, or reflect any electromagnetic radiation, making it impossible to observe directly with traditional instruments. The only way we know dark matter exists is by studying its gravitational effects on ordinary matter. For instance, when astronomers observe the rotation of galaxies, they find that stars on the outer edges of galaxies are moving much faster than expected, based on the visible matter in the galaxy. If only the stars, gas, and dust were present, these stars would be flung out into space. Yet they remain tightly bound within the galaxy, indicating that there is an unseen mass, dark matter, providing the necessary gravitational pull to keep them in place. Similarly, when astronomers study galaxy clusters, they find that the galaxies within the clusters move in ways that suggest there is more mass present than what can be accounted for by visible matter. This extra mass, again, is attributed to dark matter. Through its gravitational influence, dark matter shapes the universe's structure and dictates the interactions between galaxies. Its presence is felt in the way galaxies spin, the way they interact during collisions, and the way they are distributed across the vastness of the cosmos. Dark matter is not merely a passive entity, but an active participant in the evolution of the universe, shaping the cosmos in ways that remain hidden but profoundly impactful. Understanding dark matter and ultimately detecting it will reveal not just the composition of the universe, but the deep mechanisms that govern its formation, structure, and evolution. The universe is full of mysteries, many of which remain tantalizingly elusive, despite the remarkable strides we've made in exploring the cosmos. Among these, one of the most profound enigmas is dark matter, an invisible, intangible substance that plays a critical role in the universe's structure and behavior. While dark matter remains undetectable through traditional methods, its presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. By studying the cosmic microwave background, the faint afterglow of the Big Bang, researchers have begun to unravel the secrets of this elusive force, revealing that it is an indispensable part of the cosmic landscape. It's a fascinating puzzle, one that offers a glimpse into the universe's deeper layers, pushing the boundaries of our understanding and offering new pathways for future discovery. The idea that the universe is far more than what we can directly observe has captivated scientists and astronomers for decades. Through sophisticated tools and techniques, researchers have learned that the universe is not just made of visible matter, like stars, planets, and nebulae, but also an invisible substance that exerts significant influence. Dark matter is that substance. It does not emit, absorb, or reflect light, and so it remains hidden from conventional telescopes. But despite its invisibility, dark matter's gravitational effects are undeniable, guiding the motion of galaxies, influencing the formation of large-scale cosmic structures, and shaping the way the universe evolves. Understanding dark matter is crucial because it constitutes a substantial portion of the total mass of the universe. While we cannot observe it directly, its influence is everywhere. Dark matter holds galaxies together, keeping them from spinning apart at impossible speeds due to the forces generated by their visible components alone. Without dark matter, the galaxies would break up, scattering their stars and gas in all directions. Yet, when we look at galaxies, they behave as if there is much more mass present than we can see. This is the fundamental clue that dark matter exists. It's the unseen glue that binds the visible matter together, creating the cosmic structures we observe. The existence of dark matter helps scientists understand how galaxies are distributed across the universe. This invisible force is a key factor in determining the large-scale architecture of the cosmos. It affects how galaxies group together, forming clusters and shaping the cosmic web, the vast, filamentary structure that spans across the universe. This web-like arrangement is crucial for understanding the universe's evolution, as dark matter helps to anchor the galaxies in place, dictating their distribution and movement. One of the most exciting prospects for future research is the possibility of discovering new types of galaxies, perhaps even entirely unknown ones. By continuing to study the gravitational effects of dark matter on galaxies, scientists may uncover new forms of galactic structure, which could have profound implications for our understanding of galaxy formation and the broader history of the universe. In fact, dark matter might also play a role in the creation of galaxies themselves, providing the unseen force that allows them to coalesce and grow in the early stages of the universe's life. Beyond shaping the distribution of galaxies, dark matter also influences their motion. When we study how galaxies move within clusters or along the cosmic web, we notice that their velocities can't be fully explained by the visible matter alone. This discrepancy is another strong indication that something unseen is at work. By examining the movement of galaxies, scientists are able to infer the presence of dark matter, and by studying its effects more closely, they can begin to unravel its nature. But what is dark matter made of? Is it composed of unknown particles, or is it some exotic form of matter that defies our current understanding of physics? This remains one of the most tantalizing questions in astrophysics. Researchers are actively exploring various possibilities, from the idea of dark matter being composed of weakly interacting massive particles, WIMPs, to the notion that it might involve something even more bizarre, such as axions or other exotic particles. Each new piece of data, each new observation, brings us closer to identifying the true nature of this elusive substance. And with advancements in technology and new observational techniques, scientists hope to make significant progress in answering this question in the coming years. The next generation of telescopes and observational tools promises to probe deeper into the universe than ever before, reaching areas that have been previously out of reach. As we peer further into the cosmos, we will be able to observe distant galaxies and structures, gathering data that could provide new insights into the role of dark matter. By studying the way light bends around massive objects, a phenomenon known as gravitational lensing, scientists can map out the distribution of dark matter in galaxy clusters and other large-scale structures. This technique has already provided valuable information, but with more advanced instruments, it will allow us to see the universe in ways that were once unimaginable. The implications of dark matter extend far beyond simply solving a cosmic riddle. They offer us a gateway to a deeper understanding of the universe itself. The study of dark matter touches on fundamental questions about the origins and fate of the cosmos. What is the universe made of? How did it come to be, and where is it headed? Dark matter may hold the answers to these questions, helping us unlock some of the deepest mysteries of existence. The search for dark matter is not just a theoretical exercise. It has profound implications for the future of astrophysics and our understanding of the universe. As researchers continue to probe the unknown, we are piecing together the cosmic puzzle, inching ever closer to a more complete picture of the universe's composition. With each discovery, whether it's a new galaxy, a new particle, or a new way of observing the cosmos, we are uncovering new layers of the universe's story, one that may ultimately transform our understanding of everything from the formation of galaxies to the very nature of reality itself. In addition to dark matter, another fundamental mystery of the cosmos lies in the heart of black holes. These enigmatic objects, born from the collapse of massive stars, have long fascinated scientists and captured the imaginations of the public. Black holes are regions of space where gravity is so intense that not even light can escape. Once a massive star exhausts its nuclear fuel, it can no longer resist the gravitational forces pulling it inward. This leads to a catastrophic collapse, creating a singularity, an infinitely dense point at the center of the black hole, surrounded by an event horizon, the boundary beyond which nothing can escape. The formation of a black hole is the ultimate fate of certain stars. Throughout their lifetimes, stars fuse elements in their cores, producing energy that counteracts the inward pull of gravity. However, when the fuel runs out, this delicate balance is disrupted, and the star begins to collapse under its own weight. In some cases, this results in a supernova, an explosive outburst that blasts away the outer layers of the star, leaving behind a dense core. If the core's mass is sufficiently large, this collapse continues until the core becomes a black hole, creating an environment where the laws of physics break down. One of the most intriguing features of black holes is the event horizon, a point of no return. Once something crosses this boundary, it is irreversibly drawn toward the black hole's singularity. The extreme gravitational forces within the event horizon distort space and time in ways that are difficult to fully comprehend. Time itself behaves differently near a black hole, stretching and warping as it gets closer to the singularity. The physics of this region remain mysterious, and while scientists have made significant progress in understanding black holes, much remains unknown, especially about what happens inside the event horizon. At the heart of every black hole lies the singularity, a point where the mass of the black hole is concentrated and where gravitational forces become infinitely strong. The singularity is one of the most perplexing aspects of black hole physics. The laws of physics, as we understand them, break down at this point, and it remains unclear what happens to matter and energy that fall into a black hole. Is it destroyed, or does it undergo some radical transformation? These questions remain unanswered, and the singularity is likely to remain one of the most fascinating and confounding puzzles in astrophysics. Black holes can vary in size, with stellar black holes being the most common. These form from the collapse of massive stars, and their masses typically range from a few times the mass of our Sun to several dozen times greater. Supermassive black holes, on the other hand, are found at the centers of most galaxies, including our own Milky Way. These giants can have masses billions of times greater than the Sun's. The study of black holes continues to be a vital area of research, as they offer a unique window into the most extreme conditions of space and time, pushing the limits of our understanding of the universe. Both dark matter and black holes represent the boundaries of our knowledge. They challenge our current models of physics, offering tantalizing glimpses into realms of the cosmos where the usual rules don't apply. As scientists continue to probe these mysteries, they are likely to uncover new theories that will revolutionize our understanding of the universe, changing the way we think about matter, gravity, space, and time itself. The search for answers is ongoing, and the discoveries of the future promise to be as profound and transformative as any in the history of science. However, supermassive black holes, which lie at the very heart of most galaxies, including our own Milky Way, are capable of containing an amount of mass that boggles the imagination. These titanic objects can hold anywhere from millions to even billions of times the mass of our Sun. Yet, despite their immense power and gravitational pull, there is another class of black holes that eludes even deeper understanding: intermediate black holes. Their existence is still a matter of intense scientific speculation, with researchers continuing to hunt for definitive proof of their presence. As we delve further into the study of black holes, we unlock more profound insights into the nature of gravity, space-time, and the fundamental forces that shape the universe. Each new discovery about these cosmic behemoths reveals new layers of complexity, underscoring how much more there is to learn about these enigmatic giants. Black holes themselves are fundamentally defined by one thing: the event horizon. This boundary marks the point of no return, beyond which nothing at all can escape the black hole's insatiable grasp. It is as though the event horizon serves as a cosmic door with no way to open it again once it's crossed. Imagine that. Once you cross it, there's no going back. The pull of the black hole at the event horizon is so fierce that it overcomes even the speed of light, which is otherwise the universe's ultimate speed limit. This explains why black holes appear to be utterly black. They don't emit any light that can escape, making them invisible to the human eye. As any object gets closer to this boundary, it undergoes dramatic changes. For instance, let's consider a star heading toward a black hole. As it falls into the black hole's clutches, it gets stretched and compressed in a process known as spaghettification. The gravity between the star's side nearest to the black hole and the side farther from it is so different that the star is elongated into a thin, elongated shape, like a strand of spaghetti. This phenomenon highlights just how intense the forces near a black hole can be. Meanwhile, for an observer looking from afar, time behaves in strange ways as the object approaches the event horizon. As the object gets closer, it appears to move more and more slowly, almost as if it were frozen at the event horizon's edge. Eventually, it fades from view. This optical illusion is a consequence of time distortion caused by the black hole's extreme gravitational field. For the object or person crossing the event horizon, however, they would pass through without feeling any different. They would not perceive the time stretching that occurs for those watching from the outside. Inside the event horizon, the very laws of physics, as we understand them, start to unravel. This region is a profound mystery where the conventional rules governing space-time cease to apply. It is within this boundary that our understanding of reality begins to break down entirely. The fabric of the universe, which seems so stable and predictable on large scales, starts to behave in ways that challenge everything we think we know about the cosmos. Since direct observation of black holes is impossible due to their very nature being invisible and shrouded in darkness, scientists have developed innovative techniques to study their presence and behavior indirectly. One of the most prominent methods involves studying the effects black holes have on their surroundings, particularly the behavior of light. When matter, whether gas, dust, or even entire stars, gets pulled toward a black hole, it forms an accretion disk. This swirling disk of material is subjected to immense friction as the matter spirals inward, which causes it to heat up and emit powerful radiation. This radiation, often in the form of X-rays, can be detected by telescopes, giving scientists crucial insights into the black hole's mass, spin, and the dynamics of the material surrounding it. In addition to light, scientists also make use of gravitational waves to study black holes. These waves are ripples in space-time that occur when massive objects, especially black holes, move or collide with each other. When two black holes merge, they produce a burst of gravitational waves that travel across the universe, carrying with them information about the mass and spin of the black holes involved in the collision. Specialized detectors around the world, such as LIGO and Virgo, are capable of picking up these faint signals, enabling researchers to deduce important characteristics of black holes from these distortions in space-time. Another fascinating avenue of research lies in the study of the accretion disks that form around black holes. These disks, made up of gas, dust, and other cosmic debris, provide important clues about the black hole itself. By analyzing the speed at which material is being drawn into the black hole, scientists can estimate the black hole's size and behavior. The faster the gas spins, the more mass the black hole is likely to have. The properties of these disks also reveal details about the complex interactions between the black hole's immense gravitational forces and the matter surrounding it. The combination of these methods has significantly expanded our understanding of black holes. Although we cannot directly observe them, scientists have developed a more complete picture of these mysterious objects by piecing together information from the surrounding environment. Every discovery adds a new layer to our knowledge of the black hole's behavior and its effects on the fabric of space-time. Perhaps one of the most groundbreaking developments in recent years has been the work of the Event Horizon Telescope, EHT. This network of radio telescopes around the world achieved a historic milestone in 2019 when it captured the first ever image of a black hole. This image showed the supermassive black hole at the center of our galaxy, known as Sagittarius A Sty, and another black hole in a distant galaxy, M87. Before the EHT's achievement, black holes were primarily theoretical constructs, objects whose presence was inferred by the gravitational influence they exerted on nearby stars and gas. But with the EHT's success in imaging the shadow of the black hole, scientists now had the visual proof they needed to confirm their existence. The shadow in the image represents the event horizon itself, the point beyond which nothing can escape the black hole's grasp. By imaging this shadow, the EHT not only confirmed the presence of black holes, but also provided an anchor for scientists to study their properties more closely. This breakthrough allowed researchers to measure the size of these supermassive black holes, which is consistent with theoretical predictions based on their mass, which can range from millions to billions of times the mass of the Sun. Additionally, the data obtained by the EHT revealed important details about how matter behaves close to the event horizon, such as the powerful jets of energy emitted by black holes, which can extend for thousands of light years into space and influence entire galaxies. These discoveries are far from just confirming the existence of black holes. They have opened up a whole new frontier of research in astrophysics. The EHT's work bridges the gap between theoretical models of black holes and the observable universe, allowing scientists to explore the fundamental nature of space-time, gravity, and the very fabric of the cosmos. Black holes do not exist in isolation. They have profound effects on their surrounding environments. Their immense gravitational pull influences the motion of stars, gas, dust, and even entire galaxies. As matter falls into a black hole, it forms an accretion disk, and the friction between the particles within the disk causes them to heat up, emitting enormous amounts of energy. In many cases, this energy is emitted as light, which allows astronomers to detect black holes despite their otherwise invisible nature. The gravitational influence of black holes can also affect the dynamics of entire galaxies. Supermassive black holes, located at the centers of most galaxies, including the Milky Way, serve as anchors around which stars, gas, and other structures orbit. This central role in the formation and evolution of galaxies has far-reaching implications. For instance, the energy emitted by a black hole can heat surrounding gas, which in turn can trigger or suppress the formation of new stars. In other cases, the turbulence caused by a black hole can stir up the interstellar medium, affecting the rates at which stars are born. On a grander scale, the presence of black holes has an impact on the overall evolution of galaxies. The balance between star formation and the gravitational influence of black holes can shape the development of galaxies over billions of years. By controlling the gas supply and regulating the turbulence within the galaxy, black holes play an essential role in determining how galaxies grow, evolve, and die. Through the study of black holes, we are not only learning about these fascinating objects themselves, but also uncovering deeper truths about the universe at large. With every new observation, every new discovery, we peel back another layer of the cosmic mystery, gradually uncovering the true nature of reality. While much remains unknown, one thing is certain. Black holes are key to understanding the most fundamental questions about space, time, and the universe. Black holes, once considered mysterious, isolated cosmic objects, have transformed into fundamental players in the vast, complex universe. Their power, influence, and impact stretch far beyond their gravitational grasp, shaping not only their immediate surroundings, but the very fabric of space-time itself. When black holes collide or merge, they unleash gravitational waves, ripples in the space-time continuum that travel across the universe, detectable even billions of light years away. These gravitational waves, the echoes of cataclysmic events, provide us with a powerful tool to understand the fundamental workings of the universe. They reveal crucial information about the black holes themselves, about the nature of space and time, and about the hidden forces shaping the cosmos. This seismic disturbance in space-time isn't merely a theoretical concept. It is a groundbreaking discovery that allows scientists to probe the universe in entirely new ways. Black holes are not just dark, isolated regions. They are dynamic forces that interact with their surroundings, leaving an indelible mark on the evolution of galaxies and the structure of the universe. Supermassive black holes, those colossal entities that reside at the centers of most galaxies, including our own Milky Way, serve as the central engines of galactic development. Picture them as powerful engines that not only govern the fate of their host galaxies, but actively participate in their growth and transformation over billions of years. When a galaxy forms, it begins with a vast amount of gas and dust. The gravitational pull of a supermassive black hole is immense, drawing this material inward and creating a swirling accretion disk, a turbulent whirlpool of gas spiraling towards the event horizon. As the gas spins faster and faster, it heats up to extreme temperatures, emitting an intense burst of radiation that can be observed across the universe. This energy output doesn't just illuminate the black hole, it influences the galaxy's evolution, controlling star formation within it. Some of the energy generated by this process is so powerful that it can expel gas and dust, preventing new stars from forming and slowing the galaxy's growth. This phenomenon, known as feedback, plays a pivotal role in determining how many stars a galaxy will produce and how the galaxy itself will evolve. In an active black hole, the feedback may be so strong that it halts star formation entirely, while in a quieter black hole, the galaxy may be able to continue growing, fueling bursts of star creation. Moreover, supermassive black holes affect the very structure of their galaxies. The gravitational forces they exert ripple outwards, affecting the orbits of stars and gas within the galactic core. Over time, this gravitational influence helps shape the rotation of the galaxy, organizing it into a more stable, cohesive system. This gravitational interaction also affects the galaxy's overall shape, helping to define its spiral arms or elliptical form. In cases where galaxies collide and merge, the supermassive black holes at the centers of each galaxy will eventually merge as well, further altering the galaxy's structure. These mergers can regulate star formation in the new combined galaxy, and may even lead to the birth of a much larger galaxy. Thus, black holes, particularly the supermassive ones at the heart of galaxies, are not just passive observers of the cosmos, they are active participants in the ongoing story of galactic evolution. They shape the very nature of galaxies, influencing the balance between star creation and destruction, the distribution of matter, and even the formation of galaxy clusters that populate the cosmic web. At the very core of every black hole lies a singularity, a point of infinite density where the laws of physics as we currently understand them cease to function. Current theories suggest that all the mass of the black hole is concentrated at this singularity, creating an infinitely small point that warps space and time to the most extreme degrees imaginable. In this realm, gravity becomes so powerful that nothing, no matter, no radiation, not even light, can escape. This is the very essence of a black hole, a region where space-time is distorted beyond recognition, challenging our most fundamental ideas about the nature of reality. The singularity represents one of the most profound mysteries in physics. Scientists have yet to fully understand what happens within this infinitely dense point. The most widely accepted theory of gravity, Einstein's general theory of relativity, breaks down at the singularity, leaving us with a question that has yet to be answered. What happens when space and time bend to such extremes? One leading hypothesis is that the singularity might not be a point at all, but rather a region of incredibly high density, a shift that would require a reevaluation of how we think about the structure of black holes. This approach challenges conventional views and suggests that the intense gravitational forces near the singularity might alter space itself, potentially leading to entirely new behaviors that defy current understanding. Another intriguing aspect of black hole singularities is their potential relationship with quantum mechanics, the theory that governs the behavior of subatomic particles. The combination of quantum mechanics and general relativity, two of the most successful frameworks in physics, remains one of the greatest unsolved problems. Some theorists speculate that at the singularity, quantum effects could override the predictions of general relativity, leading to unexpected consequences for the nature of gravity, matter, and space-time. Furthermore, there are ideas that suggest time itself may behave unusually near the singularity. Under the extreme conditions of a black hole, time might slow down, speed up, or even reverse itself, leading to radical new insights into the nature of time itself. Despite the advancements in theoretical physics, the true nature of black hole singularities remains elusive. The exploration of these enigmatic regions offers the potential for groundbreaking discoveries that could forever alter our understanding of the universe. New technologies, such as advanced telescopes and improved computational models, may eventually provide the insights needed to unravel the mysteries of singularities and offer a deeper understanding of the fundamental forces of nature. One of the most groundbreaking discoveries in recent years is the detection of gravitational waves, which occur when massive objects, such as black holes, move in extreme ways. These waves, ripples in the fabric of space-time, are generated during cataclysmic events like the collision or merger of black holes. As two black holes spiral toward each other, they release enormous amounts of energy in the form of gravitational waves, which travel outward from the event and propagate across the universe. These waves carry information about the events that created them, much like sound waves carry information about their source. By measuring these waves, scientists can gain insights into the properties of black holes, such as their masses, spins, and the way they interact with one another. Detecting gravitational waves requires highly sensitive instruments, such as interferometers, which can measure incredibly tiny changes in the distance between objects as the waves pass through space. Even the most minute distortions in space-time, smaller than the width of a proton, can be detected by these instruments. The ability to measure such small changes allows scientists to confirm the existence of black holes and study them in ways that were previously unimaginable. By observing gravitational waves, we can directly witness black hole mergers and interactions that would otherwise remain hidden from traditional telescopes. This has opened up a new era of astrophysical research, allowing us to probe the inner workings of black holes and deepen our understanding of general relativity. Through the study of gravitational waves, we are not only learning more about black holes, but also gaining a deeper understanding of the universe itself. These waves provide insights into the birth and evolution of black holes, the formation of galaxies, and the way in which gravity and space-time interact on the largest scales. Gravitational wave astronomy is an emerging field that promises to expand our knowledge of the cosmos, offering unprecedented views into the most extreme and mysterious events in the universe. Black holes are not isolated phenomena, but are integral components of the cosmic web, the vast structure that connects all galaxies and dark matter. Picture the universe as an immense, intricate web woven together by galaxies, dark matter, and the forces that govern their interaction. At the intersections of this web, black holes sit, influencing their surroundings and helping to shape the larger cosmic structure. They are crucial not only in the evolution of galaxies, but also in the formation of galaxy clusters, where their gravitational forces help pull galaxies together into tightly knit groups. In the early universe, when matter was more concentrated in dense regions, black holes likely formed from collapsing stars. As they devoured surrounding material, they released enormous amounts of energy, which could influence the formation of new stars. The energy output from a black hole can heat up nearby gas, suppressing star formation in some cases, while in others it can create a balance that allows stars to form more efficiently. In this way, black holes actively regulate the rate of star formation, helping to maintain the overall structure of their galaxies. On a larger scale, the gravitational pull of black holes contributes to the formation of galaxy clusters, groups of galaxies held together by the interplay of gravity and dark matter. These clusters are fundamental building blocks of the universe, influencing the distribution of galaxies and shaping the cosmic landscape. Black holes, with their immense gravitational forces, play a central role in this process, ensuring that galaxies are drawn together, maintaining a delicate balance in the fabric of the universe. Through their interactions with galaxies and galaxy clusters, black holes reveal much about the forces that govern the universe. They challenge our understanding of gravity, space, and time, raising questions about the nature of reality itself. By studying black holes, we gain insight into the deepest aspects of the cosmos, exploring the limits of physics and the fundamental laws that govern the universe. Black holes are not merely cosmic vacuums sucking in matter and energy. They are powerful, active forces that shape verse in profound ways. They influence the formation of galaxies, regulate star formation, and contribute to the structure of the cosmic web. At the heart of every black hole lies a singularity, a point where the very fabric of space-time breaks down, offering an opportunity to explore the deepest mysteries of the universe. Through the detection of gravitational waves, we are gaining unprecedented access to the behavior of black holes, and with further advancements in technology and theoretical physics, we are poised to uncover even more about these enigmatic entities. As we continue to study black holes, we are not only exploring the universe, but also pushing the boundaries of our understanding of reality itself, revealing the true nature of the cosmos. Gravitational waves, these ripples in the very fabric of space-time, emerge as some of the most astonishing and revealing phenomena in the universe. At their core, gravitational waves are fluctuations in the curvature of space-time caused by the movement of massive objects, such as when two black holes orbit each other in an intricate cosmic dance. As these black holes spiral inwards, their eventual collision releases vast amounts of energy, rippling across the universe in the form of gravitational waves. These waves propagate outward, traveling across unfathomable distances, undeterred by obstacles like the cosmic dust or distant galaxies that might stand in their path. The very detection of these waves offers an invaluable glimpse into a world we cannot directly observe. When scientists detect gravitational waves, they are capturing a subtle yet profound trace of the most extreme and enigmatic objects in the cosmos, black holes. The study of gravitational waves is not just a matter of observing distant collisions, but rather it's akin to tuning into the deepest vibrations of the universe. Every ripple holds information. By analyzing these waves, scientists can learn about the masses, spins, and even the histories of black holes that are otherwise shrouded in mystery. This means that even in the absence of direct observation, black holes, those incredibly dense, invisible regions in space, become more tangible. This indirect method of observation opens up new windows into understanding the behavior and characteristics of these cosmic giants. More importantly, it gives us an unprecedented opportunity to test the fundamental laws of physics, shedding light on the most extreme conditions where the fabric of space-time is stretched, twisted, and strained beyond recognition. As we continue to decode the information carried by these gravitational waves, we are taking steps toward uncovering the true nature of black holes and the profound processes that govern the universe. Each discovery in this area reveals not only more about these singularities themselves, but also about the broader cosmic structure in which they reside. And as we peer deeper into these phenomena, the boundaries of human knowledge expand, forcing us to confront the complexities that unite the infinitely small quantum realms and the vast stretches of intergalactic space. Meanwhile, nestled somewhere within the universe, a mysterious force known only as the Great Attractor wields an immense gravitational pull, its presence subtly yet powerfully affecting the motion of galaxies, including our own Milky Way. To comprehend the scale and nature of the Great Attractor, imagine a giant magnetic force that pulls everything within its reach, warping the motion of galaxies like a cosmic current that tugs and shifts their paths. The Great Attractor is located 100 million light years away in the direction of the Centaurus constellation and is known to be a vast and inexplicable region in space that has eluded our understanding for decades. Its exact nature remains a matter of scientific intrigue, because the region is obscured by the very stars, gas clouds, and interstellar material that make up our Milky Way galaxy. These cosmic barriers make direct observation difficult, but the effect of the Great Attractor on the motion of galaxies is undeniable. The journey to uncover this cosmic enigma began in the 1980s when astronomers first noticed a peculiar phenomenon. Galaxies within our local cosmic neighborhood appeared to be moving towards a distinct point in the sky. This observation was striking, as it suggested an unseen force was exerting influence on the motion of these galaxies. Astronomers had long believed that galaxies should move randomly, but the motion of these distant galaxies indicated that something powerful was guiding their paths. This anomaly led scientists to postulate the existence of an object or region with a massive gravitational influence, one that was not directly observable but could be inferred by the motion of galaxies. As technology advanced and telescopes became more powerful, astronomers began to piece together the puzzle. They realized that the Great Attractor is not a single object, but instead a vast, dense region of space, a gravitational center formed by an immense concentration of galaxies, dark matter, and possibly even other as-yet undiscovered cosmic structures. It is an area so massive that its gravitational pull causes galaxies in its vicinity, including the Milky Way, to move toward it at incredible speeds. Despite its size and influence, the exact details of what constitutes the Great Attractor remain elusive, and its true nature is still under investigation. What we do know, however, is that the Great Attractor holds a pivotal place in the structure of the universe, offering vital clues about the distribution of matter across vast cosmic distances. This region is more than just a curiosity. It plays a significant role in shaping the large-scale structure of the universe, guiding the motions of galaxies and clusters within our local cosmic neighborhood. Its gravitational effect is felt across hundreds of millions of light years, subtly tugging on the galaxies that lie in its reach, drawing them towards it. Imagine the universe as a vast ocean, with galaxies scattered like islands upon its surface. In this analogy, the Great Attractor is like a massive undercurrent, a force pulling galaxies toward it, guiding their movement through the cosmos. The influence of the Great Attractor is not isolated to just a few nearby galaxies. It affects a sprawling region of space, shaping the motions of entire clusters and guiding their movement in ways that we are only beginning to understand. The Great Attractor provides scientists with a unique opportunity to study the distribution of dark matter, an invisible and mysterious substance that makes up most of the mass in the universe. Though we cannot observe dark matter directly, its gravitational effects on galaxies, such as the way it warps their motion, give us crucial insights into its nature and behavior. By studying the Great Attractor, scientists can infer more about the unseen matter that shapes the fabric of the universe, contributing to our understanding of the universe's true composition. The study of the Great Attractor also offers a unique perspective on the history of the universe. By analyzing the motion of galaxies as they are drawn toward the center of this immense gravitational pull, we can gain insights into the dynamics of the early universe. What led to the formation of such a massive concentration of galaxies and dark matter? How have the motions of these galaxies evolved over billions of years? These are questions that, when answered, will help refine our understanding of the universe's origin and development. The Great Attractor is not merely an oddity, it is a key to understanding the ongoing evolution of the cosmos. It is a cosmic puzzle, one that offers a deeper understanding of the forces shaping the universe on a grand scale. And yet, despite our increasing understanding of its gravitational effects, the Great Attractor remains in many ways an enigma, a gravitational anomaly that continues to challenge our understanding of the universe's fundamental structure. Observing the Great Attractor is no simple task. The region's position within our galaxy means that its light is often blocked or scattered by the stars and gas in the Milky Way. To peer through this cosmic fog, astronomers use a range of techniques designed to overcome these obstacles. One of the most effective methods is to observe in wavelengths beyond visible light. Infrared and radio waves, for instance, can penetrate the dust and gas that obscure our view, revealing the hidden stars and galaxies lying between us and the Great Attractor. In this way, astronomers are able to peer through the Milky Way's dense layers and gain a clearer picture of the structures at the heart of the Great Attractor. Another vital technique used to study the Great Attractor involves the careful observation of the motion of distant galaxies. By tracking the redshift of light from these galaxies, an indicator of their speed and direction, astronomers can infer the gravitational forces at play in the region. Even without direct observation of the Great Attractor itself, this motion provides a crucial piece of the puzzle. It allows scientists to map the gravitational influence of this massive anomaly and better understand its role in the larger cosmic web. As we can continue to unravel the mysteries of the Great Attractor, we come ever closer to understanding the fundamental forces that govern the universe. The study of this enigmatic region offers profound insights into the nature of gravity, dark matter, and the large-scale structure of the cosmos, helping to paint a more complete picture of the forces at work within our universe. Each new discovery brings us one step closer to unlocking the secrets of the universe itself as we continue our journey of cosmic exploration. Gravitational lensing is a captivating phenomenon, one that has fascinated astronomers and cosmic theorists alike. It occurs when light from a distant object, such as a star or galaxy, passes near a massive gravitational body, like the Great Attractor, bending and distorting the light that reaches us. This bending creates an optical illusion, making far-off celestial bodies appear stretched, multiplied, or even duplicated. Such distortions are more than mere curiosities. They hold valuable clues about the distribution and mass of invisible matter, such as dark matter, that surrounds these massive objects. These cosmic distortions offer scientists a unique window into the unseen universe, revealing not only the forces shaping the visible cosmos, but also the vast amounts of dark matter that exert their pull on the fabric of space-time. For astronomers, gravitational lensing is a powerful tool that allows them to peer deeper into the cosmos than would otherwise be possible. As light bends around these massive objects, researchers can study the effects of these gravitational forces to learn more about the nature of dark matter. The lensing effect helps to uncover the mass and spatial distribution of dark matter around such massive gravitational sources, such as the Great Attractor. It also provides a way to see past the cosmic foreground, clearing a path through the complexities of intervening structures. By observing how galaxies and other cosmic objects behave in the presence of these gravitational distortions, astronomers can begin to piece together a more complete understanding of the Great Attractor, its environment, and the profound influence it has on the local universe. The Great Attractor is a fascinating and enigmatic region of space that exerts an extraordinary gravitational pull on the galaxy cluster to which our Milky Way belongs. This cluster, known as the Local Group, is a relatively small grouping of galaxies within the vast expanse of the universe. The gravitational forces at play within the Great Attractor have reshaped our understanding of the universe's mass distribution. It reveals that mass is not spread out evenly across space, but rather clumped together in certain regions, with some areas harboring enormous concentrations of galaxies, stars, and dark matter. These cosmic mountains create gravitational whirlpools, drawing in galaxies and galaxy clusters, much like massive oceanic currents pulling ships toward an unseen vortex. In this analogy, the Great Attractor acts as a cosmic whirlpool, drawing everything around it into its gravitational embrace. At the heart of the Great Attractor lies an enormous concentration of mass, likely including a substantial amount of dark matter, which does not emit any detectable radiation or energy. This dark matter is invisible, making it extraordinarily difficult to observe directly with conventional instruments. Despite this, scientists have deduced its existence by studying its gravitational effects on surrounding galaxies and galaxy clusters. Dark matter is thought to make up a significant portion of the universe's total mass, and its presence is felt strongly within the Great Attractor. By understanding how this invisible mass affects the motion of nearby galaxies, scientists can gain insights into the larger structure and dynamics of the universe. The discovery of the Great Attractor has provided a dramatic shift in our perspective of the cosmos. It suggests that rather than a smooth, homogeneous distribution of matter, the universe's mass is instead organized into vast, interconnected clusters. These clusters can have profound effects on the way galaxies move and interact. Our galaxy, the Milky Way, along with its neighbors, is caught in the gravitational pull of the Great Attractor, making it an integral part of this grand cosmic structure. By studying these movements and the influence of the Great Attractor, scientists can better understand the forces that govern the cosmos and the eventual fate of galaxies as they are shaped by these colossal gravitational influences. The Great Attractor's reach extends far beyond the local group, touching many of the largest and most important superstructures in the universe. One notable connection is with the Laniakea supercluster, the enormous cosmic structure that is home to our Milky Way galaxy. Laniakea is not simply a random collection of galaxies. It is a vast structure shaped by the gravitational forces of many nearby and distant bodies, including the Great Attractor. Galaxies within Laniakea are not only affected by the gravity of nearby clusters, but they also feel the pull of this distant, unseen force. This intricate web of gravitational influences helps to shape the entire supercluster and, by extension, the motion of galaxies within it. Nearby structures, such as the Shapley supercluster, also play an important role in shaping the motion of galaxies in the region. The Shapley supercluster is one of the most massive collections of galaxies within the observable universe, and its own gravitational influence interacts with that of the Great Attractor. Together, these superclusters form a complex cosmic network, each one tugging on the others in a delicate balance. The interactions between these structures provide a deeper understanding of the universe's large-scale structure, highlighting how interconnected everything is, even across vast cosmic distances. This dynamic web of gravitational forces shapes the movement and arrangement of galaxies, offering a glimpse into the true complexity of the cosmos. Yet, understanding the true nature of the Great Attractor is no small task. The very factors that make it so intriguing also make it exceptionally difficult to study. The region where the Great Attractor resides is densely packed with galaxies, which makes it challenging for astronomers to observe the mass at its core. The most significant challenge, however, is that the Great Attractor lies behind our own Milky Way galaxy, obscuring much of the view. This foreground effect, created by the stars and gas of the Milky Way, makes it harder for astronomers to detect distant galaxies and other cosmic signals that are crucial to understanding the Great Attractor's properties. Further complicating matters is the motion of galaxies within this region. The Great Attractor's enormous gravitational pull causes galaxies to move toward it, a motion known as peculiar velocity. This motion distorts the data that astronomers collect, as they must account for the natural movement of galaxies as they are drawn toward the Great Attractor. Differentiating this movement from the overall expansion of the universe adds another layer of complexity to the task. This peculiar velocity effect also means that astronomers must carefully untangle the influences of local gravitational forces from those acting on a universal scale. It's a challenging and intricate process that requires the most advanced observational techniques. The distance between Earth and the Great Attractor adds yet another challenge to our understanding. Situated millions of light years away, the Great Attractor exists at the edge of what is observable with current technology. Light from distant galaxies that passes through this region is faint and hard to detect, requiring powerful telescopes and sophisticated techniques to gather usable data. Even with the most advanced instruments available today, astronomers can only observe a small fraction of the larger picture at any given time. The Great Attractor is so vast and the distances involved so great that piecing together a coherent image of this cosmic anomaly remains an ongoing effort. The presence of dark matter further complicates the search. Since dark matter doesn't emit light, it cannot be directly observed with traditional telescopes. However, its gravitational influence is undeniable. Galaxies and galaxy clusters are drawn toward the Great Attractor, and this movement provides scientists with valuable clues about the distribution of dark matter in the region. By carefully studying the motion of galaxies, astronomers can infer the amount and location of dark matter, helping to map the structure of the universe more accurately. Despite these challenges, astronomers are committed to unraveling the mysteries of the Great Attractor, using innovative tools and techniques to push the boundaries of our understanding. The Great Attractor also plays a significant role in how we perceive the expansion of the universe. The universe is generally understood to be expanding, with galaxies moving away from one another over time. However, the Great Attractor's immense gravitational pull creates a localized distortion in this expansion. Instead of all galaxies receding from one another, those in the vicinity of the Great Attractor are being drawn toward it. This creates a distortion in the expected expansion rate of the universe, complicating our interpretation of cosmic dynamics. Understanding how the Great Attractor influences the movement of galaxies is crucial for refining our models of cosmic expansion and gaining a deeper insight into the forces that shape the universe. The complexity of this cosmic phenomenon leads to exciting scientific questions. As galaxies near the Great Attractor, their movement deviates from the general trend of the universe's expansion. This alteration in their motion provides a unique opportunity to study the forces acting on these galaxies and how they interact with one another. The Great Attractor, in its subtle and far-reaching way, reshapes our understanding of the universe, expanding our perspective not just on the nature of galaxies and their movements, but also on the very nature of cosmic expansion itself. Looking ahead, the study of the Great Attractor presents an ongoing challenge that promises to yield even more profound insights into the structure of the universe. Advanced telescopes equipped with cutting-edge technology are essential for observing the faint light emitted by distant galaxies. These observations will allow scientists to better understand the distribution and movement of galaxies, providing more clues about how the Great Attractor's gravitational pull shapes the larger cosmic framework. By studying more galaxies in detail and observing how they interact with this massive gravitational force, astronomers will continue to piece together the puzzle of this colossal cosmic enigma. Space-based missions have become a cornerstone of modern astronomical exploration, marking a significant evolution in our understanding of the cosmos. By positioning observatories beyond Earth's atmosphere, astronomers can access an uninterrupted, clear view of the universe. This unique vantage point eliminates the distortions caused by the Earth's atmosphere, enabling more accurate and detailed observations of the heavens. With these advancements in observational technology, scientists are now able to collect data with unprecedented precision, helping to unravel some of the most profound mysteries of the universe. One of the most captivating objects of study is a region of space known as the Great Attractor, a cosmic anomaly that draws galaxies towards it with an immense gravitational pull. This phenomenon has become a focal point of research, as understanding its nature could offer insights into the fundamental forces shaping the universe itself. At the heart of this inquiry lies the need for multi-wavelength observations. Traditional optical telescopes, which capture light in the visible spectrum, provide a limited view of the cosmos. However, by employing a range of wavelengths, including radio waves, infrared, and X-rays, Astronomers can observe the universe through different lenses, each revealing unique features of celestial objects. X-ray observations, for example, are particularly valuable for studying regions with intense gravitational forces, such as the clusters of galaxies surrounding the Great Attractor. These observations help uncover the presence of hot gas in these clusters, offering a clue to the powerful gravitational forces that shape them. By combining data from multiple wavelengths, scientists can build a more comprehensive understanding of the objects they study, allowing for deeper insights into the dynamics of galaxies and the forces influencing their motion. In addition to direct observations, the use of simulations and computer models has become indispensable in the study of cosmic phenomena. By inputting real-time data into sophisticated computational models, researchers are able to simulate the behavior of galaxies, clusters, and even the entire universe under various conditions. These simulations help to predict how cosmic structures evolve over time, offering valuable insights into the forces that govern them. For instance, researchers can model the influence of the Great Attractor on nearby galaxies, not just in the present, but also in the distant past and future. This predictive power is essential for understanding how galaxies will continue to evolve under the influence of this enigmatic region and how it fits into the broader structure of the universe. The ultimate goal of these observations and simulations is to piece together the puzzle of the Great Attractor. This cosmic giant, located approximately 200 million light-years away in the direction of the Centaurus constellation, exerts an inexplicable gravitational pull that seems to affect the motion of galaxies across vast regions of space. The challenge for scientists has been to understand the forces at play in this mysterious region and to determine what lies at its core. One of the most perplexing aspects of the Great Attractor is its apparent connection to dark matter, a mysterious and invisible substance that constitutes a large portion of the universe's mass. Dark matter does not emit, absorb, or reflect light, making it undetectable by traditional means of observation such as optical telescopes. Nevertheless, scientists have inferred its existence due to its gravitational effects on visible matter. Although dark matter remains elusive and largely unstudied, it is thought to make up approximately 27% of the universe's mass, with ordinary matter accounting for only about 5%. The rest is made up of dark energy, a still mysterious force responsible for the universe's accelerating expansion. In the case of the Great Attractor, astronomers have hypothesized that the mass responsible for its gravitational pull is largely composed of dark matter. This would explain the powerful force drawing nearby galaxies toward the region, even though no visible matter is present to account for such an effect. By carefully tracking the movement of galaxies in the vicinity of the Great Attractor, scientists are able to map out the hidden mass that lies in this region. This data, combined with simulations, helps to refine our understanding of how dark matter is distributed throughout the universe. The study of these galactic motions not only sheds light on the nature of the Great Attractor, but also provides valuable clues about the broader cosmic structures that influence galaxy formation and evolution. As galaxies drift toward the Great Attractor, their paths are altered by its gravitational influence, revealing information about the surrounding dark matter and its interaction with visible matter. Beyond the study of dark matter, the Great Attractor also serves as a key point of investigation for understanding the large-scale structure of the universe. The way in which galaxies cluster around this mysterious region offers insights into the fundamental architecture of the cosmos. The distribution of galaxies across the universe is far from uniform. Instead, galaxies tend to cluster together in massive superclusters, which are connected by vast cosmic filaments. The Great Attractor is located at the center of one such supercluster, known as the Laniakea supercluster, which encompasses a vast region of space stretching over hundreds of millions of light years. By studying these clusters and their interactions, astronomers can gain a deeper understanding of the gravitational forces that shape the universe's structure and how galaxies form and evolve within it. The quest to understand the Great Attractor and its relationship to dark matter is just one part of a larger effort to unravel the mysteries of the universe. This investigation not only illuminates the nature of the forces at play in this region, but also provides critical insights into the broader cosmic phenomena that govern the behavior of galaxies. As researchers continue to refine their observations and simulations, they are piecing together a more complete picture of how galaxies interact, evolve, and ultimately form the cosmic structures we observe today. The discovery of the Great Attractor has profound implications for our understanding of the universe. However, it is also tied to a broader revolution in cosmology, the study of the origins, structure, and evolution of the cosmos. One of the most significant shifts in our understanding of the universe occurred with the realization that the cosmos is expanding. Prior to the 20th century, many astronomers believed that the universe was static, unchanging over time. This view persisted for centuries, as the vast distances and seemingly unchanging nature of the night sky suggested a fixed, eternal universe. However, this perception was forever altered by the groundbreaking work of astronomer Edwin Hubble. In the 1920s, Hubble made an astonishing observation. Distant galaxies were moving away from us, and the farther they were, the faster they appeared to recede. This observation was pivotal, as it provided the first direct evidence that the universe was expanding. This phenomenon, known as Hubble's law, was based on the observation that galaxies emit light that is redshifted, meaning the light is stretched to longer wavelengths as the galaxies move away. The greater the distance to a galaxy, the greater its redshift, and thus the faster it is receding from us. This discovery fundamentally changed our understanding of the cosmos, suggesting that the universe had not always existed in its present state, but had instead undergone a dynamic evolution over time. The idea of universal expansion led to the development of the Big Bang theory, which posits that the universe began as an incredibly dense and hot point approximately 13.8 billion years ago. This singularity, from which all matter and energy in the universe emerged, marked the beginning of space, time, and everything we know. The expansion of the universe, which began in the wake of the Big Bang, continues to this day, driving galaxies apart and leading to the vast and ever-growing cosmos we observe today. The discovery of the expanding universe also opened up a wealth of new questions about the ultimate fate of the cosmos. Would the universe continue to expand forever, driven by the mysterious force of dark energy? Or would gravity eventually overcome this expansion, causing the universe to contract and potentially collapse in a big crunch? The answers to these questions remain uncertain, but they represent some of the most fundamental mysteries of modern cosmology. As scientists continue to study the Great Attractor and other cosmic phenomena, they are not only piecing together the history of our universe, but also investigating its future, working to understand the forces that will shape its destiny in the billions of years to come. The discovery of the universe's expansion fundamentally transformed our understanding of the cosmos. It unveiled not just a new way of thinking about the universe, but also introduced a multitude of complex concepts like dark energy that further deepened the mystery. The idea that the universe is constantly changing, growing ever larger and more complex over time, has given rise to theories and models that aim to explain this dynamic phenomenon. These explorations into the very nature of time, space, and the forces that shape the cosmos have become central questions in the field of cosmology. As scientists continued to delve deeper into the intricate web of celestial mechanics, the universe's expansion became more than a fact. It became a lens through which we view our origins and our potential future. The discovery of dark energy, a force thought to be driving this accelerated expansion, further heightened our fascination with the cosmos. What began as a basic observation evolved into a sweeping investigation into the birth, life, and death of galaxies, the formation of stars, and the very fabric of reality itself. In the early 20th century, astronomers believed in a static universe. The prevailing view was that the universe, in its vastness, was unchanging, frozen in time. Yet this perception was shattered by the revolutionary work of Edwin Hubble, whose discoveries forever changed the course of astronomy. His observations, some of the most profound in the history of science, not only redefined the structure of the universe, but also set the stage for the development of modern cosmology. At the time, The idea that the universe was static and unchanging seemed almost self-evident to most scientists. It was a comforting notion, one that fit neatly into a worldview that did not yet possess the technology or understanding to challenge it. However, Hubble's breakthroughs shattered this static view. He began his observations by studying distant galaxies using one of the most powerful telescopes of the time. His findings were striking. The light from these distant galaxies was not only faint, but also shifted toward the red end of the spectrum, a phenomenon now known as redshift. This shift, indicative of an object moving away from the observer, was evidence that the galaxies were not stationary. The farther a galaxy was from us, the faster it appeared to be receding. This discovery opened the floodgates to a new way of thinking about the cosmos. The idea that the universe was expanding, growing larger over time, seemed almost inconceivable at first, but the evidence was undeniable. Hubble's work led to the formulation of Hubble's law, which states that the velocity at which a galaxy moves away from us is directly proportional to its distance from us. In essence, the farther a galaxy is, the faster it is moving away. This observation was revolutionary, not only because it indicated that the universe was in motion, but also because it implied that at some point in the distant past, the universe was far smaller, denser, and hotter. It provided the first concrete evidence for the Big Bang theory, the idea that the universe had a beginning, marked by a singular, cataclysmic event, and had been expanding ever since. The implications of Hubble's discovery were profound. The notion of a static, unchanging universe was replaced with the realization that the cosmos was an ever-evolving, dynamic system. This shift in thinking prompted a new era of scientific inquiry, one that sought to understand the origin, structure, and fate of the universe. How did galaxies form? How do stars live and die? What are the forces that govern the fabric of space-time? These questions, once considered speculative, became the focus of intense scientific investigation. At the heart of this exploration lies the concept of cosmic expansion. This idea that the universe is gradually growing larger over time may sound simple, but measuring this expansion is a monumental task. One of the most important tools for studying this phenomenon is the observation of light emitted by distant galaxies. When light travels through space, its wavelength can shift depending on the motion of the object emitting it. This shift, known as the Doppler effect, is a well-established principle in physics. For example, as a car passes by, the sound of its horn changes pitch. It sounds higher as it approaches and lower as it moves away. Similarly, as galaxies move away from us, the light they emit shifts toward longer wavelengths, which we perceive as redder. Astronomers have harnessed this redshift to measure the velocity at which galaxies are receding from us. By observing the light from these galaxies, they can calculate how fast the galaxies are moving and use this data to estimate their distance. The greater the redshift, the faster the galaxy is receding, providing crucial information about the universe's expansion rate. This method of measuring cosmic expansion has revolutionized our understanding of the cosmos. The tools astronomers use to measure redshift and cosmic expansion are both advanced and diverse. Telescopes, both ground-based and space-based, are equipped with spectrographs that allow scientists to split light into its constituent wavelengths, enabling them to study the light emitted by distant objects. Space telescopes, like the Hubble Space Telescope, offer a distinct advantage by avoiding the distortion caused by Earth's atmosphere, providing clearer and more accurate data. Meanwhile, ground-based observatories, such as the Very Large Telescope and radio telescopes like the Very Large Array, help to capture a broader range of electromagnetic signals, from visible light to radio waves, offering a more comprehensive view of cosmic phenomena. Moreover, studying the cosmic microwave background radiation, the faint afterglow of the Big Bang, has provided astronomers with a snapshot of the early universe. By analyzing the patterns in this radiation and how it relates to the ongoing expansion of the universe, scientists have been able to glean important insights into the universe's rate of expansion and its history. This ancient radiation, a relic of the universe's infancy, serves as a key piece of the cosmic puzzle, offering valuable clues about its evolution over billions of years. The concept of redshift and the tools used to measure it have not only provided evidence for the universe's expansion, but have also played a pivotal role in the development of the Big Bang theory. By studying how galaxies move away from us, astronomers can estimate the distances to these galaxies and determine how quickly the universe is expanding. This information has been instrumental in shaping our current understanding of the cosmos. It suggests that the universe is not static. It is a dynamic, evolving entity, constantly changing and expanding, much like a living organism. The Hubble constant is one of the most important parameters that scientists use to measure the rate of cosmic expansion. Named after Edwin Hubble, this constant represents the speed at which galaxies are moving away from us per unit of distance. To visualize this, imagine the universe as a balloon being inflated. As the balloon expands, the surface stretches, and points on the surface move away from each other. The Hubble constant is the rate at which these points are moving apart. By measuring the rate of recession of distant galaxies, astronomers can determine the Hubble constant and, in turn, calculate the age of the universe and the distance between objects in space. Understanding the Hubble constant is essential for constructing a more complete picture of the universe's history. For example, it allows scientists to estimate how long it has been since the Big Bang, the moment that marks the birth of the universe. By examining the rate of cosmic expansion, astronomers can also make predictions about the future of the universe, including its potential fate. Will it continue expanding indefinitely? Will it eventually slow down and contract? These are questions that are still being debated, but they are questions that, thanks to Hubble's discoveries, we can now ask with confidence. The expansion of the universe is a story that continues to unfold. Every new observation, every new measurement, brings us closer to understanding the true nature of the cosmos. The universe is not the static, unchanging entity that once seemed so self-evident. Instead, it is a dynamic, ever-evolving space, a place of constant growth, change, and transformation. And as we continue to explore its vast reaches, we are not just learning about the stars and galaxies that populate it, we are learning about ourselves and our place in this ever-expanding universe. The ongoing exploration of the universe's expansion, alongside the refinement of measurements such as the Hubble constant, has profound implications for science, especially in understanding one of the most enigmatic forces known to humankind: dark energy. Dark energy, an invisible, mysterious force, is believed to be the driving factor behind the accelerated expansion of the universe. As researchers continue to improve the accuracy of the Hubble constant, their work has the potential to unlock mysteries that shape the very fabric of space and time. The pursuit of these answers can reveal insights into how the universe is evolving and what forces govern its behavior, as well as challenge fundamental assumptions that could completely redefine the laws of physics. The expansion of the universe is a central concept in cosmology, and it serves as the backbone for understanding the cosmos. This expansion is not merely a theoretical idea, but a tangible process observable through various techniques. Essentially, it describes how galaxies are moving away from each other over time. However, the methods used to measure this expansion often yield results that don't always align. This discrepancy, which has puzzled scientists for years, hints at gaps in our understanding of the universe on both cosmic and quantum scales. Despite the various measurement tools available, the interpretation of these results doesn't always lead to the same conclusions. When such inconsistencies arise, they present significant challenges to our current models of the universe. One of the most prominent ways to measure the expansion of the universe is through the observation of supernovae. A supernova is the explosive death of a star, and these events can be incredibly bright, emitting immense amounts of light. Astronomers use the brightness of these supernovae to gauge their distances, assuming that the brighter the supernova, the closer the galaxy is. This provides valuable data about the rate of expansion. Another method of measurement relies on studying the cosmic microwave background radiation, CMB, a faint glow that permeates the entire universe. The CMB is the remnant radiation from the Big Bang and contains vital clues about the early universe. It serves as a snapshot of the cosmos when it was just 380,000 years old, offering essential data for estimating the current expansion rate. Yet, when comparing these two methods, scientists encounter differences in their results. In some cases, one approach suggests the universe is expanding faster than the other. This is where the real intrigue begins, as these conflicting measurements imply that something fundamental about our universe remains misunderstood. Such discrepancies might be revealing gaps in our understanding of cosmic physics. They prompt scientists to reconsider the assumptions we make about space, time, dark energy, and even the basic structure of the universe itself. These inconsistencies might not be minor anomalies, but rather signposts pointing to something more profound and potentially transformative in our understanding of physics. The consequences of these measurement discrepancies could ripple across all aspects of cosmology. If measurements derived from different methods don't align, it forces scientists to reassess the models and assumptions that underpin our comprehension of the universe's structure and its future evolution. It's as though they are trying to solve a cosmic puzzle, yet some pieces seem to resist fitting together. Nevertheless, these challenging contradictions may also open up the potential for new physics, ideas and theories that may lead to groundbreaking discoveries about the universe, possibly revealing phenomena that were previously undetectable or unimaginable. One of the most significant implications of these expanding questions is our understanding of dark energy itself. Dark energy, which accounts for a large portion of the universe's total energy content, is believed to be responsible for the acceleration of cosmic expansion. It's a strange force, invisible and elusive, and its exact nature remains one of the most pressing mysteries in contemporary science. As measurements of the Hubble constant continue to be refined, scientists are gaining new insights into how dark energy might influence the universe's fate. This ongoing search for answers underscores the dynamic and evolving nature of science. What we understand today is often the starting point for new questions, leading to deeper investigations and a broader understanding of the universe. The expansion of the universe itself has a direct impact on the light that reaches us from distant galaxies, a crucial piece of the cosmic puzzle. To grasp this concept, imagine the universe as a balloon being inflated. As the balloon expands, dots on its surface, representing galaxies, move away from each other. This analogy offers a simple way to visualize the large-scale expansion of space. The farther a galaxy is from us, the faster it appears to be receding. This motion affects the light emitted by these galaxies. When a galaxy moves away, the wavelengths of its emitted light get stretched. This is a phenomenon known as redshift, where light shifts from the blue end of the spectrum to the red end as its wavelengths become longer. The redshift observed in the light from distant galaxies provides astronomers with valuable information about both the speed at which a galaxy is moving and the age of the universe itself. As we look deeper into space, we're essentially looking further back in time. This means that the light we see from distant galaxies is not only stretched due to the expansion of the universe, but also represents a snapshot of the galaxy's past. In this way, the light reveals crucial information about the universe's expansion and the forces that have driven its growth over billions of years. However, this stretching of light doesn't just affect its wavelength. It also influences the brightness and the overall characteristics of the light we observe. Some galaxies, once vibrant and blue in their youth, appear red and dim by the time their light reaches our instruments. This can mask their true nature, making it more difficult to fully understand their composition and behavior. Nevertheless, understanding how light from distant galaxies is affected by the expansion of the universe is key to deciphering the history of the cosmos, its evolution, and the complex processes that govern its growth. The future of the universe is intrinsically tied to its expansion rate, and understanding how this expansion evolves over time is essential for predicting the universe's eventual fate. Currently, scientists have observed that the expansion of the universe is accelerating, a process attributed to dark energy. If the current rate of acceleration continues, one potential future scenario is known as the Big Freeze. In this scenario, galaxies will drift further and further apart over immense stretches of time. As stars burn out and the universe grows colder, it could eventually reach a point where it is almost entirely devoid of light, populated only by the faint remnants of long-dead stars and galaxies. Alternatively, if dark energy continues to exert a greater and greater repulsive force, the universe could face a dramatic and violent end in a scenario known as the Big Rip. Here, the expansion of the universe could become so rapid that it tears apart everything in its path: galaxies, stars, planets, and even atoms. The result would be a chaotic disintegration of all matter, leading to a violent and destructive conclusion to the universe's journey. The third scenario is known as the Big Crunch, which envisions a reversal of the expansion. If the universe contains enough mass, the gravitational forces could overcome the expansion and begin to pull everything back together. Eventually, all matter would collapse into a singular dense point, possibly resembling the conditions that existed before the Big Bang, giving rise to a cyclical universe of infinite beginnings and endings. Finally, there is the possibility of a stable universe, where the expansion slows down but never fully halts. In this case, the universe would continue to grow and evolve, but at a much slower pace. Over time, the process of cosmic evolution would continue, albeit at a subdued rate, leading to a universe that grows old and quiet without an explosive or catastrophic end. Whether it's a universe destined for cold emptiness, explosive disintegration, a dramatic collapse, or peaceful stability, the future remains uncertain. At the heart of our understanding of these cosmic possibilities lies the lambda cold dark matter, LCDM model. This widely accepted framework helps scientists interpret the structure and evolution of the universe. Central to the LCDM model is the understanding that the universe is not static but expanding, with galaxies moving away from each other over time. The expansion is driven by dark energy, represented by the Greek letter lambda, Lel, which acts as the primary force accelerating the growth of the cosmos. Alongside dark energy, cold dark matter plays a critical role in shaping the gravitational landscape of galaxies and larger cosmic structures. Though dark matter is invisible and undetectable by traditional means, scientists infer its presence through its gravitational influence on visible matter. Cold dark matter helps bind galaxies and clusters together, forming the scaffolding of the universe's large-scale structure. The LCDM model also posits that the universe began with the Big Bang, which set the initial conditions for both its structure and expansion. From that moment onward, the universe has been expanding, and the interplay between the repulsive force of dark energy and the gravitational pull of dark matter determines the rate and nature of this expansion. This framework is tested and refined by ongoing observations of distant galaxies, the cosmic microwave background radiation, and other astronomical phenomena. The evidence gathered supports the notion that the universe is expanding at an accelerating rate, driven by the complex and dynamic relationship between dark energy and matter. This understanding provides us with a clearer picture of the universe's past, present, and future. To continue expanding our knowledge, several ambitious space missions are underway. One such mission is the James Webb Space Telescope, which has been designed to observe the light emitted by distant galaxies. By studying this light, scientists hope to gain deeper insights into the rate of the universe's expansion and how it has evolved over cosmic time. Similarly, the European Space Agency's Euclid satellite, which will soon launch, is tasked with mapping the shape and distribution of galaxies across the universe. This mapping will provide essential data to understand how galaxies are spread out, shedding light on the forces driving the universe's expansion, including the mysterious and elusive dark energy. As these and other missions progress, they will continue to provide essential data to refine our understanding of the universe's expansion, its ultimate fate, and the forces that shape it. Each discovery not only deepens our knowledge of the cosmos, but also challenges us to reconsider long-held assumptions, paving the way for new discoveries that will continue to shape the future of cosmology. The universe, it seems, is far from finished revealing its secrets. In the heart of the world's most advanced astronomical research, observatories like the Vera C. Rubin Observatory in Chile play an indispensable role in exploring some of the universe's most fleeting and dynamic phenomena. This ground-based marvel, nestled in the Atacama Desert, is dedicated to tracking transient cosmic events. It is designed to observe and catalog a myriad of astronomical phenomena, from the death of stars in explosive supernovae to the sudden appearances of new objects in the sky, like asteroids or comets. The observatory's extensive survey will provide an unprecedented and comprehensive map of the cosmos. By constantly observing the night sky and collecting data on a vast array of transient events, it enables scientists to track these objects in real time, making it possible to refine our understanding of the universe's expansion rate. This extraordinary effort also allows for the measurement of the distances between Earth and these cosmic occurrences. By tracking how fast objects like galaxies or distant supernovae are receding from us, astronomers can gather invaluable data on the nature of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. The mission of the Vera C. Rubin Observatory, combined with other space-based projects, paints a multifaceted picture of the universe. Together, they offer a synthesis of light from the distant past, drawn from ancient cosmic events and the current state of our universe. The combination of both perspectives creates a richer, more complete narrative about the cosmos, shedding light not only on our position within it, but also on the complex, often mysterious forces that have shaped it over billions of years. Every new discovery in astronomy is a doorway to more questions. As we delve deeper into understanding the universe's origins, structure, and eventual fate, we also come to terms with the fact that each answer seems to unveil more mysteries. This process is not just about accumulating knowledge, but also about cultivating an ever-expanding awareness of our place in a vast, evolving cosmos. When we think about time, our everyday understanding is simple and grounded. Time on Earth is usually measured with clocks broken into hours and minutes, marking the rhythm of our daily lives. This steady flow, though seemingly constant, only scratches the surface of how time behaves in the broader universe. In the cosmos, time is not merely a fixed and linear entity. Instead, it is a malleable construct influenced by factors such as speed and gravity. In the context of space, time does not behave in the familiar, steady way we experience on Earth. Instead, it stretches, bends, and warps, particularly in extreme environments. Consider the effect of speed on time. Imagine a person traveling in a spaceship near the speed of light. To them, time would seem to pass normally. However, observers back on Earth would see their clock ticking at a slower rate. This is because as objects approach the speed of light, time itself begins to stretch, an effect known as time dilation. From the perspective of the traveler, their journey may seem to last only a few days or weeks, but when they return to Earth, they might find that decades or even centuries have passed. The faster one moves, the more pronounced this effect becomes, opening the possibility of a time travel paradox, where someone could travel into the future by simply moving fast enough. In addition to speed, gravity plays a vital role in shaping how time is experienced across the universe. Time behaves differently in areas with strong gravitational fields. Take, for example, the extreme conditions near a black hole where gravity is so intense that it warps both space and time. Imagine placing a heavy weight on a spring. The greater the weight, the more the spring compresses and stretches, slowing its oscillations. Similarly, in regions with strong gravitational pull, time slows down relative to areas where gravity is weaker. If you were near a black hole, for instance, a clock placed close to its event horizon would tick more slowly than one placed farther away. This concept of time dilation due to gravity is known as gravitational time dilation. It means that a clock closer to a massive object would tick slower compared to a clock situated farther from the object. Thus, while we experience time in a familiar, predictable manner in our daily lives on Earth, in the grand cosmic stage, time is subject to the warping influences of both speed and gravity. It forms a tapestry of different perceptions across the universe, one where each observer might experience time at a different pace. From the ticking of a distant star's clock to the seconds that pass in our own world, these varying perceptions contribute to our growing understanding of time, not as a simple linear progression, but as a dynamic, ever-changing element of reality itself. One of the most profound questions that have intrigued both scientists and philosophers is the origin of time itself. The beginning of time, as we know it, is intrinsically linked to the inception of the universe. The Big Bang Theory, the leading scientific explanation for the origin of the universe, posits that everything, space, time, matter, and energy, originated from an infinitesimally small, hot, and dense point. This singularity was the origin of not only the universe itself, but also time as we understand it. Imagine for a moment a completely deflated balloon, tightly packed with air. As air begins to fill the balloon, it expands, growing larger and larger. The universe, according to the Big Bang Theory, behaved in a similar fashion. It began as a singular point and expanded rapidly, releasing energy that eventually gave rise to matter and the structures we see today: galaxies, stars, and planetary systems. The moments following the Big Bang were marked by extremely high temperatures and density, so much so that the traditional laws of physics could not accurately describe what was happening. This period is known as the Planck era, and it represents a state where space-time was so compressed and chaotic that our current understanding of physics breaks down. As the universe cooled, particles began to form, combining to create atoms. These atoms, in turn, clumped together to form stars and galaxies. Over billions of years, these structures continued to evolve, ultimately leading to the complex and ever-changing universe we observe today. However, this is just one possible narrative for the beginning of time. Other theories, like those involving cyclic universes, suggest that rather than having a singular beginning, the universe undergoes cycles of expansion and contraction, each cycle marking a new birth and death for the cosmos. This idea of a cyclic universe, one that expands and contracts repeatedly, gives rise to the notion of an endless sequence of beginnings and endings, much like the rhythm of a heartbeat. Every cycle could be the beginning of a new universe, each one starting fresh, building upon the foundations laid by its predecessors. The idea suggests that time itself is not a linear progression, but something more dynamic, with each cycle of the universe representing a new chapter in an ongoing story. Another fascinating theory suggests that time itself might have emerged alongside the universe. According to this hypothesis, there was no before the Big Bang, as time did not exist in the way we understand it today. Instead, time could have started simultaneously with the expansion of space. This would mean that asking what happened before the Big Bang is a nonsensical question, as the very dimension of time did not exist prior to the event. These theories continue to challenge our perceptions of the universe's origins, offering a glimpse into the mysterious and often elusive nature of time itself. Relativity, one of the most transformative theories in modern physics, forever altered our understanding of time and space. Prior to Albert Einstein's groundbreaking work, time and space were considered immutable, fixed entities against which all events in the universe took place. However, relativity revealed that both time and space are malleable, shaped by the forces of speed and gravity. To grasp the effects of relativity, imagine time flowing like a river. Each person, depending on their velocity and position in a gravitational field, experiences the flow of time in a different way. For someone traveling near the speed of light, for example, time would seem to slow down relative to someone at rest on Earth. This is the phenomenon known as time dilation, which shows that the faster you move, the slower time passes for you when compared to someone who is not in motion. This has profound implications not only for space travel, but for our very understanding of time itself. In addition to time, space is also shaped by the presence of mass and gravity. When a massive object, like a planet or star, is present, it causes space to warp, creating what is known as a gravitational well. The effect is similar to placing a heavy ball on a rubber sheet. The sheet curves, and any object nearby will follow that curve. This is why planets orbit stars. They are moving along the curved paths created by the warping of space-time. The deeper one travels into a gravitational well, the more pronounced the curvature of space-time becomes. Relativity reveals the universe not as a static backdrop for events, but as a dynamic, interconnected system of space and time. These concepts show us that time is not just a measure of progress, but a fluid, flexible aspect of reality, shaped by the forces of motion and gravity. Events, for example, may appear to take different lengths of time depending on the observer's relative motion and position in a gravitational field. Likewise, the distance between 2 points may vary based on the curvature of space-time. These ideas transform our view of the universe, making it clear that our existence is part of a fluid and dynamic system. Space and time are not fixed coordinates, but malleable aspects of the cosmos, shaping and being shaped by every object, every event, and every motion that occurs within the vastness of the universe. The dance between space and time, as described by relativity, reveals a universe far more intricate and surprising than we could have imagined. Time dilation is not just a theoretical concept, it has practical implications as well. When objects are near massive bodies like planets or stars, the flow of time is affected. Imagine two clocks, one placed near a massive planet and the other situated far from any significant gravitational influences. The clock closer to the planet would tick more slowly compared to the clock far out in space. This means that time in these extreme environments flows at different rates for different observers. For astronauts traveling close to a black hole or other massive objects, the implications are even more profound. As they experience time differently, they would age more slowly compared to people who remain far from such massive bodies. If they were to return to Earth after spending time near a black hole, they would find that years, perhaps even centuries, had passed on Earth, while only a few days or weeks had passed for them. This principle of time dilation is not only a fascinating aspect of physics, but a crucial consideration in everyday technology. For example, satellites in orbit around Earth must account for the effects of time dilation to maintain accurate synchronization with Earth-based systems. The Global Positioning System, GPS, relies on highly precise timing to determine locations accurately. Without accounting for the subtle but significant effects of time dilation, GPS systems would yield increasingly inaccurate results over time. Thus, time dilation is not just an abstract concept, but a key factor in the accuracy of technology that millions of people rely on every day. It reminds us that the very fabric of space and time is not merely an academic topic, but an integral part of our daily lives. When we turn our attention to black holes and wormholes, we are confronted with some of the most tantalizing possibilities in theoretical physics, especially when it comes to time travel. Black holes, for instance, are regions of space where gravity is so intense that not even light can escape. As we approach the event horizon, the point beyond which nothing can escape, the fabric of space-time becomes increasingly distorted. For someone falling into a black hole, time would appear to slow down dramatically. From the perspective of an outside observer, their descent would seem to freeze at the event horizon. If somehow a traveler could survive the journey through a black hole and emerge on the other side, they might experience time in a dramatically different way than those left outside the black hole. This has led scientists to hypothesize that a journey through a black hole might allow a traveler to leap forward in time, emerging in a distant future. Wormholes, on the other hand, are theoretical shortcuts through space and time. Imagine a tunnel connecting two distant regions of the universe. If such a structure exists, it might allow someone to traverse vast distances instantly, effectively altering the flow of time for the traveler. But the concept of wormholes introduces even more possibilities. If a wormhole connects not just two locations, but two different times, it could provide a means for someone to travel backward in time. The idea of time travel, whether through black holes or wormholes, may seem like science fiction, but it is grounded in the principles of relativity and quantum mechanics. While these theories remain speculative, they inspire us to think about the deeper, more mysterious aspects of time, space, and our place in the cosmos. They push the boundaries of what we know and open the door to a future where the fabric of space-time may one day be navigable in ways we are only beginning to imagine. The existence of wormholes and the possibility of navigating them safely remain one of the most captivating yet uncertain aspects of modern physics. These hypothetical shortcuts through the fabric of space and time, often portrayed in science fiction as a means of fast travel across vast distances, continue to ignite the imagination of both scientists and the general public alike. However, despite their intriguing potential, wormholes remain firmly within the realm of speculation, as their existence has yet to be proven. The concepts of wormholes and time travel challenge our conventional understanding of time, suggesting that under specific and extreme conditions, time may not be as constant as we once believed. These ideas force us to reconsider the fundamental nature of time itself, hinting that instead of being a rigid and unyielding flow, it might be more malleable than we can currently comprehend. Despite the theoretical allure of these concepts, actual time travel remains one of the greatest mysteries of science. It is surrounded by numerous obstacles, many of which are tied to the extremely demanding conditions required to even begin exploring the nature of space-time, as well as our current technological limitations. The scientific community continues to grapple with these challenges through groundbreaking experiments aimed at exploring the very fabric of the universe. One of the most remarkable experiments conducted in recent years involves the observation of gravitational waves. These ripples in the fabric of space-time are created by the violent movements of massive objects, such as when black holes or neutron stars collide. By detecting and studying these waves, scientists have been able to confirm key predictions made by Albert Einstein's theory of general relativity, which describes how gravity shapes the structure of space and time. The detection of gravitational waves is not only a confirmation of Einstein's theories, but also provides new insight into the most extreme and elusive phenomena in the universe. Another experiment that has contributed significantly to our understanding of space-time involves atomic clocks. These highly precise timekeepers, which are capable of measuring time with an unprecedented level of accuracy, have been placed in various environments, such as on the ground and at high altitudes, in airplanes. The results have shown a fascinating discrepancy in the passage of time. Clocks positioned at higher altitudes tick slightly faster than those located closer to Earth's surface. This difference occurs because gravitational pull weakens with altitude. The closer one is to a massive object like Earth, the stronger the gravitational field, and consequently the slower time appears to pass. This experiment demonstrates how gravity can bend the fabric of space-time, causing time itself to stretch and shrink in response to the mass and movement of objects. The phenomenon of time dilation has been further tested through experiments involving subatomic particles called muons. These particles, which decay at a specific rate, appear to live longer when traveling at near light speeds. In the upper atmosphere where they are generated, muons race towards Earth at extraordinary velocities. As they approach the planet, the fast pace at which they move causes their internal clocks to tick slower relative to an observer on the ground. This effect, known as time dilation, shows how motion through space affects the passage of time. As an object approaches the speed of light, time seems to slow down for that object relative to a stationary observer. This idea, first proposed by Einstein's theory of special relativity, has been confirmed in a variety of experiments, highlighting the profound connection between time and motion. Scientists have also made use of particle accelerators, enormous machines that propel particles to speeds close to that of light. These accelerators provide another way to test the effects of relativity and the behavior of space-time under extreme conditions. As particles approach light speed, their behavior supports the predictions made by general relativity, offering further evidence that the fabric of space and time is not as straightforward as it may seem. These experiments allow researchers to probe the fundamental nature of the universe, revealing intricate relationships between matter, energy, and the space-time continuum. Through this ongoing process of discovery, scientists are continually refining our understanding of the universe, adding new layers of knowledge to the cosmic puzzle. At the heart of modern physics lie two foundational theories: quantum mechanics and general relativity. While both have proven to be immensely successful in their respective domains, they describe the universe in fundamentally different ways. General relativity, formulated by Einstein in the early 20th century, provides an elegant framework for understanding the large-scale structure of the universe, including the behavior of massive objects like planets, stars, and galaxies. The theory explains how gravity bends and warps the fabric of space-time, causing objects to move in predictable patterns. Picture this concept as a heavy ball placed on a stretched rubber sheet. the ball causes the sheet to bend, and this curvature is analogous to the way mass and gravity influence the geometry of space-time. Quantum mechanics, on the other hand, deals with the behavior of particles at the microscopic level. At this scale, the universe behaves in strange and counterintuitive ways. Particles can exist in multiple states simultaneously, and their exact properties, such as position and momentum, are not determined until they are measured. This uncertainty gives rise to phenomena that seem almost magical, such as particles appearing in two places at once or influencing each other instantaneously over vast distances. These behaviors, which defy classical physics, form the basis of quantum theory, a framework that has revolutionized our understanding of the subatomic world. Yet, when attempting to reconcile quantum mechanics with general relativity, a profound challenge arises. The difficulty lies in merging these two theories into a single unified framework that can explain all aspects of the universe. While general relativity works well for explaining the behavior of large objects like planets and galaxies, it fails to account for the extreme conditions that arise near black holes or during the earliest moments after the Big Bang. In these scenarios, quantum mechanics becomes the dominant force and general relativity's predictions break down. Trying to merge these two very different descriptions of reality is akin to attempting to fit two jigsaw puzzles together that have no overlapping pieces. Quantum mechanics operates within the realm of uncertainty and probability, while general relativity relies on precise deterministic measurements of space and time. This conflict has led to the search for a theory of quantum gravity, an attempt to unify the principles of quantum mechanics and general relativity into a single framework that can explain the dynamics of space-time at all scales. This theory would allow scientists to understand both the behavior of the tiniest particles and the movements of the largest cosmic structures in the same context. Developing a quantum theory of gravity remains one of the most ambitious and elusive goals in physics. However, the potential rewards are immense. A successful theory of quantum gravity could deepen our understanding of the universe, revealing the true nature of space, time, and matter. The concept of the cosmic horizon plays a key role in shaping our understanding of both space and time. The cosmic horizon can be thought of as a boundary in the universe beyond which we can no longer observe or receive information. Imagine standing on a vast beach, gazing out at the ocean. The horizon represents the furthest point you can see, and beyond that lies an area that is invisible to you. Similarly, the cosmic horizon defines the limits of our observable universe. It is determined by the speed of light and the age of the universe. As we peer into the night sky, we are not just observing distant stars and galaxies. We are looking back in time to moments when the universe was much younger. The light from these celestial bodies takes millions or even billions of years to reach us, meaning that the farther away an object is, the older the light we see from it. This relationship between distance and time has profound implications for our understanding of the cosmos. The cosmic horizon also marks the boundary beyond which light has not yet had time to reach us. This means that there are vast regions of the universe that lie beyond our observational reach. The expansion of the universe further complicates this picture. As the universe continues to expand, regions that are currently within our observable range may eventually drift beyond the cosmic horizon. Galaxies that are moving away from us faster than the speed of light will eventually disappear from our view, creating a constantly changing landscape of the universe. This dynamic nature of the cosmic horizon serves as a reminder that time and space are not fixed, but instead are continually shifting and evolving. Cosmic inflation is another fascinating concept that provides insight into the origins of our universe. It refers to the rapid expansion that occurred in the first moments after the Big Bang, when the universe was incredibly small, dense, and hot. During this brief period, the universe expanded at a rate faster than the speed of light. While this might seem paradoxical, it is important to remember that it is not the objects within space that are moving faster than light, but rather the fabric of space itself that is stretching. To visualize this, imagine a balloon being inflated. As the balloon expands, the surface area increases, and this is analogous to how space itself stretched during cosmic inflation. This rapid expansion had a profound impact on the structure of the universe, altering the distances between galaxies and affecting the flow of time itself. The concept of cosmic inflation suggests that the universe during its earliest moments was so small that regions that were once in close proximity to one another became so stretched out that they could no longer communicate. This has left an imprint on the universe's structure that we still observe today. The expansion of space-time during this period was so rapid that it reshaped the cosmos, influencing both its geometry and its history. Cosmic inflation provides a crucial piece of the puzzle in understanding the early universe and how it evolved into the vast, complex structure we see today. Through the study of these phenomena, we gain a deeper understanding of the forces that govern our existence and the universe at large. Cosmic inflation is one of the most groundbreaking theories in modern cosmology, offering a window into the early moments of the universe that continues to shape how we understand both space and time. The concept proposes that shortly after the Big Bang, the universe underwent a brief yet incredibly rapid expansion, stretching far faster than the speed of light. This sudden and dramatic growth, happening in the blink of an eye, not only transformed the primordial universe into the vast and expansive cosmos we observe today, but also laid the groundwork for the fundamental structure of the universe. In a fraction of a second, a region that was once a tiny, dense point exploded outward, transforming the universe from something exceedingly small into a space that was vast beyond comprehension. This moment, known as cosmic inflation, played a pivotal role in shaping the uniformity and structure of the universe, which is still evident in the cosmic microwave background radiation (CMBR) we detect today. These faint remnants of the Big Bang provide a snapshot of the universe when it was just a few 100,000 years old, offering a crucial look at how the universe began to evolve. The smoothness of the CMBR, despite tiny fluctuations, reveals the underlying processes that led to the formation of stars, galaxies, and other cosmic structures. Moreover, the theory of cosmic inflation has had profound implications for the way we understand the large-scale distribution of galaxies. The rapid expansion of space during inflation smoothed out what might have been significant irregularities, ensuring that the cosmos we see today has a uniform temperature and density. As a result, galaxies, stars, and other objects in the universe appear in patterns that can be traced back to the conditions set in motion during that brief but dramatic period of rapid growth. Without cosmic inflation, the universe might have developed in a fundamentally different way, with greater discrepancies in the way galaxies are distributed and the structure of space-time itself. Understanding cosmic inflation also provides a critical piece in the puzzle of the universe's history. By piecing together the fragments of knowledge gleaned from observations of the CMBR and the distribution of galaxies, scientists are able to trace the evolution of the cosmos from its earliest moments, mere fractions of a second after the Big Bang, to the expansive universe we see now. This continuity of time, stretching from the incredibly small to the vast, reinforces the idea that space and time are inextricably linked, concepts that continue to challenge and fascinate physicists and cosmologists alike. In recent years, new technological advancements have radically expanded our ability to observe and understand the cosmos. These developments have made it possible for us to glimpse galaxies that are millions and even billions of light years away, offering insights into the universe's infancy. Among the most significant advancements are the new generation of telescopes, which allow us to peer further into the depths of space, capturing light that has traveled across time itself. These telescopes provide us with invaluable data, helping us to understand not only the evolution of distant galaxies, but also the conditions of the early universe itself, just after cosmic inflation. In addition to powerful telescopes, the growing field of computational modeling has become an essential tool in modern cosmology. These simulations enable researchers to recreate the conditions of the universe in a controlled environment, allowing them to manipulate variables like gravity and time in ways that would be impossible in the real world. By simulating events like the birth of stars, the formation of galaxies, or even the behavior of black holes, scientists can gain deeper insights into the fundamental processes that shaped our universe. These simulations allow us to examine how cosmic events unfold, offering valuable clues that help us understand how the universe continues to evolve. Advancements in quantum technology are also playing a pivotal role in our exploration of the cosmos. Quantum sensors, for example, are incredibly sensitive instruments that can detect the smallest variations in gravitational fields. These sensors have the potential to revolutionize our ability to study some of the most extreme environments in the universe, such as black holes or neutron stars. They could also help us detect gravitational waves, ripples in space-time caused by the collision of massive objects, offering new ways to observe and understand the dynamics of the universe. As quantum technology continues to evolve, it is likely to open up new frontiers in cosmological research, offering fresh perspectives on the very fabric of space-time. Alongside these technological innovations, robotics and artificial intelligence, AI, are transforming the way we explore space. The use of unmanned spacecraft and rovers on planets like Mars is expanding our understanding of not only the red planet itself, but also the broader history of our solar system. Equipped with advanced sensors, cameras, and scientific instruments, these robots can gather data about the Martian landscape, atmosphere, and geology, providing critical information that informs our knowledge of how planets and the universe develop over time. With each new mission, our ability to explore the cosmos becomes more sophisticated, offering deeper insights into the complex interactions between space, time, and matter. As these technologies continue to evolve, our understanding of the universe is also deepening. We are now able to study the interactions of space and time with unprecedented precision, gaining a clearer picture of how the cosmos began, how it evolved, and where it might be headed. Each new discovery prompts further questions, not only about the physical nature of the universe, but also about the fundamental laws that govern it. How does time behave under the extreme conditions of a black hole? What is the true nature of dark matter and dark energy? And perhaps most intriguingly, how are space and time intertwined in ways that continue to defy our expectations? Cosmic inflation is just one of the key ideas that have emerged from these explorations, offering a groundbreaking perspective on the universe's earliest moments. The theory was first proposed by physicist Alan Guth in the early 1980s as a solution to several perplexing problems in the standard model of cosmology. The main motivation behind Guth's idea was to address what is known as the flatness problem, which questioned why the universe appeared to be so uniform in temperature and density, even over vast distances, despite the fact that these regions should not have had time to interact with each other due to the finite speed of light. At the heart of cosmic inflation is the notion that the universe, in its very early moments, expanded exponentially, stretching regions of space that were once incredibly close together. This rapid expansion occurred far faster than the speed of light, and it helped to smooth out any variations in temperature and density, leading to the homogeneous universe we observe today. This phenomenon explains why distant regions of the universe appear to be so similar among us, despite the fact that light from these regions hasn't had enough time to travel to us, as one might expect under normal circumstances. Furthermore, the idea of inflation provides a natural explanation for the current flatness of the universe, where space-time appears to be nearly flat on large scales. Without this rapid inflationary period, the universe's geometry could have been vastly different, leading to a much more chaotic and disordered cosmos. Instead, inflation provided a mechanism by which the universe could expand and smooth out irregularities, creating the large-scale structures that we observe today. Inflation also offers an elegant solution to what is known as the horizon problem. In a universe that expanded at such a rapid rate, regions that were once close together but are now far apart could still share common properties. This allowed them to exchange information and energy, helping to explain why the temperature and density across vast distances are so remarkably similar. The rapid inflationary expansion of the universe not only solved this puzzle, but also set the stage for the formation of the universe's complex structures, including galaxies, stars, and black holes. Perhaps the most compelling evidence supporting the theory of cosmic inflation comes from the study of the cosmic microwave background radiation. This faint glow, which permeates the entire universe, is a direct remnant of the Big Bang. The remarkable consistency in temperature across the CMBR provides a snapshot of the early universe, showing that regions that are now separated by vast distances were once in close contact, exchanging energy and information. This observation is consistent with the predictions of inflationary theory, offering strong support for the idea that the universe expanded rapidly in its earliest moments. Another piece of evidence lies in the distribution of galaxies throughout the universe. Rather than being randomly scattered, galaxies form intricate web-like structures that are consistent with the predictions of cosmic inflation. This arrangement suggests that the early universe, while undergoing rapid expansion, contained slight variations that were amplified over time, leading to the clumpy distribution of galaxies we observe today. Inflation, therefore, not only helps to explain the uniformity of the universe, but also accounts for the large-scale structures that emerged as a result of the initial fluctuations in the density of matter. The theory of cosmic inflation has fundamentally altered our understanding of the universe's origins and evolution. It has provided answers to some of the most perplexing questions in cosmology, while also opening up new avenues of research and discovery. As technology continues to advance and new discoveries are made, our understanding of cosmic inflation and its implications will continue to evolve, bringing us ever closer to unraveling the mysteries of the universe itself. Through these groundbreaking insights, we are not only learning more about the cosmos, but also about the very nature of time and space, and the profound interconnectedness between them. The cosmic history of our universe has fascinated scientists for centuries, and yet our understanding of its earliest moments continues to evolve through a combination of theories, models, and observations. One of the most captivating and essential periods in this narrative is the concept of cosmic inflation, an event that occurred in the moments following the Big Bang. This theory suggests that the universe expanded at an extraordinary rate, far surpassing the speed of light, within a fraction of a second after its inception. While this event was incredibly brief, it left behind a profound and lasting imprint on the structure of the universe we see today. At the heart of this exploration are tiny, almost imperceptible variations in the cosmic microwave background, CMB radiation. These fluctuations, though minuscule, are powerful indicators of the early universe's density differences. The CMB is a faint glow that remains from a time when the universe was still a hot, dense soup of particles. It serves as a snapshot of the universe when it was only a few 100,000 years old. The tiny fluctuations observed within this radiation reveal the seeds of what would later evolve into galaxies, stars, and other large-scale cosmic structures. These variations in density were not random. They follow specific patterns predicted by inflationary models. The fact that these fluctuations match predictions made by these models lends significant support to the idea that the universe underwent a rapid expansion during its early moments, shaping its current structure. In addition to the CMB, advanced observations of gravitational waves provide further evidence for the rapid inflationary period. Gravitational waves, first predicted by Albert Einstein in his general theory of relativity, are ripples in the fabric of space-time caused by massive events like colliding black holes or exploding supernovae. Certain patterns in these waves could point to events that occurred during the time of inflation, further corroborating the idea that the universe underwent a period of exponential growth. Together, these different pieces of evidence, fluctuations in the CMB, gravitational wave observations, and the theoretical framework of inflation, combine to form a compelling case for the existence of an inflationary epoch. This moment of rapid expansion serves as a cornerstone of our understanding of the universe's early history, providing a framework for explaining why the universe is as uniform and smooth as it is today. To fully grasp the importance of cosmic inflation, it helps to imagine the state of the universe immediately after the Big Bang. At that time, the universe was an unimaginably small, hot, and dense point. Within moments, it expanded incredibly fast, much faster than the speed of light, stretching the very fabric of space itself. This rapid expansion caused regions of space that were initially close together to move apart at staggering rates. In the aftermath of this inflation, regions of space that were once in close contact were now so far apart that they could no longer influence one another. The cosmic microwave background radiation is the only surviving remnant of the universe's early hot state. This faint glow carries with it valuable information about the universe's structure at the time when it was only a few 100,000 years old. What is remarkable about the CMB is its striking uniformity. It appears nearly identical in all directions. This uniformity, which might seem puzzling at first glance, is explained by the theory of inflation. During the rapid expansion, any small variations in temperature and density were smoothed out. The process is akin to mixing ingredients in a bowl. As you stir, any differences in texture or consistency are evenly distributed. In the same way, inflation caused small differences in the early universe to be evened out, resulting in the highly uniform appearance we observe today. Once inflation ended, the universe continued to evolve, but the initial conditions set by inflation ensured that the regions we observe in the cosmic microwave background today were in thermal equilibrium. This uniformity created the foundation for the development of galaxies, stars, and other structures that would form over billions of years. In essence, inflation acted as a cosmic equalizer, laying down the groundwork for the ordered universe we now inhabit. However, there is an even more intriguing layer to this theory. The idea of multiple inflationary events suggests that the rapid expansion of the universe might not have been a single event, but rather a series of such expansions, occurring at different times and in different regions of the cosmos. This concept, often referred to as eternal inflation, proposes that our observable universe could be just one of many bubbles in a much larger cosmos. Each inflationary event might create its own distinct bubble, each with unique physical laws, constants, and forms of matter. In this scenario, the universe we observe is just one of potentially countless others, each with its own set of conditions. The implications of multiple inflationary events are profound. For one, it opens the door to the concept of a multiverse, a collection of universes, each with its own characteristics. Some of these bubbles could host entirely different forms of life, while others might be inhospitable to life as we understand it. The possibility that there are other universes with completely different physical laws challenges our very understanding of existence. It forces us to reconsider our place in the cosmos and the nature of reality itself. Moreover, this theory could help explain the remarkable uniformity we observe in our universe. If multiple regions of the cosmos underwent inflationary periods at different times, each would have been smoothed out and homogenized by the rapid expansion. However, the conditions in each of these regions might differ, leading to unique evolutionary outcomes. For instance, some regions might develop entirely different structures, while others might lack the necessary conditions for life to emerge. This could result in a universe of infinite variety, where each bubble experiences its own unique cosmic history. In addition to offering a potential explanation for the uniformity of the universe, the theory of multiple inflationary events also provides insight into the larger processes that shape the cosmos. It forces researchers to ask fundamental questions about the origins of the universe and the forces that drive its evolution. By investigating the potential for multiple inflationary periods, scientists are pushing the boundaries of what we know about the nature of the cosmos and the underlying principles that govern it. Simulating the inflationary period is an essential tool for researchers who are trying to better understand the origins and evolution of the universe. These simulations rely on fundamental principles of physics, such as particle physics and general relativity, to model the behavior of the universe during its earliest moments. Using these theoretical frameworks, scientists can develop mathematical equations that describe how energy, pressure, and temperature interacted in the extremely hot and dense early universe. These equations provide the foundation for simulations that model the inflationary period and the fluctuations that occurred during this time. Through the use of computer simulations, scientists can visualize the effects of inflation on the universe. By inputting variables such as density, temperature, and energy distribution, they can create virtual universes that mimic the conditions of the early cosmos. These simulations allow researchers to observe how slight changes in the initial conditions of the universe could lead to different cosmic outcomes. For example, small fluctuations in the energy fields could result in the formation of galaxies, stars, and other structures, or they could lead to entirely different outcomes depending on the precise conditions. To ensure the accuracy of these simulations, researchers compare their results with actual observational data. The most important source of data is the cosmic microwave background radiation, which provides a snapshot of the universe's state at an early stage. By comparing their simulated outcomes with the observed patterns in the CMB, scientists can refine their models and improve their understanding of the inflationary process. These comparisons help to ensure that the simulations accurately reflect the complex dynamics of the early universe, allowing scientists to draw more reliable conclusions about the mechanisms at work. Despite the immense progress made in understanding cosmic inflation, studying this epoch presents significant challenges. The first major obstacle is the fact that the inflationary period occurred so long ago, just moments after the Big Bang, that it is beyond the reach of direct observation. Any light emitted during this time has long since been stretched out by the expanding universe, making it impossible to capture direct images or data from this era. Instead, scientists must rely on indirect evidence, such as the cosmic microwave background and gravitational waves, to infer what happened during the inflationary period. Moreover, the precision required to detect the faint signals that could confirm the predictions of inflationary models is extraordinarily high. Researchers must look for specific patterns, called imprints, in the cosmic microwave background and other phenomena that could confirm the inflationary theory. These imprints are incredibly subtle, often obscured by other cosmic noise, making it difficult to isolate the relevant data. To address this challenge, scientists have developed advanced instruments and techniques designed to detect these faint signals and provide a clearer picture of the early universe. In the end, the study of cosmic inflation is an ongoing and dynamic field of research. While we have made great strides in understanding the early universe and the events that shaped its evolution, many questions remain unanswered. The theory of inflation, particularly the possibility of multiple inflationary events and the existence of a multiverse, continues to push the boundaries of our knowledge. It challenges our understanding of the cosmos and our place within it, prompting us to rethink the very nature of reality. The concept of cosmic inflation, an idea that has radically transformed our understanding of the universe's origins, suggests that the universe experienced an incredibly rapid expansion in the moments immediately after the Big Bang. This event, known as inflation, would have stretched space-time itself faster than the speed of light, vastly increasing the universe's size in a fraction of a second. To grasp the significance of this idea is to understand not only the origin of our cosmos, but also the remarkable uniformity we observe across vast cosmic scales today. However, as our scientific understanding advances, we are presented with the challenge of refining or even revising this theory based on new observations and technologies. The landscape of inflationary models is far from uniform. Each version of the theory offers a different interpretation of how inflation might have unfolded, leading to a range of predictions that scientists are now tasked with evaluating. The challenge for researchers lies in distinguishing between these competing models. It is not simply a matter of collecting more data, but rather determining which of these theoretical frameworks best matches the observations that we can make. The diverse set of possibilities adds a layer of complexity to the scientific inquiry, making it difficult to find consensus within the scientific community. Moreover, inflationary models are not isolated within one specific field of research. They are interwoven with various other areas of scientific exploration, including particle physics, quantum mechanics, and cosmology. These fields must work together, each contributing insights to the larger puzzle of understanding the early moments of the universe. Yet, coordinating these disparate areas of knowledge is no small feat. The theoretical and practical challenges of merging such different scientific languages, methodologies, and perspectives complicate efforts to make real headway in resolving the mysteries of cosmic inflation. This intricate web of theoretical possibilities, experimental challenges, and interdisciplinary cooperation underscores the profound difficulty involved in our quest to uncover the true nature of the universe's beginnings. But it also highlights the remarkable ambition and ingenuity of scientists working in this field, as they tackle questions that touch upon the very fabric of existence itself. Cosmic inflation is not just a scientific theory. It is a journey into the heart of what makes the universe tick, a puzzle whose resolution could dramatically alter our understanding of everything from the laws of physics to the nature of reality. As we look toward the future, several avenues of exploration could provide the breakthrough insights that we need to refine or possibly even overhaul the current inflationary models. One of the most exciting developments in this pursuit is the advent of new, more powerful telescopes. These advanced instruments could allow scientists to peer deeper into the cosmos, observing regions that were previously beyond reach. By looking further than ever before, we could gather new data on the cosmic microwave background (CMB) radiation, the faint afterglow of the Big Bang that carries invaluable information about the conditions in the early universe. The study of the CMB offers a potential treasure trove of information about the universe's infancy. By analyzing the tiny fluctuations in the CMB, scientists can gather insights into the physics of the inflationary period. These fluctuations are remnants of the quantum processes that occurred during inflation, offering a window into the forces at play during those first moments of the universe's existence. Any new findings, whether they involve unexpected patterns or entirely new features, could force a reevaluation of our current models of cosmic inflation. With each new observation, there is the possibility of unveiling new dimensions of understanding. In addition to observational tools like telescopes, another key area of progress is the improvement of computational simulations. These simulations, which model the behavior of the universe under different physical conditions, have become increasingly sophisticated. By running simulations with varying parameters, such as different types of matter, forces, and physical laws, researchers can explore a wider range of possible scenarios and test how well these simulations align with actual observations. If these simulations suggest that alternative models of inflation or entirely new phenomena could be at play, the implications for our understanding of the cosmos could be profound. The more closely simulations match real-world data, the more likely they are to reveal new insights into the process of cosmic inflation and the universe's earliest moments. Yet another potential breakthrough could come from the study of gravitational waves. These ripples in the fabric of space-time, generated by massive accelerating objects like merging black holes or neutron stars, could offer a completely new avenue for understanding the early universe. Experiments designed to detect gravitational waves are already underway, and there is hope that they will eventually provide direct evidence of processes that occurred during the inflationary epoch. If scientists can detect gravitational waves that originated in the very early moments of the universe, they could provide an unprecedented way to test inflationary models. These waves could either support or challenge the current understanding of inflation, offering direct evidence that could either confirm or refute various theories. Another exciting avenue for potential discovery involves the search for new particles or fields in high-energy physics. The exploration of fundamental particles and the forces that govern them could shed light on the physics of the early universe. If new particles or fields are discovered, they could lead to a rethinking of the mechanisms behind inflation, potentially offering a more complete or refined understanding of the universe's early expansion. The creation of specific experimental conditions in laboratories designed to explore these new particles might provide vital clues about the forces that shape the universe in its infancy, helping to answer questions about how inflation occurred and what that means for the universe's structure and fate. In sum, as technology continues to improve, simulations become more refined and new experimental techniques emerge, scientists are on the precipice of potential discoveries that could dramatically reshape our understanding of cosmic inflation. Each new piece of evidence, whether it comes from telescopic observations, gravitational wave detection, or particle physics experiments, has the potential to transform the way we view the universe. These breakthroughs may not only refine our current models of inflation, but could fundamentally alter our conception of the cosmos itself. The search for answers to these questions underscores the dynamic and ever-evolving nature of scientific inquiry, a testament to humanity's relentless drive to understand the universe. At the heart of all these discussions lies the profound philosophical and existential implications of an inflationary universe. The idea that the universe expanded at speeds faster than the speed of light shortly after the Big Bang raises fundamental questions not just about the origins of the cosmos, but also about the nature of space, time, and reality itself. If inflation allowed the universe to expand beyond any conceivable boundary, then what are the limits of our understanding? Can we truly comprehend a universe that stretches beyond the edges of our perception? The notion of a universe without boundaries forces us to confront the inherent limitations of human knowledge. It raises the question of whether the universe we observe is the whole of reality or if there are parts of it that remain forever inaccessible to us. These existential questions, while not easily answered, open up profound avenues of philosophical inquiry, compelling us to think about our place in a universe that may be far more vast and complex than we can even imagine. Furthermore, the theory of inflation opens the door to the intriguing possibility of the multiverse, a concept that suggests our universe may not be unique, but rather one of many. If inflation can occur multiple times, it could give rise to an infinite number of disconnected universes, each with its own set of physical laws and constants. This raises profound questions about the nature of existence. Are we simply a random occurrence in an unimaginably vast cosmos, or is there a deeper purpose to our place in this universe? Are we special because we exist in this particular universe, or are we just one possibility among countless others? The notion of a multiverse challenges our understanding of necessity and chance, prompting reflections on meaning and purpose in a universe that may be far more diverse than we can comprehend. In addition to the metaphysical implications, the idea of a multiverse also raises significant questions about the limits of observation and knowledge. If there are universes beyond our own, and if many of them are governed by different laws of physics, what does this mean for our ability to know the true nature of reality? Are there truths that are forever beyond our reach, hidden in realms that we can never observe? The multiverse theory forces us to confront the boundaries of scientific knowledge, challenging us to recognize that our understanding of the universe might always be incomplete. Through these multiple lenses, cosmic inflation, the search for evidence, and the philosophical implications of an expanding universe, we are drawn into a deeper understanding of both the cosmos and ourselves. Whether or not the multiverse exists, and whether or not we ever fully comprehend the origins of the universe, one thing is certain: the pursuit of knowledge in this field has only just begun. With each new discovery, the vastness of the cosmos and the mysteries of its origin grow ever more complex, offering an endless horizon for exploration and understanding. However, some theories propose the existence of other universes, each with its own set of dimensions, potentially leading to realities far beyond our comprehension. These additional dimensions could radically alter fundamental aspects of our reality, such as how time operates or how the forces of nature interact with one another. The changes could result in phenomena that are unpredictable, strange, and entirely foreign to anything we have encountered in our own universe. Imagine, for instance, a world where time doesn't flow as we know it, or where the basic forces of gravity and electromagnetism behave in ways we simply cannot anticipate. Such speculations open the door to a vast, intriguing array of possibilities that challenge the boundaries of human understanding. In addition to this, some theorists suggest that other universes might be governed by completely different sets of fundamental constants than the ones we observe in our own. Within our universe, certain constants, such as the strength of gravity or the charge of an electron, are stable and fixed. But in an alternate universe, these values could be drastically different. These alterations could lead to a universe that behaves in fundamentally different ways, perhaps even making it impossible for atoms to exist as they do here. The very fabric of such a reality could be so different that the building blocks of matter might not even form, or they could be arranged in ways that are unrecognizable to us. This idea paints a picture of the universe, not as a singular unified entity, but as one of many, each governed by a unique set of rules that could vary in unimaginable ways. The concept of the multiverse suggests that our universe is just one of countless others, each with its own laws of physics, dimensions, and histories. The diversity of these universes could be staggering, with each one potentially representing an entirely different arrangement of physical properties, timelines, and realities. This raises profound questions about the very nature of existence itself. If we consider the multiverse, we are invited to imagine a cosmic landscape that is infinitely richer and more varied than what we currently perceive. It suggests that the universe we inhabit may not be the only one, and that other, perhaps radically different worlds might exist just beyond the edge of our observable reality. One of the more captivating models to emerge from this idea is the bubble universe theory. This concept offers a fascinating way of thinking about the cosmos and its potential for multiple universes. Picture our universe as a single bubble floating within an immense cosmic foam. Each bubble represents a distinct universe, and the foam is made up of an infinite number of these bubbles, each one potentially formed through a process that took place during the early stages of our universe's expansion. This rapid growth is referred to as cosmic inflation, a period of swift and dramatic expansion that happened just after the Big Bang. During this time, space itself expanded faster than the speed of light, creating pockets, bubbles, if you will, that continued to grow and evolve independently. Within each of these bubbles, physical laws and constants could evolve in different ways. The specific conditions present during the bubble's formation would determine the characteristics of the universe that it houses. Some of these universes could develop the necessary conditions for stars, planets, and life, while others might be completely inhospitable, devoid of anything resembling the structures that we recognize as necessary for the existence of life. This concept paints a picture of a universe far grander and more complex than our current understanding allows. It suggests that if these bubbles continue to form and separate, the multiverse could consist of an almost infinite number of universes, each with its own unique properties and potential. This way of thinking challenges the very foundation of our understanding of the cosmos and invites us to wonder whether the reality we know is just one small part of an infinitely larger and more varied collection of possible worlds. The idea of the multiverse also raises the intriguing possibility that if these bubbles can form, and if they can exist simultaneously, there could be countless universes, each with distinct characteristics and laws. This framework for understanding the universe leads to a compelling question. What might lie beyond our own universe, hidden in the infinite expanse of reality? The concept of a multiverse suggests a cosmic reality far more intricate and vast than what our senses allow us to experience. There could be universes that are vastly different from our own, and the potential for diversity in the ways that matter, energy, and life manifest could be beyond our wildest imagination. Supporting evidence for the multiverse theory has emerged from the realms of physics and cosmology, especially from theories like cosmic inflation. This theory suggests that our universe, which began with the Big Bang, may have undergone a period of rapid expansion that set the stage for the formation of other universes. If this process happened at different times and in different regions of space, it could have given rise to multiple universes, each expanding in its own unique way. This model of cosmic inflation implies that distinct regions of space might have gone through inflation at different points, leading to the formation of separate bubbles or universes, each with its own set of physical constants and rules. One potential way to test the existence of these parallel universes is by looking for patterns or irregularities in the cosmic microwave background, CMB, radiation, which is the faint afterglow of the Big Bang. The CMB contains clues about the early conditions of the universe and could reveal subtle imprints left by interactions between different universes, should they exist. However, this evidence is still speculative, and it is far from conclusive. The challenges in confirming the multiverse theory stem from the fact that if these other universes exist, they are fundamentally beyond the reach of our observational instruments. On the other hand, a major challenge to the multiverse hypothesis is the difficulty in testing or observing universes that may exist beyond our own. Scientific theories are generally considered valid only when they can be tested or measured. Since other universes lie outside the range of our observation, many scientists argue that the multiverse is not a scientifically rigorous idea. Essentially, if we cannot gather empirical evidence or make observations about these other universes, the very idea of their existence becomes a matter of philosophical speculation rather than scientific fact. This is a major hurdle for proponents of the multiverse, as the lack of testability makes it difficult to substantiate or refute the theory in any meaningful way. Another area where the multiverse theory intersects with ongoing scientific debates is the concept of fine-tuning. Our universe seems to be uniquely set up to support life, with conditions that are just right for the existence of matter, stars, and living organisms. Some have suggested that this fine-tuning is not the result of random chance, but rather the outcome of many universes, some of which are capable of supporting life, and others that are not. If the multiverse theory is correct, we might be one of the lucky few universes in which the conditions are right for life. In this case, the fine-tuning we observe could be the result of a selection effect. We are only able to observe a universe where life can exist because it is the only one that allows us to do so. This brings us to the anthropocentric principle, which helps us explore the question of why the universe seems to be so finely tuned for life. The principle suggests that the reason the laws and constants of our universe are compatible with life is that we are here to observe them. In other words, we find ourselves in a universe that seems perfectly suited for our existence because we are the ones asking the question. When combined with the multiverse theory, this concept gains an intriguing new dimension. The multiverse hypothesis proposes that there could be an infinite number of universes, each with different properties. Some of these universes will have the necessary conditions for life to form, while others will not. From this perspective, it's not surprising that we live in a universe that allows life to thrive. It's simply the universe where life has had the chance to develop. This intersection between the anthropic principle and the multiverse theory invites us to rethink our place in the cosmos. It suggests that the reason we observe such fine-tuning in our universe might be because we are part of a larger and more complex reality. A reality that contains many universes, some capable of supporting life and others not. The multiverse, then, doesn't just help explain why our universe seems so perfectly suited for life. It suggests that we are here because we find ourselves in the one universe that has the right conditions for life to emerge. However, testing the multiverse hypothesis presents its own unique set of challenges. The core idea of the multiverse, that our universe is one of many, each existing in its own separate reality, presents a problem for traditional scientific methods. Other universes, if they exist, are beyond the reach of our instruments. We are limited to observing and measuring phenomena within our own universe, and any evidence for the existence of other universes would, at best, be indirect. Furthermore, the theories that suggest the possibility of a multiverse, such as string theory and cosmic inflation, are still in development and are often mathematically complex. They are difficult to test in a clear, straightforward way, and many of their predictions remain speculative. In the end, while the idea of the multiverse opens up a vast array of possibilities for what might exist beyond our own universe, it also raises fundamental questions about the limits of scientific inquiry. If we can't directly observe or measure other universes, can we truly claim that they exist? Until scientists can develop a way to test or observe these other realities, the multiverse remains a captivating yet elusive idea, one that invites us to imagine the vast, unexplored reaches of the cosmos, even if we may never be able to touch them. The notion of the multiverse, an idea that stretches the boundaries of what we consider possible, raises profound and complex questions that echo far beyond the realm of physics. Even if we were to one day gather definitive evidence supporting the existence of multiple universes, this discovery would not just affirm the existence of realms beyond our own. Instead, It would ignite a flood of philosophical and scientific inquiries that could reshape our very understanding of existence, observation, and the nature of reality itself. The mere thought of multiple universes forces us to confront difficult questions about the scope of scientific inquiry and the very nature of what we perceive as knowledge. The crux of this dilemma lies in whether science, as we know it, should evolve to accommodate phenomena that are currently beyond the reach of observation. Can we, as human beings, modify our definitions of scientific validity to include realms that are inherently unobservable? This challenge, as daunting as it may seem, is one that keeps the scientific community engaged and stimulated. It forces physicists, cosmologists, and philosophers to grapple with the question, is the multiverse a legitimate scientific hypothesis or merely an imaginative construct based on theoretical speculation? The debate is ongoing, with many scientists arguing that it is impossible to prove the existence of the multiverse in the traditional sense, while others propose that as our tools of observation and understanding continue to evolve, what is once unobservable may one day fall within the realm of scientific investigation. Indeed, as our theoretical frameworks advance, the boundaries of exploration may shift, but the multiverse, as of now, remains tantalizingly just beyond the horizon of empirical science. Researchers continue their tireless efforts to probe the nature of existence, pushing forward with an understanding that what is true today may be fundamentally different tomorrow. Their work navigates through the intricate web of uncertainty in examining each layer of evidence in search of answers to one of the most profound questions of our time. At its core, the concept of the multiverse suggests that our universe may be just one among many, potentially infinite universes. This idea is not the product of a single branch of science, but rather the intersection of multiple fields of physics, each contributing its own tools and perspectives to the grand puzzle. The collaboration between cosmology, quantum mechanics, string theory, and general relativity is crucial to building a coherent picture of what a multiverse could be. Each branch, though distinct in its approach, offers unique insights that, together, form a collective understanding of the cosmos. Cosmology, the study of the origin and structure of the universe, plays an indispensable role in this quest. Cosmologists use tools like the cosmicrowave background radiation, the faint afterglow left over from the Big Bang, to explore the conditions that led to the formation of our universe. This radiation serves as a time capsule, capturing a snapshot of the universe at a critical moment in its history. It is from these observations that scientists speculate about the conditions necessary to produce not just our universe, but potentially many others. Quantum physics, with its focus on the behavior of subatomic particles, adds another layer of complexity to the multiverse hypothesis. Quantum mechanics introduces the concept of superposition, wherein particles can exist in multiple states simultaneously. Some interpretations of this theory suggest that each decision, each possibility, might result in a branching of reality, creating parallel universes for every potential outcome. This quantum perspective opens up a new dimension of what a multiverse could be, suggesting not just the existence of multiple universes, but an entire web of realities, each representing a different version of events and outcomes. String theory adds yet another profound dimension to this theoretical landscape. According to string theory, the fundamental building blocks of the universe are not point-like particles as traditionally believed, but tiny vibrating strings. These strings exist in higher dimensions of space, far beyond the 3 dimensions we experience daily. Some string theory models predict a vast landscape of possible universes, each with its own distinct physical laws, suggesting that the multiverse may not be a singular, unified concept, but a collection of vastly different universes, each operating according to different rules of physics. General relativity, Einstein's theory that explains gravity's influence on the fabric of space and time, also plays a crucial role in shaping our understanding of the multiverse. General relativity describes how mass and energy warp space-time, and it provides a framework for theorizing how different universes might exist, each with its own geometry and physical properties. The interplay between mass, energy, and space-time could, in theory, give rise to entirely distinct universes, each with its own unique set of laws and dimensions. While these branches of physics are often treated as separate disciplines, they do not function in isolation. They intertwine and collaborate, generating new theories, mathematical models, and even computer simulations that help researchers probe the boundaries of reality. It is through these combined efforts that the concept of the multiverse transforms from mere speculation into a scientifically rich and compelling field of inquiry. Though questions remain unanswered and much evidence is still needed, the cumulative work of these disciplines continues to push the boundaries of human understanding, bringing us closer to unraveling the mysteries of the universe. The implications of the multiverse theory extend far beyond the realm of physics. It challenges our understanding of existence, reality, and our place in the cosmos. Imagine, if you will, that our universe is just one of countless bubbles floating in a vast ocean, with each bubble representing a different universe. Each of these universes might have its own set of physical laws, dimensions, and conditions. In some universes, the very fabric of reality could be fundamentally different from what we experience here and now. Perhaps in one universe, the laws of gravity behave in an entirely alien way. In another, time itself might flow backward, or the concept of life may take on an entirely new form. This vision forces us to reconsider what it means to be part of this universe. If ours is merely one of countless realities, then our sense of uniqueness, our sense of being in the one true universe, may need to be reevaluated. The multiverse, with its infinite possibilities, forces us to confront the notion that our existence could be nothing more than a random occurrence among countless other potential realities. This calls into question the idea of universal truth, suggesting that each universe could operate according to its own set of laws and truths, thus making reality infinitely more complex and diverse than we had ever imagined. Moreover, the concept of the multiverse sparks deep philosophical questions about identity, free will, and destiny. If there are infinite versions of ourselves existing in parallel universes, what defines our sense of identity? Are we simply the product of the specific parameters of this universe, or is there something more universal that connects all of existence? In the multiverse, every decision we make could create a new version of ourselves, each one taking a different path based on the choices made. This raises the question, how do we define who we truly are? Are we merely the sum of our choices, or is there something intrinsic, something fundamental, that transcends the shifting sands of multiple realities? At the same time, the notion of the multiverse challenges our understanding of free will and moral responsibility. If every choice leads to the creation of an alternate universe, does this imply that our decisions are not as significant as we once believed? Are we truly responsible for our actions, or are they merely a part of an endless cascade of branching realities, each one independent of the others? From an ethical standpoint, the multiverse theory suggests that the moral weight of our decisions might be different in each universe, where actions considered wrong in one universe could have entirely different outcomes in another. Such ideas force us to re-examine our beliefs about ethics and morality, perhaps shifting our focus from absolute standards to a more relativistic understanding. If the multiverse is real, then ethical dilemmas might not have a single universal solution, but rather a range of possible outcomes, each shaped by the specific laws and realities of the universe in which they occur. This perspective could encourage us to think more deeply about the implications of our actions, not just within the context of our own universe, but across the vast expanse of existence itself. The multiverse also leads to existential reflections about the meaning and purpose of life. If there are countless alternate versions of ourselves living out infinite variations of our lives, does this diminish the significance of any one version of our existence? On the one hand, some might find comfort in the idea that no matter what choices they make, every possible path they could have taken is being realized somewhere in the vast expanse of the multiverse. On the other hand, the sheer multiplicity of possible lives could lead to a sense of insignificance, as the uniqueness of any individual experience is drowned in the ocean of infinite possibilities. But in embracing the idea of the multiverse, we are also invited to rethink what it means to live a meaningful life. It challenges us to explore the deeper connections that may link all versions of ourselves, and to understand that our actions, though part of an infinite web of reality, may still carry weight in shaping the world in which we live. The multiverse, in its boundless possibilities, pushes us to explore our place in the cosmos and reconsider the true nature of existence. Ultimately, the pursuit of understanding the multiverse is more than a scientific endeavor. It is a journey that invites us to explore the deepest, most fundamental questions of existence, questions about reality, identity, and the nature of the universe itself. As we continue to study the cosmos, both through advanced instrumentation like the cosmic microwave background, CMB, and through the creative intersection of multiple fields of physics, we inch closer to a deeper understanding of the vast, mysterious world around us. The multiverse remains one of the most captivating, enigmatic ideas ever proposed, and whether we ever uncover evidence for its existence or not, it will continue to inspire both scientific inquiry and philosophical reflection for generations to come. The cosmic microwave background, or CMB, is an essential piece of the cosmic puzzle, offering us a glimpse into the early universe and allowing scientists to explore the building blocks of everything we observe today. It serves as a vast, almost uniform map of the universe's infancy, providing critical information about its overall composition. Through the study of the CMB, researchers are able to deduce the proportions of ordinary matter, and dark energy that make up the cosmos. These findings not only deepen our understanding of the universe's structure, but also inform the ongoing investigations into the most fundamental questions of physics and cosmology. When we look at the CMB, we are gazing at the remnants of light that traveled across the universe more than 13 billion years ago, shortly after the universe's birth. This light is a relic from a time when the cosmos was just about 300,000 years old, an era marked by a hot, dense, and rapidly expanding state. During this time, the universe was filled with energy and particles. As the universe continued to expand, it began to cool, allowing protons and electrons to combine into hydrogen atoms. This cooling process enabled light to travel freely for the first time in the universe's history, and that light has continued to journey through space ever since. What we detect today as the CMB is the faint glow of this ancient light, now stretched and cooled as the universe has expanded over the ages. The most compelling aspect of the CMB lies in its uniformity. At first glance, the CMB appears almost perfectly homogeneous when observed across the entire sky. However, hidden within this seemingly smooth radiation are subtle variations, minute fluctuations in temperature that offer invaluable clues about the universe's early conditions. These temperature differences, though incredibly small, serve as fingerprints of the gravitational forces that shaped the cosmos. You can think of these fluctuations as ripples in a pond after a stone is thrown in. Some regions of space are slightly warmer or cooler than others, indicating that matter was slightly more concentrated in these areas. Over time, these regions of higher density began to attract more matter, giving rise to the galaxies, stars, and cosmic structures we see today. These tiny variations in temperature, though seemingly insignificant, are of enormous importance. They provide scientists with crucial information about how the matter in the early universe was distributed and how gravitational forces influenced the formation of the first stars and galaxies. In some regions where the density of matter was slightly higher, gravity began to pull in more matter, causing these areas to become even denser. Over billions of years, these small differences in density expanded, eventually leading to the formation of vast clusters of galaxies and enormous cosmic voids, large-scale structures that we observe in the universe today. By examining the CMB, scientists gain critical insights into the forces that governed the early universe, helping us understand how the universe evolved from a chaotic, hot, and dense state into the large, intricate cosmic structure we observe today. Furthermore, the CMB is not just a map of the universe's composition, but also a key piece of evidence supporting the Big Bang Theory. Picture the universe as a balloon being inflated. This analogy provides an excellent way to visualize the rapid expansion that took place during the early stages of the universe. In its infancy, the universe was an incredibly hot and dense fireball, teeming with energy and particles. As the universe began to expand, it also cooled, which allowed the formation of atoms and the release of light. The CMB represents the remnants of this light, which has now been stretched to a much longer wavelength as the universe expanded. This radiation fills the cosmos and appears to come from every direction in space, almost uniformly. However, the minute variations in its temperature reveal the underlying structure of the early universe. In addition to temperature fluctuations, the CMB also provides us with critical information about the polarization of light from the early universe. Polarization refers to the alignment of light waves in particular directions, rather than them being scattered randomly. The study of polarization within the CMB gives us further insights into the universe's earliest moments, especially during the period known as inflation. Inflation refers to a period of rapid expansion in the universe that occurred in the first fraction of a second after the Big Bang. During this brief but crucial phase, the universe expanded exponentially, stretching tiny quantum fluctuations into large regions of space, setting the stage for the formation of galaxies, stars, and other cosmic structures. The polarization of the CMB can be classified into two main types: E-mode and B-mode polarization. E-mode polarization is more common and arises from ordinary density fluctuations in the early universe. This question touches upon some of the most fundamental aspects of cosmology and quantum mechanics, and resolving it could revolutionize our understanding of the universe's origins. Another mystery centers around the strange patterns of polarization in the CMB. The polarization of the CMB contains information about gravitational waves, ripples in space-time that propagate outward from the sources that created them. Scientists are particularly interested in whether these gravitational waves originated during the inflationary period, as predicted by the theory of inflation. Detecting these waves would not only provide direct evidence of inflation, but also offer clues about the expansion rate of the universe in its earliest moments. The search for these signals is one of the most exciting areas of contemporary cosmology, as it could reveal crucial details about the birth of the universe and its subsequent evolution. Ultimately, the cosmic microwave background is more than just a faint glow that fills the universe. It is a powerful tool for understanding the universe's history, composition, and fundamental physics. From its origins as a faint echo of the Big Bang, to its potential to reveal the secrets of inflation and gravitational waves, the CMB continues to be one of the most important sources of information about the universe's past and its ongoing evolution. Through the study of this ancient radiation, scientists are gradually piecing together the story of the cosmos, an ongoing narrative that stretches back to the very beginning of time itself. The enigma of dark matter stands as one of the most profound mysteries of modern science. While the cosmic microwave background, CMB, offers compelling evidence of its existence, the nature of dark matter continues to evade the understanding of physicists and cosmologists. This elusive substance does not emit, absorb, or reflect light, which makes it virtually invisible to traditional methods of detection. Yet, its presence is inferred from the gravitational effects it has on visible matter, radiation, and the large-scale structure of the universe. What is dark matter made of? How does it interact with the ordinary matter that makes up the stars, planets, and even ourselves? These fundamental questions remain unanswered and drive an intense and ongoing wave of research into the unknown. As scientists strive to unravel the enigma of dark matter, another equally perplexing phenomenon is also calling for investigation: dark energy. The CMB, with its subtle yet profound clues, hints at the existence of this mysterious force believed to be responsible for the accelerated expansion of the universe. Despite its prominence in current cosmological models, the true nature of dark energy remains one of the most confounding questions in physics. Is it a constant force that drives the cosmos apart? Or is it something entirely different, a transient effect that might evolve as the universe ages? These and other questions loom large in the minds of researchers, urging them to probe deeper into the very fabric of space and time. What makes these questions particularly exciting is that each holds the potential to rewrite the very foundations of cosmology. The answers may not only reshape our understanding of the universe's origin, but also change our conception of its future. As we look to the CMB for answers, we realize that there is still much to learn from this cosmic relic. Clues that may eventually reveal the hidden forces that govern the universe. including the very nature of dark matter and dark energy. The cosmic microwave background, CMB itself, is often described as a faint afterglow of the Big Bang, a snapshot of the universe captured just a few 100,000 years after its birth. This relic radiation is not just a remnant of the past, it is a living map, guiding researchers through the early stages of the universe's evolution. When the universe was young, it was a hot, dense plasma where light and matter were constantly interacting, preventing photons from traveling freely. However, as the universe cooled, matter began to condense into neutral atoms, allowing light to finally escape. This moment, known as decoupling, left an imprint on the CMB that scientists can still observe today. The study of the CMB has made remarkable strides over the past few decades, largely thanks to advances in technology. In the early years, researchers used simple radio receivers to detect the faint radiation emitted by the universe. These initial efforts were limited by the sensitivity of the equipment and the noise from other sources, which made it difficult to obtain clear and precise data. However, as technology progressed, the development of more sophisticated instruments, such as highly sensitive detectors and advanced data processing algorithms, allowed scientists to capture more detailed and accurate images of the CMB. One of the major breakthroughs in CMB research came with the launch of satellite missions such as the Cosmic Background Explorer, COBE, which was launched in the late 1980s. COBE was equipped with highly sensitive detectors that could measure temperature fluctuations in the CMB across the entire sky. These tiny fluctuations, though minute, provided crucial information about the early universe's structure and composition. Subsequent missions, such as the Wilkinson Microwave Anisotropy Probe, AWAMAP, further refined these measurements, leading to more precise maps of the CMB. These maps helped scientists estimate the age of the universe, its composition, and provided some of the first direct evidence for the existence of dark energy. In recent years, even more advanced telescopes and instruments have been developed both on the ground and in space. With improved resolution and enhanced methods for data processing, researchers are now able to probe finer patterns within the CMB, gaining deeper insights into the forces that shape the universe in its infancy. The latest projects, such as the Polarized Radiation Imaging and Spectroscopy mission, PRISM, focus on studying the polarization of the CMB, the direction in which the light waves oscillate. This polarization can reveal information about the universe's early conditions, including the process of cosmic inflation, a brief but incredibly rapid expansion that occurred just moments after the Big Bang. The journey of CMB research has been one of continuous improvement, with each new development in instrumentation and data analysis bringing scientists closer to uncovering the universe's deepest secrets. Each technological leap opens up new doors, allowing cosmologists to test their theories with unprecedented precision. As a result, our understanding of the cosmos continues to evolve, revealing new layers of complexity that were once unimaginable. The CMB, far from being a relic of the past, remains one of the most powerful tools in our quest to understand the universe. The CMB, by virtue of its origin, holds invaluable clues about the early universe. Formed just moments after the Big Bang, it consists of faint remnants of heat that permeate all of space. This ancient light provides a snapshot of the universe at a time when atoms were just beginning to form, allowing scientists to probe the state of matter and energy in those early days. By analyzing the CMB, researchers can uncover the density and distribution of matter across the cosmos, giving insight into the universe's expansion rate. Consider the universe as a vast, dynamic entity set into motion by the Big Bang. The speed at which the universe expands and how that speed changes over time can offer vital clues about its fate. The CMB also reveals minute variations in temperature across different regions of space, fluctuations that indicate where matter began to clump together, eventually forming the galaxies and clusters of galaxies we observe today. By studying these fluctuations, scientists can learn about the universe's geometry. For instance, a flat universe suggests that it will continue expanding forever, albeit at a slowing rate, while a closed universe might eventually collapse back in on itself in a cataclysmic event known as the Big Crunch. Moreover, the CMB also reveals the influence of dark energy, a mysterious force that is believed to be driving the accelerated expansion of the universe. If dark energy is constant or increases over time, the universe may continue to expand forever, leading to a scenario where galaxies drift further apart and stars burn out. On the other hand, if dark energy were to diminish, the universe's expansion might slow, stop, and eventually reverse, leading to a contraction and possibly a big crunch. Thus, the CMB serves as a kind of cosmic guide, offering crucial insights into the possible futures of the universe. In addition to providing a map of the universe's structure and expansion, the CMB has another crucial role, revealing the anomalies that prompt scientists to question and refine their models of the cosmos. As scientists analyze the data, they often encounter unexpected features or irregularities, anomalies that deviate from the predictions of current theories. These anomalies are not to be dismissed, rather, they spark new avenues of investigation. Are these anomalies simply errors in measurement, or do they signal something more profound? Perhaps they reveal new physics that extends beyond the limits of current models. Some anomalies might even provide evidence for phenomena like gravitational waves, ripples in space-time caused by cosmic events such as black hole mergers. When anomalies are detected in the CMB, researchers first work to ensure that they are not the result of errors in measurement or data collection. Once verified, these anomalies are considered for a range of possible explanations. For instance, they could suggest the presence of unknown structures, or they might offer new insights into the theory of cosmic inflation, which proposes that the universe underwent an incredibly rapid expansion immediately after the Big Bang. Understanding these anomalies, however, requires collaboration between scientists from different fields, working together to test, debate, and refine their ideas. In this sense, the study of the CMB is not merely a technical exercise. It is a global, collaborative effort to uncover the mysteries of the universe. Each anomaly is not just a puzzle to be solved, but also an opportunity to gain deeper insights into the universe's origin, composition, and the fundamental forces that govern its evolution. Beyond the CMB, cosmic rays offer another fascinating glimpse into the high-energy universe. Cosmic rays are particles, typically protons or atomic nuclei, that travel through space at nearly the speed of light. These particles can originate from a variety of sources, ranging from our sun to the explosive deaths of massive stars, supernova, that occur in distant galaxies. When cosmic rays enter Earth's atmosphere, they collide with atmospheric molecules, triggering a cascade of secondary particles, including muons, pions, electrons, and positrons. These particles can be detected on the ground, providing valuable information about the cosmic events that produced them. The discovery of cosmic rays dates back to the early 20th century, when scientists first noticed mysterious radiation that could not be accounted for by known sources on Earth. In 1916, physicist Victor Hess made a groundbreaking contribution by conducting a series of balloon flights to measure radiation levels at higher altitudes. As he ascended into the atmosphere, he observed that radiation levels increased, providing clear evidence that this radiation was coming from outer space. Hess's work earned him the Nobel Prize in 1930, and cosmic rays became a cornerstone of high-energy astrophysics. Today, cosmic rays are a vital area of research. Scientists continue to study these energetic particles to understand their origins and their effects on Earth. High-energy cosmic rays, especially ultra-high-energy ones, can be traced back to some of the most extreme events in the universe. Supernovae, active galactic nuclei, and gamma-ray bursts are all capable of accelerating particles to velocities that allow them to travel across vast distances, eventually reaching Earth. Understanding cosmic rays helps scientists not only probe the most energetic phenomena in the universe, but also gain insights into the fundamental processes that govern the cosmos. Whether through the study of the CMB or cosmic rays, we are continually uncovering new layers of the universe's hidden story, with each discovery inching us closer to understanding the true nature of reality itself. Cosmic rays, the high-energy particles that traverse the universe at nearly the speed of light, originate from a range of extreme cosmic phenomena such as supernovae, black holes, and neutron stars. These particles, traveling vast distances through space, embody the tremendous energy and chaotic forces that govern the cosmos. At their most fundamental, Cosmic rays are high-energy protons, nuclei of heavier elements, and a variety of other subatomic particles that exist in a highly energetic state. Their journey from distant cosmic origins to Earth's atmosphere adds another layer of complexity to their already mysterious nature. As these particles make their way through space, they undergo a series of transformations and interactions that ultimately make them both a fascinating scientific puzzle and a significant concern for space exploration, technology, and human health. One of the most powerful contributors to cosmic rays are pulsars and magnetars, both types of neutron stars that are among the most extreme and enigmatic objects in the universe. These stellar remnants, the collapsed cores of massive stars, spin rapidly and generate extraordinarily strong magnetic fields. This combination of rotation and intense magnetism allows them to accelerate particles to high energies, some of which reach beyond what we typically encounter on Earth. This accelerative power transforms pulsars and magnetars into efficient cosmic ray factories. As they spin, they send out energetic jets or beams of particles in all directions, many of which are capable of reaching Earth after traveling through the vast expanse of space. But cosmic rays don't simply originate from such high-energy events. Their creation is a complex chain reaction. For instance, when cosmic rays collide with interstellar matter, such as gas clouds, dust, or remnants of dead stars, they produce secondary ultra-high-energy particles. These secondary particles, including muons, neutrinos, and gamma rays, contribute further to the already dynamic and chaotic environment of space. Together, the pulsars, magnetars, supernovae, and other cosmic phenomena form a vast, interconnected web that generates an array of particles, each contributing to the broader mystery of cosmic ray origins. This dynamic backdrop of cosmic rays serves as a gateway to understanding the universe's most violent and energetic processes. Supernovae, the explosive deaths of massive stars, are another leading source of cosmic rays. When a star runs out of nuclear fuel, it can no longer support its own gravity, leading to a catastrophic collapse. This collapse causes an outward shock wave, which expels a tremendous amount of material and energy into space. The shock wave that results is one of the most energetic processes in the universe, and it's within this violent explosion that cosmic rays are born. By studying these particles, scientists gain critical insights into the conditions surrounding dying stars, such as temperature, density, and the types of elements being synthesized during stellar fusion. This information is essential in understanding nucleosynthesis, the process by which new elements are created in the hearts of stars through nuclear fusion. Despite their fascinating origins and their role as messengers from the farthest reaches of the universe, cosmic rays present a significant challenge to technology and human health, particularly in the context of space exploration. When cosmic rays reach Earth's atmosphere, they initiate cascades of secondary particles, which can travel downward into the planet's surface. These cascades form the basis of cosmic ray showers, which are not only of scientific interest, but also pose risks to modern technologies and human life. For astronauts, in particular, cosmic rays represent a serious health concern. High-energy particles have the ability to penetrate spacecraft shielding and even human tissue, leading to radiation exposure that can cause cellular damage. Over long-duration missions, the cumulative effect of this exposure increases the risk of cancer and other serious health problems. As space agencies such as NASA and the European Space Agency push further into the depths of space, especially with missions to Mars and beyond, mitigating this radiation risk is becoming an urgent priority. Researchers are continually developing advanced shielding technologies to protect both astronauts and sensitive equipment from these energetic particles. However, cosmic rays don't only pose risks to humans. They can also interfere with the functioning of electronic systems in spacecraft and satellites. When these particles interact with the materials in circuits, they can cause glitches or, in more severe cases, permanent damage to critical systems. This is particularly concerning for systems essential to the safety and success of space missions, where reliability is of paramount importance. Engineers and scientists must develop technologies that are resilient to the disruptive effects of cosmic rays, ensuring that spacecraft can continue to operate even in the most hostile environments. For long-term space exploration, particularly for missions beyond Earth's magnetic field, cosmic rays represent a significant challenge. Without the protection of Earth's magnetic shield, which deflects many of these particles, astronauts will be exposed to higher doses of radiation. This exposure is even more concerning for deep space missions, where the duration of travel and the lack of readily available shielding pose further risks. Scientists are already exploring solutions for this problem, from advanced radiation shielding to medical countermeasures that could help mitigate the effects of long-term exposure to these particles. It's an area of active research that will ultimately determine how safely humanity can explore the furthest reaches of space. The challenge of understanding cosmic rays is compounded by the difficulties in detecting and analyzing them. Unlike other astronomical phenomena that can be observed directly, cosmic rays are not visible to conventional telescopes. Instead, scientists rely on a network of indirect detection methods, each with its own strengths and limitations. Ground-based particle detectors, for example, are large arrays of sensors spread over vast regions of land. These detectors don't capture cosmic rays directly, but instead record the secondary particles that are produced when cosmic rays collide with the Earth's atmosphere. By analyzing these secondary particles and their energies, researchers can infer the properties of the original cosmic rays, such as their energy, charge, and potential sources. Balloon-borne detectors are another tool used to study cosmic rays. These detectors are carried high into the atmosphere by large balloons, allowing them to measure cosmic rays before they interact with the atmosphere. This setup provides a clearer view of the cosmic ray's energy and composition, but it still faces certain limitations. For example, balloon-borne detectors have a limited operational altitude, and they cannot capture cosmic rays from the higher energies that might be present in the upper reaches of space. In contrast, space-based observatories offer a more direct approach to studying cosmic rays. These observatories are equipped with specialized detectors designed to capture cosmic rays without interference from Earth's atmosphere. By positioning these observatories in orbit around Earth or in other locations beyond the atmosphere, scientists can obtain valuable data on cosmic rays directly from space. Instruments such as neutron detectors and gamma-ray telescopes are particularly valuable in this regard, as they measure neutrons produced by cosmic ray interactions and high-energy photons emitted from cosmic ray collisions with cosmic matter. Neutron detectors and gamma-ray telescopes, along with other sophisticated instrumentation, form a comprehensive network of tools for cosmic ray research. These instruments help scientists build a more complete picture of cosmic rays, their origins, and their interactions with the environments through which they travel. This intricate network of observatories and detectors plays a crucial role in unraveling the mysteries surrounding cosmic rays and their sources, providing valuable insights into the broader workings of the universe. Cosmic rays also provide significant clues about the evolution of galaxies and the life cycles of stars. As these particles travel across the vast distances of space, they interact with the interstellar medium, the matter that exists between stars, such as gas clouds and dust. These interactions can create secondary particles, which provide additional information about the conditions in space and the processes at play. By studying cosmic rays and their interactions, scientists gain a better understanding of galactic evolution, star formation, and the ultimate fate of stars and galaxies. Tracing the origins of cosmic rays is one of the greatest challenges in modern astrophysics. Although we know these particles come from extreme events, such as supernovae or black holes, their path through space is rarely straightforward. As charged particles, cosmic rays are subject to the influence of magnetic fields as they travel, distorting their trajectories. This deflection makes it difficult to trace their origin directly. Additionally, cosmic rays vary greatly in energy, with some having relatively low energy while others have energies so high they challenge the limits of current detection technology. The higher the energy, the rarer the cosmic rays are, making them even harder to study. The deflection caused by magnetic fields, combined with the challenge of collecting data on these high-energy particles, complicates the task of pinpointing their source. The absence of a direct observation method further adds to the complexity. While other astronomical phenomena can be studied by pointing a telescope at them, cosmic rays cannot be observed in such a manner. Instead, scientists must rely on indirect evidence, such as the study of secondary particles produced when cosmic rays collide with Earth's atmosphere. This indirect method requires sophisticated simulations and models to reconstruct the paths these particles may have taken, further complicating the search for cosmic ray origins. Despite these challenges, the study of cosmic rays remains a critical and fascinating field of research. Understanding these high-energy particles not only helps scientists understand the most violent and energetic processes in the universe, but also provides essential insights into the life cycles of stars, the formation of galaxies, and the evolution of the universe itself. By piecing together the data gathered from cosmic ray observatories and detectors, scientists continue to uncover new aspects of the universe, pushing the boundaries of human knowledge and allowing humanity to explore the cosmos in ever more profound ways. Cosmic rays are among the most intriguing and mysterious phenomena in the universe. Traveling through space at nearly the speed of light, these high-energy particles originate from some of the most violent and energetic events in the cosmos. Supernova explosions, the active nuclei of distant galaxies, and even the sun are some of the sources of these cosmic messengers. Their effects, both in our solar system and beyond, are far-reaching and complex, impacting everything from planetary atmospheres to the very processes that shape the development of life. The impact of cosmic rays on biological processes cannot be underestimated. For one, they have the ability to facilitate mutations in living organisms by interacting with DNA. This introduces variations that can ultimately lead to evolutionary changes. While this phenomenon might be of particular interest on Earth, it takes on even greater significance when we consider the conditions on other planets. On worlds with thinner atmospheres or weaker magnetic fields, like Mars or exoplanets in distant star systems, the influence of cosmic rays can be far more pronounced. Without the protective shield of a thick atmosphere or a strong magnetic field, the constant bombardment of cosmic rays can cause significant atmospheric erosion. Over time, this erosion can strip away essential gases, such as carbon dioxide or water vapor, that are crucial for maintaining a stable climate. In the most extreme cases, this could render a planet incapable of supporting life as we know it. Understanding the effects of cosmic rays on planetary environments is a crucial part of the puzzle of planetary evolution. As scientists delve deeper into these energetic particles and their impact on planetary systems, they gain a clearer picture of how interconnected cosmic phenomena are with the processes that govern the development of planets. Cosmic rays are not simply random particles traveling through space. They are integral to shaping the environments of planets, helping to define the boundaries of solar systems and influencing the broader dynamics of our universe. The role of cosmic rays extends far beyond their interactions with planetary environments. They play a critical part in shaping the boundaries of our own solar system. The heliosphere, a vast bubble created by the solar wind, streams of charged particles emitted by the sun, marks the outermost boundary of the solar system. This solar wind interacts with the interstellar medium, the gas and dust that exists between the stars, creating a dynamic interface that is constantly shifting and evolving. Cosmic rays interact with both the solar wind and the interstellar medium, driving complex processes that influence the size, shape, and behavior of the heliosphere over time. As cosmic rays enter the heliosphere, they can ionize particles in the surrounding interstellar medium. This ionization leads to changes in the density and pressure of the surrounding particles. One of the most noticeable effects of these changes occurs at the boundary of the heliosphere, known as the heliopause. This is the point at which the pressure from the solar wind fades and the pressure from the interstellar medium takes over. The presence of cosmic rays at the heliopause may play a significant role in regulating the balance of forces at this critical boundary. In a way, cosmic rays help to shape and maintain the very structure of our solar system. Cosmic rays are also involved in creating secondary particles when they collide with particles in the solar atmosphere and the interstellar medium. This cascade effect can amplify the intensity of cosmic rays within the heliosphere, increasing their influence on space weather and, consequently, how the planets within our solar system interact with solar radiation. Thus, cosmic rays act as vital players in the cosmic ecosystem, helping to define the interface between our solar system and the vast, unexplored regions of space beyond. Their significance is not limited to planetary systems. The study of cosmic rays opens up exciting avenues for future research in astrophysics. These energetic particles can provide valuable insights into the most extreme and energetic environments in the universe, such as the aftermath of supernova explosions or the powerful radiation around black holes. Cosmic rays offer a unique way to probe the underlying energy processes in these colossal events. As researchers continue to study the behavior of cosmic rays, they may uncover crucial information about the conditions required for matter and energy to coexist at such high energy levels. Moreover, cosmic rays may hold the key to understanding some of the most elusive and mysterious components of the universe: dark matter and dark energy. Although these substances remain hidden from direct observation, cosmic rays may interact with them in ways that provide indirect evidence of their existence. By examining how cosmic rays behave in different regions of the universe, scientists may gather valuable clues that point to the presence and characteristics of these invisible forces. Advancements in technology are also helping to expand our ability to detect, track, and analyze cosmic rays. As observational tools and experimental methods improve, researchers will be able to monitor cosmic rays across greater distances and with unprecedented precision. Projects designed to study cosmic rays in detail, such as large-scale observatories and experiments, promise to unlock new discoveries that could reshape our understanding of the universe. These advancements could provide valuable data on the origins, spectrum, and flux of cosmic rays, offering new insights into the forces and processes that govern the dynamics of our universe. In conclusion, the future of cosmic ray research holds the potential to dramatically alter our understanding of astrophysics. By answering fundamental questions about the formation, composition, and forces at play in the universe, this research could reveal the hidden mechanisms that drive the evolution of the cosmos. As we continue to study these fast-moving particles, we may unlock the secrets of the universe itself, gaining a deeper understanding of our place in the vast expanse of space. One area of scientific inquiry that has long fascinated humanity is the search for life beyond Earth. Driven by the quest to understand whether we are alone in the universe, researchers and space agencies around the world are focused on several key priorities. These priorities are guiding their efforts to identify environments where life might exist, to explore new worlds, and to unravel the mysteries of the cosmos in search of extraterrestrial life. At the heart of this search is the identification of potentially habitable environments beyond Earth. This involves looking for planets and moons that possess the essential conditions for life as we know it: liquid water, the necessary chemical building blocks, and a temperature range that supports biological processes. The search for such environments is a monumental task, but one that holds the promise of incredible discoveries. Among the most promising candidates is Mars, the red planet. Long believed to have once harbored flowing water on its surface, Mars has long been a focal point for the search for microbial life. Robotic missions, such as the rovers currently exploring the Martian soil and atmosphere, are tasked with searching for signs of past or present life. This includes looking for organic molecules, which are the fundamental building blocks of life. Another key area of interest in the search for extraterrestrial life lies within the icy moons of our solar system. Moons like Europa, Enceladus, and Ganymede are thought to harbor subsurface oceans beneath their icy surfaces. These hidden seas could provide the right conditions for life to thrive, protected from the harsh environment on the surface. By analyzing the plumes of water vapor expelled from these moons, or by planning future missions to land on them, scientists hope to uncover the potential for life in these frozen, distant worlds. Beyond our solar system, astronomers are focused on scanning distant exoplanets for signs that they may harbor life. Exoplanets are planets that exist outside our solar system, and they are often discovered through the technique of measuring the light that passes through a planet's atmosphere during a transit. By analyzing this light, scientists can identify the presence of organic molecules or gases that might indicate biological activity. The detection of gases like oxygen or methane, which are byproducts of biological processes, could offer compelling evidence that life exists or once existed on distant worlds. As technology continues to improve, so too do the methods for detecting potential signs of life. Programs like the Search for Extraterrestrial Intelligence, SETI, are actively pursuing the goal of detecting signals or other signs of advanced civilizations within our galaxy. These efforts are part of a broader strategy to scan the vastness of the cosmos for any hint that we are not alone. The search for extraterrestrial life also involves studying extremophiles, organisms that thrive in extreme environments on Earth. By understanding how these organisms survive in conditions once thought to be inhospitable, scientists are broadening their definition of what life could be. This knowledge is crucial in expanding our search for life to include environments that we might otherwise overlook. In addition to searching for life in the familiar environments of Mars and icy moons, researchers are also working to expand our understanding of the factors that make a planet habitable. The search for potentially habitable exoplanets is guided by several key factors. First and foremost, scientists look for planets located in what is known as the habitable zone. This is the region around a star where the temperature is just right to allow liquid water to exist on a planet's surface. Liquid water is considered the essential ingredient for life as we know it, making the habitable zone a crucial area of focus in the search for extraterrestrial life. However, the search for habitable planets goes beyond simply identifying those located in the habitable zone. Scientists also consider other factors that might make a planet more or less suitable for life, such as the presence of a stable atmosphere, the chemical composition of the planet's surface, and its ability to support long-term ecological systems. This broader view of habitability allows researchers to refine their search and focus on those planets that are most likely to support life, increasing the chances of finding extraterrestrial life in the vast expanse of the universe. In the end, the search for life beyond Earth is one of humanity's greatest scientific endeavors. The progress made in understanding the conditions that support life, as well as the advances in technology that enable us to study distant worlds, will shape the future of this field. The discoveries made in the coming decades could change our understanding of life itself and our place in the cosmos, offering profound insights into the nature of existence and the potential for life beyond Earth. When scientists study distant planets, one of the key factors they consider is the planet's position relative to its star. This is often referred to as the habitable zone or Goldilocks zone, an area where conditions might allow for liquid water to exist on the planet's surface. If a planet is too close to its star, the heat could be intense, causing any water on the planet to evaporate into vapor, rendering life as we understand it impossible. On the other hand, if the planet is too far away, the temperature could plunge, causing water to freeze and ice to dominate the environment, effectively ending any chance for life to thrive. This delicate balance between too hot and too cold is crucial when scientists search for planets that could potentially harbor life. Beyond just the distance, scientists also examine the size and composition of a planet to determine whether it could sustain life. Typically, planets that are similar in size to Earth are considered the best candidates. If a planet is much larger than Earth, it might have a dense atmosphere, potentially creating crushing pressure on any life forms that might attempt to live there. Smaller planets, on the other hand, may not have the gravity necessary to retain an atmosphere, which is crucial for protecting life and maintaining stable weather systems. Without an atmosphere, temperatures would swing wildly, making survival difficult, if not impossible. Therefore, a planet's size, composition, and gravitational pull play a significant role in determining whether it could support life. Another critical factor is the planet's atmosphere. The composition of the atmosphere can reveal vital clues about the planet's ability to support life. A thick atmosphere, for instance, could help regulate temperature and provide protection from harmful solar radiation, which would otherwise strip away any potential for life. Weather patterns, which rely on atmospheric conditions, could also be supported by a stable atmosphere. Understanding these elements is essential when searching for exoplanets that could harbor life. To identify these potentially life-sustaining planets, scientists rely on advanced telescopes and a variety of high-tech tools. One of the primary methods used is the transit method. This technique involves observing distant stars for slight dimming when a planet passes in front of them. The planet blocks a small portion of the star's light, creating a measurable dip in brightness. By analyzing this dimming, scientists can determine the size of the planet, its orbital period, and its distance from the star. This information is crucial for narrowing down which planets are in the habitable zone and might have the right conditions for life. Another widely used technique is the radial velocity method, which measures the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. These subtle movements can reveal important data about the planet's mass, orbit, and distance from its star. By using both the transit method and the radial velocity method, scientists can gain a more complete picture of the planet, confirming its existence and learning more about its properties. However, it's important to remember that just because a planet is located in the habitable zone does not guarantee that it has life. It simply means that the conditions on the planet are right for life to potentially exist. This is a critical distinction in the search for exoplanets, as it reminds scientists that finding a habitable zone is only the beginning of the journey to determine whether life actually exists there. The process of finding extraterrestrial life is a long, ongoing quest, and each discovery raises new questions about what life might look like elsewhere in the universe. Astrobiology, the study of life in the universe, plays a central role in this search. Astrobiologists aim to understand not only the conditions that could support life, but also the signs that might indicate its presence. This interdisciplinary field explores a wide range of environments, from the extreme conditions on Earth, such as deep-sea vents and polar ice caps, to the frozen moons of distant planets, to understand how life could exist in places previously thought inhospitable. Astrobiology is not just about finding life. It's about expanding our understanding of what life is and how it might evolve under a variety of circumstances. One of the most significant aspects of astrobiology is the search for biosignatures. These are indicators that suggest the presence of life, either past or present. Biosignatures can take many forms, such as specific gases in a planet's atmosphere, unusual chemical patterns, or even complex organic molecules. For instance, gases like oxygen and methane are often associated with biological activity, as these substances are typically produced by living organisms. If a planet's atmosphere contains large amounts of these gases, it could be a sign that life is present, or at least was once present. To detect biosignatures, scientists use powerful telescopes that can analyze the light emitted by distant planets and moons. These instruments are capable of breaking down the light into its component wavelengths, allowing scientists to identify the chemical ingredients in the planet's atmosphere. If the combination of gases in the atmosphere suggests biological processes, it increases the likelihood that life could exist or have existed on that planet. The search for biosignatures is one of the most exciting aspects of astrobiology because it provides concrete evidence that we are not alone in the universe. In addition to looking for biosignatures, astrobiologists also use models to predict where life might be found based on what is known about life on Earth. They take into account factors like temperature, the availability of water, and the presence of essential elements like carbon and nitrogen. By understanding how life thrives under different conditions, scientists can refine their search for signs of life in the universe. This predictive modeling is essential for focusing their efforts on the most promising candidates. While the search for life beyond Earth is still in its early stages, advances in technology are rapidly improving our ability to observe distant planets. Missions like Kepler and TESS, Transiting Exoplanet Survey Satellite, have revolutionized our understanding of exoplanets. Before these missions, the search for exoplanets was like finding a needle in a haystack. The methods available were limited, and many discoveries were based on serendipitous observations. However, Kepler, launched in 2009, focused on a specific area of the sky, monitoring it continuously over a long period of time. Using the transit method, Kepler was able to detect the slight dimming of stars caused by planets passing in front of them. Through this method, Kepler discovered thousands of exoplanets, revealing that planetary systems are common around stars. Building on the success of Kepler, TESS was launched in 2018 with a broader mission. Unlike Kepler, which focused on a small patch of the sky, TESS was designed to observe nearly the entire sky over a 2-year period. TESS's primary goal is to identify nearby stars that have planets orbiting them, particularly those that are easier to study in more detail. One of the key aims of TESS is to find smaller Earth-like planets in the habitable zone where conditions might be suitable for life. By focusing on nearby stars, TESS has significantly enhanced our ability to study exoplanets and gather more information about their potential for life. These two missions, Kepler and TESS, have transformed our understanding of the diversity of planets in the universe. We now know that planets come in many different sizes, compositions, and distances from their stars. This has opened up new possibilities for finding planets that could harbor life and has raised new questions about the nature of life on other worlds. While these missions have expanded our catalog of exoplanets, they have also spurred deeper inquiry into the potential for life beyond Earth. The quest to discover life on other planets is not just about finding evidence of microbial organisms or alien life forms. The discovery of simple life, such as bacteria or microorganisms, would have profound implications. It would suggest that the ingredients for life are widespread in the universe, and that life can emerge in a variety of environments, including those previously thought inhospitable. This discovery would spark a wave of scientific exploration, pushing humanity to explore further and look for more complex forms of life on moons and planets that may already harbor simpler organisms. In contrast, the discovery of intelligent life would have even more profound consequences. Finding evidence of advanced civilizations would indicate that intelligent life is not only possible, but may be more widespread in the universe than we ever imagined. Such a discovery would challenge our understanding of humanity's place in the cosmos and provoke deep philosophical questions about our role in the universe. It would lead to a reevaluation of our technological capabilities, our ethics, and our way of life. The possibility of communicating with an intelligent alien civilization would open up vast opportunities for cultural exchange and knowledge sharing, potentially accelerating our own progress in science and technology. The search for extraterrestrial life is one of the most exciting frontiers in science. As technology advances and our ability to observe distant planets improves, the dream of finding life beyond Earth becomes more achievable. Whether we discover simple microorganisms or intelligent civilizations, the implications of such a discovery would fundamentally reshape our understanding of life itself and our place in the universe. The journey is just beginning, and every new finding brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? The discovery of extraterrestrial life has captivated the human imagination for centuries. It raises profound questions about our existence, the nature of life, and the fundamental structure of the universe. At its core, the search for life beyond Earth challenges the assumptions we hold about our uniqueness as a species and our place in the cosmos. However, such a discovery would not come without its complexities. It would spark debates about the implications of interacting with more advanced civilizations and provoke concerns about safety, ethics, and the potential consequences of contact with extraterrestrial intelligence. In this context, the question of whether we are alone in the universe isn't just a scientific inquiry. It touches on deeply philosophical and existential issues that could reshape humanity's worldview forever. The quest to understand the likelihood of finding intelligent life elsewhere in the universe is not a recent endeavor. One of the most influential frameworks for addressing this question is the Drake equation. Created in the early 1960s by the American astrophysicist Frank Drake, the equation was designed as a tool to stimulate scientific discussion about extraterrestrial life. It provides a way of estimating the number of technologically advanced civilizations in our galaxy that might be capable of communicating with us. The equation is built on a series of variables that attempt to quantify the vast uncertainties involved in the search for alien life. Imagine for a moment standing at the edge of an immense forest, each tree representing a star in our galaxy, and each branch housing the potential for life to take root. The Drake equation begins with one fundamental question. How many stars are being born in our galaxy? The rate of star formation is crucial because new stars may host planets in their habitable zones, the regions where conditions might be just right for life. The creation of these stars, in turn, increases the possibility of planets that could harbor life, given that stars form not just in isolation, but with planetary systems. It is this celestial birthing process that sets the stage for the subsequent factors considered in the equation. Next, the equation considers the fraction of stars that have planets orbiting them. With the discovery of thousands of exoplanets in recent decades, we now know that planets are abundant in the universe. Given that our galaxy, the Milky Way, is estimated to contain around 100 billion stars, it follows that a substantial fraction of these stars might also host planets, many of which could have conditions suitable for life. This brings us to the next factor in the equation, the fraction of those planets that could support life. Not all planets are born equal. The conditions required for life are specific and demanding. A planet must be within the habitable zone of its star, where temperatures are moderate enough to allow for liquid water, a crucial ingredient for life as we know it. Additionally, the planet must have other essential ingredients, such as a stable atmosphere and a suitable chemical composition. The presence of water, in particular, has become a cornerstone of astrobiological studies. Scientists now recognize that liquid water may not only exist on Earth-like planets, but also on moons and other celestial bodies in our solar system and beyond. But even if a planet is situated within the habitable zone and has the necessary conditions for life, there is no guarantee that life will arise. The next part of the Drake equation asks, what is the probability that life will actually develop on a given planet? Earth is, as far as we know, the only example of a planet where life has emerged. However, scientists have speculated about various pathways through which life could take root, ranging from simple microbial organisms to complex multicellular life forms. While the specific mechanisms of life's emergence remain elusive, the study of extreme environments on Earth has provided critical clues about the resilience and adaptability of life. Some of the most fascinating discoveries in recent years have come from the study of extremophiles, organisms that thrive in the most hostile environments on Earth. From boiling hot springs to deep-sea hydrothermal vents, these resilient organisms have shown that life can persist in environments once thought to be inhospitable. This discovery has expanded our definition of habitable zones to include not just temperate environments, but also the extreme conditions found on other planets and moons. If life can survive under conditions of extreme heat, radiation, or pressure here on Earth, it stands to reason that similar life forms could exist on other celestial bodies with comparable environments, such as the icy moons of Jupiter and Saturn, Europa, and Enceladus, which are believed to harbor subsurface oceans beneath their frozen crusts. The next stage in the Drake equation examines the fraction of planets where life evolves to become intelligent. While Earth is home to advanced civilizations capable of communication, this is by no means a guarantee for all planets. Evolution is a random, contingent process, and intelligence may not be a necessary outcome of life's development. Some life forms may never develop the cognitive capabilities required for communication or technological advancement. Thus, the equation attempts to quantify this fraction, the likelihood that life on a given planet will evolve into intelligent beings capable of sending signals into space. Finally, the equation considers the lifespan of these civilizations. Even if an intelligent species does emerge and develop the technology to communicate, there remains the question of whether they will still be around long enough for us to detect them. Civilizations may rise and fall, their technologies disappearing as quickly as they emerged, and it is possible that other intelligent civilizations are too distant in both space and time for us to make contact. The lifespan of any given civilization is influenced by countless factors, political, environmental, and technological, that are difficult to predict. Taken together, these factors create an estimate of how many civilizations might currently exist in our galaxy that are capable of sending signals. While the Drake equation provides a framework for understanding the potential for extraterrestrial life, it is important to note that the equation is based on a series of assumptions that are, at best, educated guesses. The true number of extraterrestrial civilizations is, as of now, unknowable. Nonetheless, the equation offers a valuable tool for focusing our efforts in the search for life beyond Earth and invites continued scientific inquiry. In the pursuit of discovering alien life, technological advancements have played a significant role. One of the most important developments has been the construction of increasingly powerful telescopes. These instruments have enabled astronomers to peer deeper into space and observe distant stars and planets in greater detail than ever before. With these telescopes, scientists are able to study the chemical composition of exoplanet atmospheres, looking for signs of life, such as the presence of oxygen or methane. These gases are often associated with biological processes, and their discovery on distant worlds could serve as a compelling indicator that life exists elsewhere in the universe. Moreover, space exploration technologies have advanced in leaps and bounds, allowing us to send robotic probes farther into the solar system than ever before. Missions to Mars have provided tantalizing evidence that the planet may have once harbored conditions suitable for life. Similarly, probes sent to the icy moons of Jupiter and Saturn are investigating the possibility that subsurface oceans on these moons could harbor microbial life. These explorations are gradually extending the boundaries of our understanding and may one day uncover evidence of alien life. Artificial intelligence, AI, has also become an invaluable tool in the search for extraterrestrial life. AI systems can analyze vast amounts of data from telescopes, space probes, and other sources, identifying patterns and anomalies that might suggest the presence of alien signals. These AI algorithms can sift through large volumes of information much faster than humans, making it possible to detect subtle clues that might otherwise be overlooked. Additionally, the rise of nanotechnology has allowed for the creation of highly sensitive detection tools, enabling the exploration of biological markers at incredibly small scales. These tools could one day help identify even the simplest forms of life or detect specific biosignatures that might indicate the presence of extraterrestrial life. Finally, the trend of global collaboration in scientific research is helping to accelerate the search for life beyond Earth. Researchers from around the world are sharing data, insights, and resources, working together in a concerted effort to solve the mystery of whether we are alone in the universe. Collaborative databases, which allow scientists to pool their knowledge and findings, are enhancing our ability to make significant breakthroughs in the search for alien life. While the pursuit of extraterrestrial life has made tremendous strides, the discovery of intelligent alien civilizations would have profound implications for humanity, far beyond the scientific. Such a discovery would not only challenge our understanding of biology and the cosmos, but also shake the very foundations of our philosophical, ethical, and religious beliefs. Philosophically, the recognition of intelligent extraterrestrial life would force us to re-examine fundamental concepts such as consciousness, morality, and existence. It would raise questions about the nature of intelligence and sentience. Would these alien beings have the same rights as humans? Would our ethical frameworks developed over millennia be sufficient to guide our interactions with these new forms of life? The implications for human morality and ethics would be profound, potentially forcing us to redefine the very nature of sentience and rights in the context of a much larger and more complex universe. Religiously, the discovery of extraterrestrial life could challenge many traditional narratives about humanity's place in the universe. Many religions place humans at the center of creation, interpreting the Bible, the Quran, and other sacred texts as indicating that humanity is uniquely chosen by God. The discovery of intelligent alien civilizations might be seen by some as evidence of the vastness and complexity of divine creation, affirming the belief in a creator whose reach extends far beyond Earth. Others, however, might struggle with the idea of extraterrestrial life, viewing it as incompatible with their religious teachings. The theological dilemmas this would create concerning salvation, the nature of God, and humanity's place in the grand cosmic order could be profound and far-reaching. In the end, the search for extraterrestrial life is not just a scientific endeavor. It is a quest that touches on the deepest questions of existence, morality, and meaning. As we continue to explore the cosmos, we are not only seeking answers about the universe, but also about ourselves, our origins, our future, and our place in the vast, mysterious expanse of space. Across cultures, the understanding of life and existence has been shaped by centuries of philosophical debate, religious doctrine, and scientific inquiry. For some, the prospect of discovering extraterrestrial life would enhance and deepen their spiritual beliefs, offering new perspectives on the nature of existence and our place within the vast cosmos. To others, however, such a discovery might ignite fear or provoke an existential crisis, leaving humanity to confront the question of its significance in an infinite universe. This search, at its core, is not merely a scientific endeavor, but a profound journey that touches on the very essence of what it means to be human. It compels us to examine our values, our beliefs, and our self-understanding. The quest for extraterrestrial life challenges us to broaden our horizons and reconsider what it truly means to share the universe with other forms of intelligent existence. The mere discovery of alien life could catalyze profound shifts in society, affecting various aspects of human life, from culture and religion to science and economy. Imagine the tidal wave of excitement and wonder that would ripple through the world as we come to terms with the realization that we are not alone in the universe. Such a discovery would likely unite humanity in a shared sense of curiosity and awe, sparking conversations, debates, and collaborations across borders, cultures, and disciplines. However, it would also come with an equal measure of concern, as many would grapple with the fundamental question, what does it mean to be human in a universe inhabited by other intelligent beings? On a scientific level, the discovery of extraterrestrial life forms would undoubtedly trigger an unprecedented surge in research and exploration. Scientists, driven by the desire to understand the biology, physiology, and possible technologies of these life forms, would embark on a new era of discovery. Every detail of their biology and behavior, from their physical makeup to the environments they inhabit, would become a subject of intense scrutiny. This could lead to the birth of entirely new branches of study, revolutionizing our understanding of life itself. Concepts that we once considered unique to Earth, such as intelligence, consciousness, and evolution, might take on entirely new meanings when placed in the context of alien life forms. Moreover, this discovery could usher in a wave of technological and medical breakthroughs. The biological systems of extraterrestrial beings, shaped by entirely different environmental pressures, could offer insights into new ways of thinking about medicine, health, and technology. Just as the study of extremophiles, organisms that thrive in extreme conditions on Earth, has led to advances in biotechnology and medicine, so too might extraterrestrial life reveal secrets that could transform our own technologies. Imagine the possibilities of harnessing new forms of energy or learning new ways to cure diseases based on alien biology. The potential for innovation would be limitless. Culturally and religiously, the discovery of extraterrestrial life would force societies to reevaluate long-held beliefs and traditions. Many religious doctrines teach that humanity holds a special place in the universe, often positioned as the pinnacle of creation. The existence of other intelligent life forms could challenge or even undermine these teachings, leading to reinterpretations of sacred texts and spiritual philosophies. Some religious traditions might see this discovery as a validation of their teachings, suggesting that life exists elsewhere as part of a grand cosmic design. Others, however, might struggle to reconcile the existence of extraterrestrial beings with their worldview, leading to theological debates and new interpretations of ancient texts. Economically, the impact of such a discovery would be profound. Industries related to space exploration, technology, and communication would experience significant growth. New markets could emerge, focused on everything from establishing contact with alien civilizations to traveling to distant planets. Space tourism, previously a niche industry, might transform into a mainstream endeavor as humanity begins to explore the universe in earnest. The scientific community, too, would receive an influx of funding as governments and private organizations recognize the importance of understanding the broader universe and our place within it. New fields of research and new technologies would emerge, transforming the global economy in ways we can only begin to imagine. However, as with any groundbreaking discovery, the question of ethics would inevitably arise. The discovery of intelligent extraterrestrial beings would prompt profound questions about how we should treat them. Should they be afforded the same rights and protections as human beings? What moral responsibilities do we have toward them, especially if they possess emotions, consciousness, and intelligence comparable to our own? These ethical questions would force humanity to reconsider its moral frameworks, not just in relation to each other, but in relation to all life, whether on Earth or beyond. How we respond to extraterrestrial life could reshape our understanding of morality, justice, and compassion, redefining our responsibilities toward life in all its forms. Ultimately, the discovery of extraterrestrial life could change the fabric of human society in ways we can scarcely predict. It would force us to redefine our role within the cosmos and examine our place in a universe that may be teeming with life. This journey would not only be about expanding our scientific knowledge, but also about expanding our consciousness and understanding of what it means to exist in an infinite, interconnected universe. In the search for extraterrestrial life, one of the most intriguing phenomena encountered by scientists is the mysterious fast radio bursts, or FRBs. These intense and brief flashes of radio waves, which last just a fraction of a second, have puzzled astronomers since their discovery in 2007. Despite their brief duration, these bursts release an astonishing amount of energy that, in a single millisecond, can surpass what our sun emits over the course of several years. Their origins remain largely unknown, sparking numerous theories and hypotheses about what might be causing these enigmatic signals. Some scientists have speculated that FRBs might be the result of rapidly rotating neutron stars, also known as pulsars. These dense, compact remnants of massive stars could potentially emit powerful bursts of radiation as they rotate. Others have proposed even more exotic possibilities, such as the merging of black holes or other catastrophic astrophysical events. Still, there is no consensus on the true cause of FRBs, and some researchers have even entertained the idea that these bursts might be evidence of advanced extraterrestrial technologies, though this remains a highly speculative theory. The first detection of an FRB occurred in 2007 when astronomers recorded an intense pulse of radio waves that appeared to originate from outside our galaxy. At first, the discovery was met with confusion, as the bursts seemed erratic and difficult to trace. Yet, as technology improved and observational data accumulated, scientists began to identify more of these fleeting signals. The continued detection of FRBs has only deepened the mystery, presenting a challenge to our understanding of the universe. FRBs have captured the attention of researchers not only because of their mysterious origins, but also because of their potential to reveal important secrets about the cosmos. The way in which these radio waves travel through space can offer valuable insights into the nature of the universe's intergalactic medium, the diffuse matter that exists between galaxies. By studying the effects that FRBs have as they traverse this vast expanse, scientists can learn more about the composition, density, and structure of the universe on a large scale. These bursts, which travel across billions of light years, provide a unique lens through which we can observe the fundamental properties of the universe itself. In addition to their scientific significance, the study of FRBs also raises philosophical questions about the nature of the cosmos and the possibility of extraterrestrial life. The fact that these bursts can traverse such immense distances suggests that the universe is far more complex and interconnected than we might have previously imagined. Could these signals be a clue to the existence of intelligent life elsewhere in the universe? Or are they the result of natural phenomena that we have yet to fully understand? Regardless of their origin, fast radio bursts serve as a reminder of the many mysteries that still lie hidden in the vast expanse of space, waiting to be uncovered. As the search for answers continues, one thing is clear. The study of FRBs, along with the broader search for extraterrestrial life, has the potential to reshape our understanding of the universe and our place within it. Every new discovery brings us one step closer to answering the most profound question humanity has ever asked. Are we alone in the universe? And if we are not, what does that mean for our future as a species? The cosmic phenomena known as fast radio bursts, or FRBs, are among the most captivating and enigmatic occurrences observed in the universe. Their unpredictability only enhances their allure, as they seem to appear without warning, exhibiting an almost chaotic randomness that defies our understanding of cosmic behavior. This inherent unpredictability, coupled with their sudden and intense bursts of energy, presents a challenge that astronomers are eager to tackle. Each fleeting burst, lasting mere milliseconds before vanishing without a trace, holds the potential to unlock secrets about the fundamental workings of the universe. The mystery of FRBs is not just a puzzle, but represents an exciting frontier in astrophysics, where each new discovery serves as a small yet significant piece in the ever-growing puzzle of understanding the cosmos. These bursts, seemingly so brief and elusive, could hold the key to unveiling new physics or uncovering previously unknown cosmic mechanisms, making them not only fascinating phenomena, but also pivotal to unraveling deeper cosmic mysteries. At their core, FRBs are brief, powerful radio wave emissions that have baffled scientists ever since their discovery. Their origins remain a subject of intense debate, with a variety of theories proposed to explain these strange bursts of energy. Some of the leading hypotheses suggest that FRBs could be connected to magnetars, a type of neutron star with an extraordinarily strong magnetic field. Picture a star that has collapsed under immense gravitational pressure, spinning at an incredibly fast rate. In such a scenario, the star's magnetic field is amplified beyond our imagination, creating conditions where sudden magnetic shifts could result in the release of vast amounts of energy, potentially manifesting as an FRB. This idea draws on our current understanding of magnetars, which are already known to produce other high-energy emissions, and adds a layer of intrigue to their role in the cosmic landscape. Another prominent theory suggests that FRBs could arise from the cataclysmic collisions of compact objects, such as neutron stars merging with each other, or even from the interactions between black holes and neutron stars. These violent events generate powerful shockwaves, the likes of which could create the right conditions for the rapid bursts of radio waves that we observe as FRBs. The sheer scale of energy involved in such collisions makes it plausible that these events could produce the intense, fleeting bursts that characterize FRBs. In fact, some researchers have proposed that these mergers could also explain the broader phenomena associated with gravitational waves, further suggesting a connection between these extreme cosmic events and the bursts of radio waves that we detect from afar. While magnetars and cosmic collisions are among the most widely accepted explanations, other hypotheses explore even more exotic scenarios. Some researchers have ventured into the possibility that FRBs could be the result of supernova explosions, the violent deaths of massive stars. As these stars explode, ejecting material at extraordinary speeds, they may produce powerful radio emissions in the process. In this case, the FRBs would represent a brief but intense burst of energy released during the explosive event. The violent nature of supernovae, combined with the complex interactions of stellar material, provides a potential explanation for the high-energy signals we observe. In a more speculative domain, there have even been suggestions that FRBs could have technological origins potentially emitted by advanced extraterrestrial civilizations. While this theory remains far from widely accepted in the scientific community, it does open an intriguing dialogue about the possibility of life beyond Earth. Could these bursts be intentional signals designed by intelligent beings to communicate across vast interstellar distances? While this idea remains speculative and unproven, it touches on the broader question of whether humanity is truly alone in the cosmos and serves as a reminder of the vast unknowns that still lie beyond our current understanding. Overall, the diverse range of possible sources for FRBs underscores the complexity and richness of our evolving understanding of the universe. As new technologies and observational methods come online, we may be closer than ever to unraveling the mystery of these elusive bursts. The advent of more powerful telescopes, such as the Canadian Hydrogen Intensity Mapping Experiment, CHIME, has revolutionized the way scientists study FRBs, offering new insights into the phenomena that were once beyond our reach. The CHIME telescope, in particular, has proven to be a game changer in the study of FRBs. Unlike traditional telescopes, which often relied on manual tracking and were limited in their field of view, CHIME operates as an innovative wide-field radio telescope that continuously monitors a vast portion of the sky. Imagine trying to find a single twinkling star in the night sky with a small flashlight. It's a daunting task. Now, picture using a massive floodlight to illuminate the entire sky at once, giving you a much broader view. This is how CHIME works. By continuously scanning the sky and capturing data from multiple sources simultaneously, CHIME is able to detect FRBs that might otherwise go unnoticed. This wide-field design has proven invaluable in increasing the detection rate of FRBs. Since these bursts are fleeting, lasting only milliseconds before fading away, many would be missed by traditional telescopes. CHIME, however, captures thousands of these bursts daily, providing an unprecedented volume of data for scientists to analyze. In addition to detecting the bursts, CHIME also helps researchers better understand their origins and frequency patterns. By examining how the radio waves spread across different frequencies, scientists can infer the density and composition of the cosmic material the bursts pass through, offering valuable clues about the environments in which these bursts originate. Moreover, CHIME doesn't just passively observe these events. It plays an active role in advancing our understanding of FRBs. As soon as the telescope detects a burst, it quickly determines its position in the sky and sends out alerts to other observatories around the world. This enables scientists to follow up with observations across different wavelengths of light, allowing for a more comprehensive study of the objects that produce the bursts. By coordinating efforts across multiple observatories and wavelengths, CHIME is helping to unravel the mystery of FRBs, one discovery at a time. Fast radio bursts, in all their mystery and unpredictability, represent one of the most exciting and challenging phenomena in modern astrophysics. Their brief yet intense nature makes them incredibly difficult to study, and classifying them remains a significant challenge for astronomers. However, advancements in data processing and analytical techniques are helping scientists to make sense of the vast amounts of information collected from radio telescopes. Traditional methods of data analysis, which often relied on manual sorting and interpretation, have been replaced by powerful algorithms capable of sifting through enormous data sets with incredible speed and precision. Machine learning, in particular, has emerged as a valuable tool in the search for new FRBs. By training algorithms on known FRB signals, researchers can create systems that can detect new bursts with remarkable accuracy. These machine learning models are able to recognize the unique characteristics of FRBs, such as their frequency patterns and duration, and can do so much faster than any human could. This allows astronomers to focus less on filtering through data and more on analyzing the properties and potential implications of the bursts. The increase in computing power has also made it possible for astronomers to process data in real time, rather than waiting days or weeks to analyze collected information. This represents a significant leap forward in the field, as it allows scientists to receive near instantaneous insights into new FRBs as they are detected. It's akin to turning on a light in a dark room and immediately seeing everything around you, rather than fumbling around in the dark, unsure of what you might discover. These advancements in data handling and processing are accelerating our ability to study FRBs and deepen our understanding of these mysterious phenomena. In the end, fast radio bursts are not just intriguing anomalies that momentarily disrupt the quiet expanse of space. They are vital pieces of a much larger cosmic puzzle, one that, when solved, could reveal groundbreaking insights into the fundamental processes of the universe. Whether they are the result of exotic stellar phenomena, cosmic collisions, or even extraterrestrial intelligence, FRBs serve as a reminder of how much we still have to learn about the vast and mysterious universe that surrounds us. As new technologies and collaborative efforts continue to evolve, we may be closer than ever to unlocking the true nature of these remarkable cosmic signals. Fast radio bursts, often referred to simply as FRBs, have become one of the most captivating and puzzling phenomena in modern astrophysics. These brief but incredibly powerful bursts of radio waves originate from distant corners of the universe, and their discovery has ignited a wave of intense scientific inquiry. The allure of FRBs lies not only in their mysterious nature, but also in the vast potential they hold to unlock secrets about parts of the universe that we have yet to explore. These flashes of energy last mere milliseconds, yet in that fleeting moment, they can release as much energy as the sun will emit over the course of several years. Their sudden appearance, intense power, and short duration have sparked significant investigation into their origins, their behavior, and their potential to shed light on the most fundamental aspects of the cosmos. As the study of FRBs advances, we are now seeing more sophisticated methods and tools being employed to understand these enigmatic signals. One of the key advancements in this research lies in imaging techniques and data processing capabilities. Researchers are increasingly relying on advanced algorithms and data analysis tools to create detailed maps of the sky. These maps not only highlight the locations from which FRBs are emitted, but also give us an indication of how often these bursts appear and where they are likely to originate. This new approach allows scientists to refine their understanding of the possible sources of FRBs and opens up the potential for further discoveries about the types of cosmic events that might produce them. Through the application of these imaging techniques, the classification of FRBs is becoming more accurate and systematic, which is a crucial step in decoding their true nature. In this context, these advanced data handling methods are not just helping researchers classify the bursts, they're also acting as a gateway to unravel the broader mystery surrounding these fleeting yet incredibly powerful signals. By analyzing the patterns in which FRBs occur, and by identifying the signals with increasing precision, we are inching closer to understanding their origins, the types of environments in which they arise, and the cosmic processes that generate them. The more we learn about FRBs, the clearer it becomes that they are not just isolated incidents or random signals. In fact, the patterns of their occurrence can give us valuable insights into the broader structure of the universe. For instance, the way these bursts are scattered as they travel across space can reveal information about the medium they pass through, such as gas and dust. This scattering phenomenon can provide crucial clues about the density, composition, and overall structure of the surrounding cosmic environment. Moreover, these bursts can even indicate the presence of previously undetected cosmic objects, such as untamed galaxies or stellar remnants, which might otherwise go unnoticed by conventional observation methods. As researchers delve deeper into the study of FRBs, they have also discovered that some of these bursts appear to repeat. This discovery has been particularly exciting, as it suggests that the sources of certain FRBs might not be random, but rather originate from specific identifiable sources. By tracking down these sources, scientists are beginning to explore the extreme environments in which these bursts occur. Some of these environments may include areas with intense gravitational fields, regions with strong magnetic activity, or even dense stellar clusters where multiple stars and other cosmic objects interact in unpredictable ways. These findings hint at the possibility of cosmic phenomena that we are currently unable to fully comprehend, pushing the boundaries of our understanding of the universe. Furthermore, the study of FRBs is providing new opportunities to refine our models of the universe's evolution, particularly with regard to the enigmatic components known as dark matter and dark energy. These two elusive substances are thought to make up the majority of the universe's mass and energy, yet they remain poorly understood. FRBs, by virtue of their ability to pass through vast stretches of space, may provide valuable data that could help scientists better map the distribution of dark matter and dark energy across the cosmos. By studying the way these bursts interact with various cosmic materials and structures, researchers hope to uncover new insights into the nature of these mysterious forces that influence the very fabric of the universe. The process of studying FRBs has also led to technological innovations that are transforming the way we approach the exploration of deep space. To decode the signals from these fast radio bursts, extremely sensitive radio receivers are essential. These devices must be capable of detecting incredibly faint signals that have traveled billions of light years, often losing much of their intensity along the way. The high sensitivity of modern radio telescopes makes it possible to detect these brief but powerful bursts of energy, even when they are scattered and stretched across vast expanses of space. In addition to the hardware, advanced signal processing techniques are necessary to sift through the massive amounts of data generated by these bursts. The signals collected by radio telescopes are often noisy and complex, and improved algorithms are helping scientists filter out the background interference, making it easier to identify the real signals from FRBs. The ability to process these signals in real time would further accelerate our understanding of FRBs. Real-time data analysis would enable scientists to immediately identify the characteristics and potential sources of these bursts as soon as they are detected, allowing for faster, more efficient exploration. This would require not just advanced software, but also more powerful computing hardware, capable of processing the vast amounts of data produced by radio telescopes. In addition to technological advancements in signal detection and processing, international collaborations are also playing a vital role in the study of FRBs. By linking multiple radio telescopes across the globe into a coordinated network, researchers can improve their chances of capturing these fleeting bursts and create a more comprehensive picture of their origins and behavior. An important factor in the study of FRBs that is often overlooked is the role of Earth's ionosphere, which can distort the signals as they travel through our atmosphere. As radio waves from FRBs pass through the ionosphere, they can be altered in ways that complicate the analysis of the original signals. New technologies that model and predict how radio waves are distorted by the ionosphere will be crucial in correcting these distortions, leading to more accurate data and a better understanding of the bursts themselves. Together, these technological advancements in radio astronomy, coupled with innovative approaches to data analysis, are setting the stage for groundbreaking discoveries about the universe. In the future, the potential applications of FRBs as cosmic probes could revolutionize our understanding of the universe. Because the signals from these bursts travel across vast distances, they provide a unique opportunity to study the universe's structure and evolution in ways that were previously unimaginable. One of the most exciting possibilities is the potential to use FRBs to investigate the distribution of dark matter. As these signals pass through different regions of space, any changes they undergo could provide valuable clues about the presence of dark matter and its distribution across the universe. This could have profound implications for our understanding of cosmology and the fundamental nature of the universe itself. Additionally, FRBs might help refine our knowledge of neutron stars, which are the incredibly dense remnants of massive stars that have exploded in supernova events. Many FRBs appear to originate from regions that contain neutron stars, and detailed studies of these bursts could provide new insights into the properties of neutron stars, including their magnetic fields and internal structures. This research might also reveal new information about the behavior of matter in extreme conditions, such as the intense pressure and magnetic fields found in neutron stars, which are unlike anything we encounter on Earth. Ultimately, the ongoing study of FRBs is not only advancing our understanding of distant cosmic phenomena, but also providing us with the tools to explore the deepest mysteries of the universe, from dark matter to the nature of space and time itself. As the field of FRB research continues to evolve, it promises to reshape our understanding of the cosmos in profound and unexpected ways. Moreover, fast radio bursts, FRBs, are increasingly becoming invaluable tools for exploring the intergalactic medium, the vast and largely invisible matter that exists in the space between galaxies. These fleeting high-energy radio signals, which last only a few milliseconds, have proven to be more than just mysterious cosmic phenomena. By carefully analyzing the dispersion in FRB signals, the delay caused by different frequencies traveling at different speeds, scientists are able to glean crucial insights into the density and composition of the material that surrounds galaxies. This information is helping to refine our understanding of how galaxies evolve and interact with one another across the immense span of cosmic time. In the coming years, as detection technologies continue to improve, astronomers expect to uncover an increasing number of repeating FRBs, which could offer even deeper insights into their origins and behaviors. The detection of repeating signals could provide clues to the specific mechanisms or environments responsible for their emission. This, in turn, would help to further unravel the mysteries surrounding FRBs and their potential connection to exotic cosmic events or objects, such as neutron stars or even the enigmatic dark matter that permeates the universe. FRBs are rapidly becoming a central focus of research in the field of radio astronomy, holding the potential to revolutionize our understanding of the universe. From shedding light on the nature of dark matter to unraveling the properties of neutron stars, and perhaps even beyond, every new discovery related to these bursts opens up new avenues of research and exploration. As such, FRBs are not just transient events, but key pieces of the cosmic puzzle that could reshape the way we think about the universe for years to come. In parallel, one of the most fascinating and perplexing objects in the universe is Tabby's star, also known by its catalog number KIC 846852. Located approximately 1,500 light-years away from Earth in the constellation Cygnus, Tabby's star has captured the imagination of both astronomers and the general public due to its highly irregular and unpredictable dimming patterns. Unlike typical stars whose brightness fluctuates in a regular pattern, typically due to orbiting planets or other celestial phenomena, Tabby's star exhibits strange, dramatic dips in brightness that seem to defy conventional explanations. What makes this star so intriguing is the extent of the dimming. Observations revealed that Tabby's star can lose more than 20% of its light, and these dimming events can last for days or even weeks at a time. Such extreme and sustained fluctuations in brightness are extraordinarily rare, suggesting that something highly unusual is happening around the star. Over time, these dramatic dips have sparked a variety of hypotheses, each attempting to explain the star's bizarre behavior. One of the most widely discussed possibilities is that a massive swarm of comet fragments or debris could be orbiting Tabby's star. As these objects pass between Earth and the star, they could block its light, causing the dimming effect. However, the irregularity and unpredictability of these dips in brightness suggest that the star's behavior is far more complex than what could be explained by the simple passage of comets or other small bodies. Another, more speculative theory that has captured public attention is the idea that the dimming could be caused by an artificial structure built by an advanced extraterrestrial civilization. This suggestion gained significant traction in 2015 when astronomer Tabitha Boyajian, after whom the star is named, and her colleagues proposed this possibility. The theory speculates that the dimming could be due to a large-scale construction, such as a Dyson sphere or other megastructures, designed to harvest energy from the star. Although this hypothesis remains highly speculative and lacks direct evidence, it taps into our fascination with the potential for intelligent alien life, and it has sparked widespread interest both in the scientific community and among the public. While the idea of an alien megastructure around Tabby's star might sound like science fiction, it highlights the allure of this star and the continued intrigue surrounding the search for extraterrestrial intelligence. At the same time, more conventional theories, such as the presence of dust clouds or an unusually dense collection of comets, remain on the table. The possibility of dust or gas clouds obstructing the star's light is often proposed as a more plausible explanation, especially given the irregularity of the dimming events. Astronomers have been continuing their observations of Tabby's star using a range of advanced telescopes and observational techniques to better understand its strange behavior. As technology improves and more data is collected, it is hoped that one day we will be able to definitively determine what causes the bizarre dimming of Tabby's star. Understanding its unique characteristics could provide insights not only into the nature of this star itself, but also into the broader processes at play in the environments of distant stars and galaxies. Through these ongoing investigations, Tabby's star has become a symbol of the many mysteries that still lie hidden within the universe. It serves as a reminder of the limits of our current knowledge and a catalyst for the endless questions that drive humanity's exploration of the cosmos. With every new discovery related to this star, we move closer to unlocking its secrets, whether they lie in natural phenomena or, as some hope, in the possibility of alien civilizations beyond our own. Moreover, the history of Tabby's star, its discovery, and the subsequent scientific investigations highlights an important aspect of modern astronomy, the role of citizen science. It was, in fact, a group of amateur astronomers working on the Planet Hunters project who first observed the unusual dimming patterns of Tabby's star. This discovery, made by volunteers analyzing data from NASA's Kepler Space Telescope, was the catalyst for a global scientific investigation. The involvement of these citizen scientists was crucial in bringing attention to the star, and their analysis led to the identification of dimming events that could not be explained by traditional models of stellar behavior. The unique contribution of citizen scientists has been invaluable in the investigation of Tabby's star. They not only helped identify the peculiar dimming, but also provided fresh perspectives and ideas that professional astronomers might have overlooked in their day-to-day work. This collaboration between professional and amateur astronomers helped to generate a wide range of hypotheses and fostered a collaborative atmosphere that has been essential to the ongoing investigation. Through this partnership, citizen scientists have demonstrated that curiosity and critical thinking are not confined to professional researchers alone. The collective efforts of both professional and amateur astronomers have brought invaluable attention to the mystery of Tabby's star, leading to more extensive observations and new insights into its behavior. This phenomenon showcases the power of collaboration, where people from all walks of life can contribute to the exploration of the cosmos and help uncover some of its most perplexing mysteries. As the investigation of Tabby's star continues, it serves as a case study in how modern astronomy is evolving in the digital age. The blending of traditional scientific methods with crowdsourced, citizen-driven data analysis has the potential to accelerate our understanding of the universe in profound ways. As more people become involved in such efforts, we can expect to see a broader range of discoveries and a deeper, more nuanced understanding of the universe and the forces that shape it. Tabby's star remains one of the most captivating and mysterious objects in the night sky, challenging our understanding of how stars behave and inviting us to think beyond the conventional models of astrophysics. Its strange dimming behavior continues to defy explanation, drawing scientists, amateurs, and stargazers into a collaborative effort to solve its cosmic riddle. Whether the cause turns out to be an entirely natural phenomenon or something more extraordinary, the journey to uncover the truth about Tabby's star will continue to inspire new generations of astronomers, curious minds, and dreamers across the globe. Ultimately, Tabby's star and fast radio bursts are two examples of the many enigmatic phenomena in the universe that challenge the boundaries of human knowledge. Both hold the potential to reshape our understanding of the cosmos, from the nature of dark matter to the very mechanisms behind stellar behavior. As we continue to develop new technologies and refine our methods of exploration, the mysteries of the universe will slowly begin to reveal themselves, bit by bit, one discovery at a time. The mystery surrounding Tabby's star has captivated astronomers and the public alike, primarily due to its highly unusual dimming patterns. These dimming events, which involve sudden and drastic drops in the star's brightness, appear unlike anything seen in other stars. At first glance, one might think that such phenomena could be caused by a passing planet, but closer inspection reveals a much more perplexing reality. The dimming dips in brightness observed at Tabby's star are far too extreme to be attributed to the passing of a single planet, as these dips can exceed 20 cent, a level much greater than what a planet, even a large one, could block. Furthermore, when astronomers scrutinize the light curve of the star, essentially a graph of the star's brightness over time, they find no consistent repeating dips that would suggest the predictable presence of a planet. This leaves scientists with no obvious answer and urges them to consider alternative possibilities. One potential explanation that has been examined involves clouds of dust or debris obscuring the star's light. This hypothesis seems plausible because dust particles in space can scatter and absorb light, which could result in a dimming effect. However, upon closer inspection, studies have shown that for such clouds to account for the large and irregular dimming patterns seen with Tabby's star, the dust would need to be extraordinarily dense and arranged in a highly specific manner. The precision required for such an arrangement to explain the observed dimming makes this theory less convincing. Moreover, when considering the star's behavior over time, it becomes even harder to accept this dust theory as a fully satisfying explanation. The star's dimming events do not appear to follow any predictable pattern, which is at odds with the behavior one might expect from dust clouds that would pass in front of the star and cause a temporary obscuration of its light. As astronomers continue to investigate the behavior of Tabby's star, more outlandish and speculative explanations have been proposed. One of the most intriguing theories involves the possibility of artificial structures orbiting the star, such as a Dyson sphere. A Dyson sphere is a theoretical megastructure, an artificial shell or array of solar panels designed to capture the entire energy output of a star. This would be a monumental achievement for an advanced civilization. While this idea is fascinating, it has not gained significant traction within the scientific community. The reason for this is clear. There is currently no evidence to support the existence of such a structure. No emissions or signatures that would typically be associated with a Dyson sphere have been detected around Tabby's star. While the idea of an advanced alien civilization constructing such an immense structure is captivating, it remains speculative at best, with no substantial evidence to confirm its existence. Despite the lack of supporting evidence for these more extraordinary theories, astronomers continue to rule out traditional explanations and search for answers in a more systematic manner. Utilizing sophisticated data from multiple telescopes and observatories, scientists analyze light spectra to look for signatures that could indicate the presence of planets, moons, or even dust clouds. By studying the star's light in great detail, they aim to detect the faintest irregularities that might provide clues about what is causing the dimming. Ongoing monitoring efforts are also underway, with astronomers carefully tracking the behavior of Tabby's star during dimming events. These repeated observations are crucial, as they allow scientists to capture a more comprehensive view of the star's activity, helping to determine whether the dimming is part of a natural cycle or if it is caused by an external, unknown factor. Through these various methods, researchers have narrowed down several possibilities, though no definitive explanation has emerged. What is clear, however, is that Tabby's star is a celestial body unlike any other, and its peculiar behavior invites further investigation. The mystery surrounding the star is far from being solved, but this only adds to its allure. Each new discovery brings astronomers closer to understanding the star's behavior and opens up new avenues of exploration. The search for an explanation continues, fueled by the possibility that Tabby's star could provide insight into previously unexplored aspects of astrophysics and stellar phenomena. One of the most compelling aspects of Tabby's star is the potential it holds for understanding advanced technologies, particularly those of extraterrestrial civilizations. If a Dyson sphere, or something similar, were indeed built around Tabby's star, it would suggest a level of technological sophistication far beyond anything humanity has achieved. Such a megastructure could provide a nearly limitless energy supply, drastically altering the course of civilization. The implications of such an energy source would extend far beyond technological advancements, affecting every aspect of life, from the economy to social structures. The idea of harnessing the power of a star on this scale raises profound questions about the capabilities of advanced civilizations and the potential for life beyond Earth. Additionally, the construction of an artificial structure around Tabby's star would have significant consequences for the star system itself. The mass and light output of the star would be altered, potentially affecting the temperature and environment of any nearby planets. This could make some planets more habitable, while rendering others uninhabitable. Such changes would have profound effects on the habitability of any celestial bodies in the system, offering a tantalizing glimpse into the potential for life elsewhere in the universe. The construction of such a structure also invites speculation about the social, and logistical challenges faced by the civilization that built it. How would they manage resources? How would they maintain structural integrity? And what would life be like for a species living within such a vast artificial structure? Although the Dyson sphere theory remains speculative, it provides a fascinating lens through which to view Tabby's star. It invites questions about the future of humanity and the possibilities for the survival and expansion of intelligent life. If a structure were to be found around Tabby's star, it would not only transform our understanding of that particular star, but it would also challenge our assumptions about the existence of life elsewhere in the universe. It could mark the beginning of a new era of exploration and discovery, where the search for extraterrestrial intelligence takes on an entirely new dimension. As scientists continue to monitor and study Tabby's star, they hope to unlock the secrets hidden within its light patterns. Each dimming event brings new questions and potential answers, but it also serves as a reminder of how much we still do not understand about the universe. The peculiar behavior of this star has already led to new theories and a deeper understanding of stellar evolution. By continuing to observe and analyze Tabby's star, scientists hope to gain a clearer picture of how stars behave throughout their life cycles, how they interact with neighboring celestial bodies, and how they might evolve over time. The study of Tabby's star could provide vital clues about the nature of stars in general, offering new insights into their behavior as they age and undergo changes. One of the more exciting prospects is the possibility of discovering planets orbiting Tabby's star. If planets do exist in this system, studying their atmospheres, climates, and even signs of life could yield fascinating insights into the conditions necessary for habitability. Understanding the behaviors of stars like Tabby's star could refine the search for life beyond Earth, helping scientists to adjust their expectations and technologies accordingly. As more data is gathered, researchers hope to fine-tune their models for searching for life on other planets, enhancing our ability to detect life beyond the solar system. The continuous monitoring of Tabby's star serves as a magnifying glass through which scientists can better understand the broader mysteries of the universe. Each new observation provides valuable data that could reshape our understanding of stellar life cycles, the dynamics of star systems, and the complex interactions that govern the behavior of celestial bodies. The mystery of Tabby's star challenges our assumptions, and in doing so, it pushes the boundaries of our cosmic knowledge forward. Every new discovery brings us one step closer to unlocking the secrets of the universe. To truly understand the enigmatic behavior of Tabby's star, scientists need advancements in several key areas of technology. One of the most important developments is the improvement of observational tools. As our current telescopes and instruments are not always capable of capturing the high-resolution images needed to study such distant and mysterious stars, new telescopes equipped with better resolution capabilities will be essential for making further progress. These tools will allow astronomers to obtain clearer images of Tabby's star, enabling them to analyze its light patterns with greater precision. Equally important are advancements in spectroscopy, the technique used to analyze the interaction between light and matter. Spectroscopy allows scientists to study the composition of a star's light, revealing crucial information about its atmosphere and the physical processes occurring within it. More refined spectroscopic techniques could help astronomers identify the underlying causes of unusual dimming events like those seen at Tabby's star. Another key area of progress involves data analysis. The sheer volume of data generated by telescopes and observatories can be overwhelming, so scientists must rely on advanced computational methods and machine learning algorithms to process and interpret this information. By leveraging these tools, researchers will be able to detect subtle patterns and anomalies that might otherwise go unnoticed, bringing them closer to uncovering the source of Tabby's star's unusual behavior. Finally, collaboration with space-based observatories is crucial. The development of smaller, cost-effective satellites to complement existing space telescopes would allow for continuous monitoring of Tabby's star, providing valuable insights into how its brightness changes over time. This ongoing monitoring effort will be essential for understanding the full scope of the star's dimming events and determining whether they are part of a larger, more complex pattern. Together, these technological advancements will pave the way for further discoveries and help scientists unravel the mystery of Tabby's star. By improving our ability to observe, analyze, and interpret the behavior of distant stars, we can gain new insights into the workings of the universe and deepen our understanding of the cosmic phenomena that continue to challenge our knowledge. In the end, the study of Tabby's star is not just about solving one mystery. It is about pushing the boundaries of human understanding and taking one more step toward uncovering the secrets of the universe. In the vast and boundless expanse of space, there are phenomena that challenge our understanding of the universe and the very tools we use to study it. One such enigma is Tabby's star, or KIC 8462852, a star that has baffled astronomers and scientists since its unusual light fluctuations were first observed. This mysterious object dims in ways that defy the usual explanations offered by current astronomical models. Unlike other stars, which typically fade in a predictable manner, Tabby's star swells and fades unpredictably, suggesting that something extraordinary is blocking its light. In an effort to understand this puzzling behavior, scientists have turned to a variety of approaches. One of the primary methods involves observing the star through different wavelengths of light. Stars, as we know, do not emit energy exclusively in visible light. They also radiate energy in forms such as infrared, radio waves, and other types of radiation. By observing Tabby's star across these various wavelengths, astronomers hope to unlock new insights into its environment and perhaps identify the cause of its erratic brightness. Each wavelength reveals a unique aspect of the star's surroundings, and by piecing these observations together, scientists can better understand the forces at play. Furthermore, theoretical modeling plays a crucial role in exploring the mysteries surrounding Tabby's star. Through simulations, scientists recreate the conditions around the star, attempting to replicate the intricate interactions of its atmosphere, its surrounding environment, and any potential objects that may be influencing its light. These models are then tested against real observational data. By tweaking the parameters and adjusting the conditions in the simulations, its researchers can explore various scenarios, determining which one most accurately fits the dimming behavior observed in the star. This process not only helps test existing theories, but also opens the door to entirely new possibilities, as each attempt brings scientists closer to a comprehensive explanation. Through the combination of observing different types of light, conducting in-depth analyses, and developing simulations, researchers hope to solve the riddle of Tabby's star. The star's mysterious dimming is at the heart of ongoing scientific investigations, which aim to determine whether this phenomenon is a natural part of stellar evolution or whether it points to something even more extraordinary. Could it be the result of a massive swarm of comets blocking the star's light? Or could it suggest the presence of a massive structure surrounding the star, perhaps even a Dyson sphere or another form of megastructure created by an advanced civilization? While each of these theories has its own merit, none fully account for the wide range of observed behaviors, and the mystery persists. The enigma of Tabby's star underscores a fundamental truth about our understanding of the universe. It is still incomplete. Despite the many advancements in astronomical research, there are countless phenomena that remain unpredictable or poorly understood. Studying Tabby's star serves as a reminder that our knowledge of the cosmos is constrained by the limits of our current technology and theories. As we strive to understand the universe, we are reminded that some of its most fascinating secrets remain elusive, waiting for future generations of scientists to uncover. The continued investigation of Tabby's star highlights the gaps in our understanding of stellar evolution, cosmic dust, and the potential for extraterrestrial life. Moreover, this star challenges the very way we approach our study of the cosmos. It serves as a powerful reminder that our scientific tools, though remarkable, are not infallible. As we look deeper into the universe, we realize that there is still so much we cannot explain. However, this realization does not deter scientists. Instead, it fuels their curiosity and drives them to refine their theories and instruments. The search for answers continues, and with each new discovery, our understanding of the universe expands. Tabby's star serves as a testament to the complexity of the universe and to the resilience of human curiosity, reminding us that the more we discover, the more we realize there is yet to uncover. In parallel with the quest to understand the mysteries of distant stars, the Voyager space probes, Voyager 1 and Voyager 2, embarked on their own groundbreaking journey. Launched in the 1970s, these missions were tasked with exploring the outer planets of our solar system, specifically Jupiter and Saturn. The primary goal was to gather detailed data about these gas giants, including their atmospheres, magnetic fields, and moons. The information gathered by the Voyager probes would help scientists better understand the fundamental processes at work on these distant worlds, providing valuable insights into planetary formation and evolution. The Voyager missions also aimed to explore the planetary rings of Jupiter and Saturn, which had remained largely mysterious prior to their arrival. These rings, composed of countless particles, are intricate and dynamic systems that can reveal much about the forces shaping the planets they orbit. The close-up images and data returned by Voyager 1 provided a striking look at Jupiter's Great Red Spot, a massive storm that has raged for centuries and offered new insights into the planet's dynamic atmosphere. The spacecraft's journey through the outer solar system was a monumental achievement, providing a level of detail previously unattainable. As the probes continued their journey, they passed beyond the outer planets, moving into a region of space known as the heliosphere. This vast bubble of solar wind extends far beyond the orbit of Pluto, marking the boundary of the Sun's influence. The Voyagers were not just exploring the outer reaches of the solar system, they were preparing to cross into interstellar space, a realm of space beyond the direct influence of our Sun. In doing so, they became the first human-made objects to enter this vast, uncharted territory. As they journeyed farther from the Sun, the probe sent back data that revealed an entirely new environment, one unlike anything experienced within the inner solar system. The sparse gas and cosmic particles in this region offered a dramatic contrast to the denser, more energetic conditions closer to the Sun. Voyager 2, in particular, made history by becoming the first and only spacecraft to visit Uranus and Neptune. These distant planets had remained largely unexplored prior to the Voyager missions, and their remote positions in the solar system meant that they had remained elusive to earlier missions. Voyager 2 provided the first close-up images of Uranus, unveiling the planet's unusual tilt and revealing it to be a true oddball among the planets. Uranus's unique orientation, with its axis nearly parallel to the plane of the solar system, sets it apart from the other planets, offering valuable clues about the forces that may have shaped its evolution. The probe's encounter with Neptune was equally groundbreaking. Voyager 2 captured stunning images of Neptune's vibrant blue atmosphere and revealed the planet's shifting weather patterns. The data returned from these missions transformed our understanding of the outer planets, offering new insights into their atmospheres, magnetic fields, and internal structures. The findings from Voyager 2, along with those from Voyager 1, revolutionized our understanding of the solar system's outer reaches and provided a wealth of new data that would shape future research. But the Voyager missions were not only about scientific exploration. They also carried messages aimed at any potential extraterrestrial civilizations that might one day encounter them. Each probe carried a golden record, a phonograph disc containing sounds and images representing the diversity of life on Earth. This symbolic gesture was an effort to ensure that humanity's existence would be known should intelligent life ever come into contact with these probes in the distant future. The Voyager missions, in this sense, represent not just a quest for knowledge, but also an attempt to connect humanity with the broader cosmos. As the Voyager probes continue their journey into the far reaches of space, their discoveries have fundamentally changed our view of the solar system and beyond. They have provided unprecedented data on the gas giants, the outer planets, and the space between stars, offering new insights into the nature of planetary systems, solar wind, and interstellar space. Their journey is far from over, and the data they continue to send back will continue to shape our understanding of the universe for years to come. Just as Tabby's star challenges our theories of stellar behavior, the Voyager probes continue to challenge and expand our understanding of the cosmos, showing us that the universe is far more complex, mysterious, and beautiful than we ever imagined. As the Voyager spacecraft continue their journey, their missions have evolved into a defining chapter in the story of human exploration. Far from simply gathering data about distant planets, these two probes, Voyager 1 and Voyager 2, have become symbolic messengers of humanity, pushing the boundaries of our reach into the unknown. Their journey is not only about science, it is a profound representation of our aspirations, our curiosity, and our yearning to understand the cosmos and communicate with it. These spacecraft have not just captured images and data, they have captured the spirit of human exploration and curiosity. Voyager 1's entry into interstellar space marked a pivotal moment in the history of space exploration. As it crossed the threshold into this vast, uncharted territory, it provided humanity with its first direct insight into the space that exists beyond the protective bubble of our solar system. The interaction of solar wind, streams of charged particles emitted by the sun, with the surrounding interstellar medium was a phenomenon that had never been studied before. This groundbreaking data has expanded our understanding of how the solar wind affects the broader environment of space, revealing more about the magnetic fields that influence our galaxy, the cosmic rays that bombard us from all directions, and the radiation effects that shape the universe beyond our solar neighborhood. But the Voyagers did not just push the scientific envelope. They also carried with them something deeply philosophical, a golden record, designed as a message in a bottle to any extraterrestrial intelligence that might one day encounter it. This record, crafted with careful consideration, symbolizes humanity's enduring desire to communicate with the unknown. It is not merely a collection of sounds and images, but a profound attempt to encapsulate the essence of who we are, where we come from, and our place in the vast universe. Its very existence reminds us of our desire for connection and our impulse to reach out across the cosmos, hoping that somewhere, somehow, someone or something might hear our message and recognize us. The contributions of the Voyager probes have been nothing short of transformative. Launched in the late 1970s, the Voyagers have provided humanity with a new and unprecedented perspective on our solar system, pushing the limits of what we know and uncovering extraordinary discoveries along the way. Their mission to explore the outer planets revealed previously unseen wonders, opening our eyes to the complexities of distant worlds. Voyager 1, for instance, provided us with unparalleled insights into Jupiter's atmosphere, including its iconic Great Red Spot, a storm so large it could engulf the entire Earth. It also uncovered the intricate cloud patterns swirling across Jupiter's immense atmosphere, revealing a planet in constant motion. Furthermore, the probe discovered dozens of previously unknown moons, one of which, Ganymede, is notable for the potential of a subsurface ocean, a finding that has profound implications for the search for life beyond Earth. Voyager 2, meanwhile, followed closely behind, delivering equally stunning observations of Saturn. The spacecraft unveiled the planet's stunning rings, composed of billions of particles ranging in size from tiny dust grains to massive chunks of ice and rock. It also identified numerous fascinating moons, including Titan, Saturn's largest moon, which boasts a thick atmosphere and liquid methane lakes on its surface. This discovery ignited new discussions about the potential for life in environments vastly different from our own, suggesting that the ingredients for life might exist in forms we've never imagined. As both probes continued their journeys, they reached the farthest edges of our solar system. Voyager 1, in particular, became the first human-made object to enter interstellar space, a moment that marked a historic milestone in space exploration. It was the first time a spacecraft left the protective influence of our sun's magnetic field and ventured into the cold void of interstellar space. In doing so, Voyager 1 also confirmed the presence of cosmic rays in the space between the stars, shedding light on the high-energy particles that traverse our galaxy and giving scientists their first real sense of the environment that lies beyond our solar bubble. The significance of the Voyager probe's journey only deepened as Voyager 2 ventured farther, becoming the only spacecraft ever to fly past Uranus and Neptune, two of the most enigmatic planets in our solar system. Voyager 2 revealed Uranus's peculiar tilt and its complex ring system, while providing stunning images of Neptune's deep blue hue and violent, high-speed winds. These discoveries added to our growing understanding of these ice giants, whose mysterious atmospheres and dynamic systems were previously unknown to us. The data sent back by Voyager 2 continues to inform our understanding of the outer reaches of the solar system, where the influence of the sun wanes and the cosmic environment becomes even more alien and extreme. Yet, the mission of the Voyager spacecraft was not limited to scientific discovery alone. Their golden records, attached to each spacecraft as a sort of cosmic time capsule, have become an enduring symbol of humanity's hope to transcend the isolation of our planet. These records are meant to communicate the story of Earth, not just for future generations, but for any intelligent beings who might one day encounter them. The records are carefully designed to offer a snapshot of life on Earth, showcasing sounds and images that capture the essence of who we are. The record includes greetings in over 50 languages, musical compositions ranging from classical to traditional, and visual images that depict the diversity of life on Earth, from human activities to animals, plants, and our most significant achievements. These images and sounds were chosen to give a comprehensive view of the planet and its inhabitants, illustrating the variety of life, culture, and knowledge that defines humanity. The intent behind the Golden Record is clear. It is a message of peace, understanding, and connection, sent into the cosmos with the hope that one day, someone, somewhere, might listen. The Golden Record, however, is not just a message. It is a statement of humanity's place in the universe. The inclusion of images such as human anatomy, mathematical concepts, and depictions of Earth from space is a recognition of our smallness in the grand scheme of the cosmos, but also of our potential to reach beyond ourselves. It is a reminder that, though we are a tiny speck in the vastness of space, we possess the curiosity, creativity, and resilience to explore and to understand the universe around us. As the Voyager spacecraft continue their travels, they face a host of challenges that push the limits of human ingenuity. One of the primary concerns is the extreme isolation of deep space. While both spacecraft are currently traveling through what is essentially empty space, they are not completely alone. They encounter cosmic rays, streams of energetic particles generated by various cosmic events, which pose a threat to the spacecraft's delicate electronics and instruments. These high-energy particles can cause malfunctions or degradation over time, making the longevity of the probes a concern as they continue their journey deeper into the unknown. Another challenge is the cold. As the Voyager spacecraft travel farther from the sun, the temperature drops dramatically, making it increasingly difficult to power the instruments and systems. The spacecraft's power sources, radioisotope thermoelectric generators, RTGs, are designed to convert heat from the decay of radioactive material into electricity, ensuring that the probes can continue to function even in the frigid void of space. However, over time, the power output of the RTGs decreases, requiring careful management of energy usage. Critical systems must be prioritized to ensure that they remain operational for as long as possible. Communication with Earth has also become a growing challenge. The increasing distance between the Voyager spacecraft and our planet means that signals take longer to reach their destination. What was once a communication delay of mere minutes has now stretched into hours, making real-time interaction impossible. Every message requires patience, and the signals that do arrive are often weak, subject to interference, and increasingly difficult to detect. As a result, maintaining contact with the Voyagers is becoming more and more tenuous, and the spacecraft's ability to send back data is gradually diminishing. Despite these challenges, the Voyager spacecraft remain a testament to human innovation and perseverance. They continue to send back valuable data, and with each passing day, their journey serves as a reminder of the incredible achievements of human exploration. As the probes move further from our solar system and venture into the vast expanse of interstellar space, They carry with them a profound message, one not just of scientific discovery, but of humanity's enduring desire to reach out, to explore, and to connect with the universe. The Voyagers, in their lonely odyssey, are not just machines. They are ambassadors of Earth, carrying with them our hopes, our dreams, and our story as they venture farther into the unknown than any human-made object before them. The vastness of space, with its boundless and unpredictable nature, holds dangers that could jeopardize any spacecraft on its journey. Among these unforeseen threats are micrometeoroid impacts, tiny, high-velocity particles that, though infrequent due to the immense distances between celestial objects, possess the potential to cause significant damage. Even though the Voyager spacecraft were built with durable materials designed to withstand harsh conditions, no design is impervious to all risks. One single collision could potentially disable vital components, turning the mission from one of exploration to one of survival. Despite these hurdles, the Voyager missions continue their steady and remarkable progression, offering invaluable insights into the universe. Their ongoing journey serves as a testament to human ingenuity and determination. These spacecraft, launched more than 4 decades ago, symbolize the unwavering spirit of discovery. Each step they take, each milestone they reach, speaks volumes about human resilience in the face of adversity. They remind us not only of our boundless curiosity, but also of our persistent quest to understand our place in the cosmos, no matter the distance or the obstacles. Launched over 40 years ago, the Voyager spacecraft have radically transformed our understanding of the solar environment. Their journey has provided us with invaluable data, most notably about the heliosphere, a vast protective bubble surrounding our solar system. This bubble is created by the solar wind, which consists of streams of charged particles emitted by the sun. The heliosphere, extending far beyond the planets, shields us from the harmful radiation that floods space. As the Voyager probes travel further away from Earth, they pass through an increasingly uncharted and mysterious territory. At a certain distance from the Earth, the influence of the solar wind begins to wane. This point, known as the heliopause, marks the boundary between the heliosphere and interstellar space. This is where the environment no longer feels the touch of the sun's wind, but is shaped by the material and radiation from other stars. The Voyagers, journeying beyond the outer limits of our solar system, have provided groundbreaking data about this transition. They've revealed how the solar wind interacts with the interstellar medium, the particles, magnetic fields, and radiation that exist between stars in our galaxy. The probes have detected shifts in cosmic rays, those high-energy particles that constantly bombard the Earth from all directions, and measured subtle changes in magnetic fields. These findings are not merely scientific curiosities. They're essential to understanding how our solar system functions as a shield against more dangerous interstellar radiation. The data from the Voyagers has provided a more precise model of the heliosphere's dynamic role in protecting our home planet. Furthermore, this information has allowed scientists to track how the solar wind's strength and direction fluctuate over time. The sun's 11-year cycle, which governs the intensity of solar activity, has a significant impact on the flow of solar wind and the levels of cosmic rays that reach Earth. By analyzing the data collected by the Voyager probes, researchers can now model solar behavior with far more accuracy, ultimately improving our ability to safeguard not just human life, but the vast array of technologies that we rely on for communication, navigation, and scientific research. The journey of the Voyager spacecraft has changed the way we view our solar environment. It's a story of discovery that has illuminated the importance of the heliosphere in protecting Earth from space weather. But the Voyager missions did more than simply expand our knowledge of the solar system. They represented a pivotal moment in human history, a leap into the unknown that inspired a new era of space exploration. Launched in the late 1970s, the Voyagers were designed with one clear purpose: to push beyond the outer planets and leave our solar system in search of interstellar knowledge. But their legacy has grown far beyond that. One of the most lasting impacts of the Voyager missions has been the treasure trove of data they've sent back over the years. As the spacecraft passed by the giant planets, Jupiter, Saturn, Uranus, and Neptune, They took breathtaking photographs and gathered scientific observations that completely reshaped our understanding of these massive worlds. Their findings have informed future space missions, allowing researchers to refine their strategies and improve their approaches to planetary exploration. The Voyager missions also demonstrated that sending spacecraft to places previously thought unreachable was not only possible, but feasible. Through their daring journey to the outer planets and beyond, the Voyager spacecraft proved that humanity was capable of sending machines to places that no human could ever travel. The success of the Voyager probes has since paved the way for future missions that aim to explore the farthest corners of our solar system and even beyond. For example, the New Horizons mission to Pluto and the Juno mission to Jupiter owe much of their inspiration to the pioneering path laid by Voyager. Another iconic legacy of the Voyager missions is the Golden Record, a message to potential extraterrestrial life that was carried aboard each spacecraft. This record contains a variety of sounds and images meant to represent the diversity of life and culture on Earth. It was a symbolic gesture, a way for humanity to say, "We here." The inclusion of this message reinforced the spirit of curiosity and exploration. It's a symbol of our longing to reach beyond our planet, to communicate with other intelligent beings, and to understand our place in the universe. The Golden Record has sparked fascinating discussions about the possibility of contacting extraterrestrial civilizations and, on a more philosophical level, about the fundamental nature of human existence. The Voyagers have not only changed the way we think about space, they've also laid the groundwork for technological advancements that continue to impact life on Earth. Operating spacecraft over such vast distances, where communication delays can stretch to hours, has required the development of innovative technologies. Engineers had to find ways to send vast amounts of data back to Earth using limited bandwidth. The techniques they developed for data compression and efficient transmission have become standard practice in modern space missions and beyond. Furthermore, the challenges faced by the Voyager spacecraft, operating in extreme conditions, enduring intense radiation, and surviving countless micrometeoroid impacts, have spurred innovations in material science and telecommunications that benefit industries outside of space exploration. The Voyager missions have also instilled a sense of unity and wonder among humans. As these spacecraft journey further and further from Earth, they serve as a constant reminder of how small our planet is in the vastness of the cosmos. Yet, in that vastness, they show us something extraordinary, that we as a species have the power to reach out into the unknown and make meaningful discoveries. This perspective has been invaluable in shaping our attitudes toward future exploration, be it the study of Mars, the potential for human missions to distant planets, or even the search for habitable worlds beyond our solar system. In a way, the Voyager spacecraft have done more than transmit data. They've transmitted a message of hope, determination, and curiosity. Their continuing operation has inspired future generations of scientists, engineers, and explorers. Through their ongoing journey, they've shown that the spirit of discovery never fades, and that the pursuit of knowledge is a never-ending adventure. As they journey through the stars, the Voyager spacecraft have sparked a wave of new questions about the nature of the universe. They have encouraged humanity to ask deeper, more profound questions about our place in the cosmos, igniting a passion for exploration that will drive us to discover more about the stars, the galaxies, and perhaps even the unknown reaches of interstellar space itself. The legacy of the Voyager missions goes far beyond the spacecraft themselves. They represent the culmination of human curiosity, ingenuity, and a relentless desire to push the boundaries of what is possible. More than just machines designed to gather data, they are symbols of what humanity can achieve when we dare to dream and explore the unknown. The lessons learned from the Voyager missions will continue to influence space exploration for generations to come, reminding us that no matter how far we travel, the journey of discovery is a path without end. The Voyager spacecraft, launched in the late 1970s, are more than just extraordinary feats of engineering and technology. They have become symbols of humanity's unyielding curiosity, our ceaseless desire to explore the farthest reaches of the universe. Their most iconic moment, the pale blue dot photograph, taken from a distance so vast it defies comprehension, captures Earth as a mere speck in the infinite cosmos. This image, both humbling and awe-inspiring, serves as a poignant reminder of our fragile place in the universe. It transcends the realm of science, touching on deep philosophical reflections about existence, meaning, and our collective responsibility as stewards of this tiny yet precious planet. This single photograph, more than any other image captured by the Voyager spacecraft, encapsulates the core of the human spirit, our boundless curiosity, and our drive to understand the unknown. It challenges us to think beyond the narrow confines of daily life, urging us to consider the broader implications of our existence. The power of exploration, it turns out, is not just about the scientific data we collect or the discoveries we make. It is about the way these endeavors inspire us to reimagine who we are and what we can become. Voyager, in its journey beyond the known reaches of our solar system, is not just a tool of science. It is a bridge that connects us to something far greater than ourselves. The Voyager missions underscore the fact that long-term space exploration is not simply a matter of advanced technology. It requires foresight, ingenuity, and the ability to think decades ahead. Durable design is paramount. These spacecraft will withstand the extreme conditions of space for years, if not decades, to come. Redundancy in engineering ensures that even if one system fails, there are backup systems in place to continue the mission. This strategy has proven to be invaluable as the Voyagers continue to operate, sending back data and transmitting signals from the furthest corners of our solar system and beyond. Communication, too, is a critical element. Efficiency in this regard has allowed scientists to receive valuable data from these distant Voyagers, despite the vast distances involved. But perhaps the most significant contribution of the Voyager missions is their ability to inspire. The success of these missions speaks to a larger truth, that science, exploration, and human ingenuity have the power to inspire generations to come. The Voyager spacecraft are not just mechanical devices, they are ambassadors to the cosmos. Their journey represents a monumental leap for humankind, moving beyond the boundaries of our familiar celestial neighborhood to explore the outer planets and their moons. With each passing year, the Voyagers send back images that reveal a universe teeming with wonders. Who could forget the first photographs of Jupiter's swirling, multicolored clouds, or the striking images of Saturn's majestic rings, each photograph carrying a message from a distant world, offering us a glimpse into the beauty and complexity of our solar system. These images and the data that accompany them are not just scientific achievements. They are windows into a larger universe, each one capable of capturing the imagination of young minds and sparking a lifelong passion for space exploration. Imagine a child, eyes wide in wonder, seeing the images of these distant planets and moons for the first time. Perhaps they marvel at the vivid swirling storms on Jupiter or the icy rings of Saturn, and in that moment, a new sense of possibility is born. For this child, the universe suddenly feels closer, more accessible, more inviting. They are no longer simply looking at pictures. They are seeing a vision of the future, a future that might one day include them as explorers, scientists, or engineers, uncovering the mysteries of the cosmos. The Voyager missions offer a roadmap for what is possible when we combine imagination, creativity, and a determination to reach beyond the stars. These spacecraft do not just explore the outer planets, they reshape the way we think about the universe. They have uncovered phenomena that were once the stuff of speculation and theory. Take, for instance, the discovery of intense magnetic fields around Jupiter, or the water vapor plumes erupting from the icy moon Enceladus. These findings have opened new avenues of scientific inquiry, igniting curiosity not only in scientists, but in students and the general public as well. The study of planets, moons, and distant worlds is no longer confined to textbooks and classrooms. It has become an adventure, a real-world exploration that captures the imagination. Voyager has shown us that the universe is a vast, dynamic, and mysterious place, filled with phenomena that challenge our understanding and fuel our desire to know more. Moreover, The ongoing journey of the Voyager spacecraft into interstellar space offers a powerful lesson in perseverance. These missions, launched decades ago, continue to function, sending back data and maintaining communication with Earth from distances farther than any human-made object has ever traveled. The fact that Voyager 1, for example, is now over 14 billion miles from Earth, still transmitting signals after more than 40 years, speaks to the durability of human ingenuity and the power of setting bold goals. It also serves as a reminder that human achievement is not confined to the present moment. It is something that endures, something that can have an impact across generations. The fact that the Voyager spacecraft will continue to send data back to Earth for many years, even as they journey into the vast unknown, is a testament to the resilience and long-term vision that defines the best of humanity. Finally, the broader implications of the Voyager missions cannot be overlooked. One of the most profound aspects of the Voyager spacecraft is the golden record they carry, an audio-visual message intended for any intelligent life that might encounter it. This golden record contains sounds and images that provide a glimpse into the diversity and richness of human life on Earth. It includes music, greetings in 55 different languages, and images of our species, our planet, and our culture. The golden record is more than just a scientific artifact. It is a message of peace, a message of hope, a message that says to any beings out there, we are here. This idea, the notion that we are sending a message into the cosmos, a signal to anyone who might be listening, is deeply philosophical. It raises questions about our place in the universe, the nature of intelligence, and the possibility of life beyond Earth. For young dreamers, the golden record inspires deep contemplation about existence and the possibilities of life elsewhere in the universe. The Voyager missions are about much more than simply exploring the outer planets. They represent a profound leap in human understanding, a journey that inspires us to think bigger, to look farther, and to question what is possible. These missions continue to be a source of inspiration, not just for scientists and engineers, but for anyone who dares to dream of a future that goes beyond the confines of Earth. The legacy of Voyager is one of hope, creativity, and endless possibility, a legacy that will continue to resonate for generations to come. And as we look up at the stars, we are reminded of the infinite potential that lies beyond, waiting to be explored.